Woo! All right, I'm Anthony Francis, and I would like to welcome you all to the 5th annual Embodied AI workshop. And we have been running for a while, and I'm going to give you just a brief introduction to the workshop and to Embodied AI. First, I wanted to give a shout out to our organizers. In addition to myself, our lead organizers include Claudia Perez-Darpino from NVIDIA and Luca Weiss from AI2. We are supported by a wonderful committee, including Ade Famadi, Angel Chang, Changhan Chen, Cheng-Shu Lee, David Hall, Devin Helm, Joel Jang, Lamberto Balin, Matt Dietke, Mike Roberts, Naoki Yokoyama, Alexander Maksamets, Ram Ramyaka, Ran Gong, Rin Metcalf, Zorn Perk, and Jonathan Bisk. Our scientific advisory board includes Alexander Toshev, Andrei Kolobov, Aniruddha Kemavati, Dhruv Batra, Herman Ross, John Truong, Manolis Sava, Roberto Martin, and Rusva Mataki. We are also blessed with a whole number of challenge organizers, and I'm going to let them introduce themselves during their own challenge presentations later during the day. So we have been running for 5 years, starting in 2020. And over the years, we've had a number of challenges, a number of speakers. And one of the questions that came up, and over at the 3rd year, we did a retrospective paper, which you can find on Archive, which documents the first 3 years of progress on our embodied AI challenges. Even though things continue to improve with the different workshops, I still get asked this question of what embodied AI is and why it just isn't robotics or computer vision. And so first, I like to distinguish what isn't embodied AI, and classical open loop robotics is not it. Still to this day, there are robotic systems where if everything is not perfectly aligned and anything is wrong, the robot is going to execute a fixed trajectory and it's going to bung up its manipulator, or it's going to weld the wrong part. Ask me how I know about the latter one. And it's also not classical image classification. We're not taking a point in image space and trying to classify it or extract a segmentation or do a comparison with another image. Embodied AI is about interacting with an environment. And here you have a robot from Google, or it's from Fetch, but this is at Google, where it's trying to get to this corner over here, and the path that it originally planned was blocked off by this cart. And it dynamically replanned. And this is a technique called PRMRL, where we're combining probabilistic roadmap with reinforcement learning for it to do dynamic replanning. And generally, when we have these trajectories, we have some notion that the trajectory was good. But as we've recently seen, we're going beyond this and going beyond a solitary embodiment where we can readily examine the trajectories. So here we have, in an open set problem, this is a system called Vader from Google, where the robot is performing open set tasks, and it uses a language model to plan, but a visual language model to detect issues that it can't cope with. In this case, it's not able to quite reach the Coke can on the table. It asks the human for help. The human does so, and they have a little negotiation when the human thinks that the robot can pick up the task, and then it checks itself and then moves on. So because this task didn't necessarily exist before, we don't precisely have a notion of whether or not it's just good, like we got to the corner of the room. The human and the robot have to negotiate a shared meaning of whether or not the robot's behavior is right. So classically, we talked about embodied AI as agents that can see, hear, act, reason, and converse. And it's been putting together through increasing complexity beyond the functions and images to interaction with environments, collaboration with shared meaning. And this increasing complexity has been enabled by a whole bunch of advances in the community. Robotic, even moving the arm in the fixed paths required inverse kinematics. Getting the images required labeled data sets. But then we started doing things with Markov decision processes, model predictive control to enable robots to move in spaces. And now we have foundation models and effective simulators that enable even more complicated systems. But to me, what makes embodied AI is the fact that we have these challenges where people put together a set of problems and a data set or simulator, and then we try to solve them. And initially, the community starts out, did something just happen to the, this is Yeah, it seems to be happening in a lot of the rooms. Are we back? Okay. Is there a way to? Okay. So I'm back on. Okay. So when the challenges start, they're difficult to tackle. People don't get them quite right. But then over a while, the challenges get solved. We have solutions that are deployed. We have findings, such as whether or not maps are required for navigation. And these lead into new tools that we use, and the challenges in turn get updated. So I really see embodied AI as not just AI, which is looking at the world and trying to, the world that it has to interact with. It's a research field that's being reshaped by its own work. We don't just like recognize cats and then deploy that on the phone. We collaborate with the human and then say, well, we need to make this collaboration problem harder in the next iteration. So how's this workshop been shaped by that? Well, our theme is open world embodied AI. The three sub-themes are embodied mobile manipulation, which is arguably the foundational task of open world embodied AI, generative AI for embodied AI, which is using generative models to create policies or training data sets, and language model planning, where we use language models to attempt to direct the robot what to do. And especially with the papers, you'll see that we accepted on the website, which will be going up after CVPR. We have perennial themes around simulation environments, visual navigation, rearrangement, and embodied QA, vision, language, and hearing. We'll be presenting 6 challenges today, including navigation and social challenges like multi-on, multi-object navigation, hazard, rescuing objects from fires, PRS, which is social navigation, manipulation challenges like ManiSkill, which is a visual, tactile simulation task this year, and Arnold and OVMM, which are mobile manipulation challenges this year. Our speakers include Aniruddha Kembavi, Brian Ichter, Sharon Song, Chris Paxton, Eric Jang, Richard Newcomb, Olivia Norton, Richard Bathicki, and Ashley Lawrence. We have 31 accepted papers. The poster session will be at 1 p.m. in Arch 4E, posters 50 to 81, and the papers will be on the website after CVPR concludes. I deny all knowledge that we're scrambling to get all the camera-ready copy. I didn't say that. Our sponsors this year include Project Aria, Microsoft, and Logic and Robotics, and we want to thank them very much for their support in bringing this conference together. And they are going to be providing an award of 300 to the first place winners of each of the embodied AI challenges. So thank Microsoft, thank Project Aria, and I'm not going to thank Logical Robotics because that's me, and that'd be kind of awkward. So our schedule, after I stop yapping, we'll talk about our navigation and social challenges at 9. Aniruddha Kembavi will talk about generative AI at 10. Microsoft Ade will lead a panel on advancing embodied AI at 10:30. Brian Ichter will speak about language model planning at 11. And then Richard Newcomb will talk about Project Aria at 11:30. We'll break for lunch, and then the poster session is, again, from 1 in Arch 4E, posters 50 to 81. Our manipulation challenges will be at 2. Embodied mobile manipulation talks will be at 3 and 3:30 from Sharon Song and Chris Paxton. And Eric Jang will speak about humanoid robotics at 4. And we'll conclude with the speaker panel moderated by Claudia Perez-Dapino from NVIDIA. So without any further ado, I would like to welcome you all to the 5th annual Embodied Artificial Intelligence Workshop. And we can get started with our navigation and social challenges.
Oh, I'm so sorry. uh, Sorry. We have a constraint on the maximum number of steps, which is like set to 2,500 in our case. The agent has access to RGB images, depth images, relative GPS and compass, which is relative to the start position of the episode. It has access to the goal specification in terms of language instruction. This year, we have set our data set on Habitat Synthetic Scenes dataset, which is a collection of high quality 3D synthetic scenes. And it has a diverse set of objects. Specifically, each of our episodes contain 3 goal objects, and which is made available to the agent one after the other. And each of the goal is described using language instruction. So for example, find the candlestick on the buffet. So each of this instruction might have a spatial relationship, for example, candlestick on the buffet, or like it has a varying granularity of object descriptions. So it might say, go to the candle, or it might say, go to the red short pillar candle. So in case of coarsely specified object description, we have multiple correct goal locations, and the agent, if navigates to one of the goal locations correctly, it is considered a success. Here are a couple of examples from our episodes. So for the baseline, we combine 2 methods, MOPA and VL maps. So we base our baseline on the MOPA architecture, which is a modular approach, and it has different modules in it: object detection, map building, planning, exploration, and navigation. But we substitute the object detection and map building with VL maps to support the open vocabulary nature of our approach, of our task. So VL Maps basically builds a map with clip image features, and our approach selects the location which maximizes the similarity score with the object description. Coming to the leaderboards, we had 3 teams submitting to our challenge this year, but in the end, only 1 team finalized the submission, and it outperforms the baseline. Congratulations, team Intelligo Labs. So Francesco is here. I will call him up in a few minutes, but like in a few seconds. Sorry, but before I do that, let me thank the workshop organizers for organizing this, the Eval AI team, the Habitat team for supporting us in this challenge. As a reminder, we'll keep the challenge open. So I'll ask all of you to check it out and get back to us if you need any help. Now, Francesco can go in detail into his winning entry.
So next up is the hazard challenge, who are remote.
Hello. Yeah, I'm remote. Hi. Hello, I'm Qinghong Zhou from the UMass Amherst. Today I'm going to introduce the hazard challenge, the embodied decision making in dynamically changing environments. Sorry. Okay. Hazard is a challenge about rescuing objects from disasters, including fire, flood, and wind. Here are several examples of agents and scenes. And this challenge focuses on the embodied decision-making problem. We especially focus on the dynamically changing environments. Let me briefly introduce the motivation on this. First, the decision-making in a dynamically changing environment is an important way to evaluate the embodied agents. Because this type of environment is featured by rapid changes, great uncertainty, and complexity. To overcome these difficulties and make good decisions, the embodied agents are required to first perceive these environmental changes, then reason the dynamics and future developments of the changes, and finally, they need to consider these factors during their planning, and therefore find the best plan in the dynamic environments. Second, this kind of things in dynamically changing environment is closely connected to real-world applications, such as the search and rescue. However, studying this topic in real world is not very proper because the implementation of the rapid changes is both dangerous and expensive. Therefore, we need to simulate the changes in the simulators. In this work, we choose the 3D World simulator from the MIT. This simulator is featured by its powerful dynamics and simulation and the realistic image rendering. Here's an overview of this challenge. We name it Hazard Challenge because it includes these three disasters, the fire, flood, and wind. We first implement the simulations of these three disasters based on the 3D world. In an indoor fire scenario, the flames spread rapidly throughout the house, potentially destroying the flammable target objects. And in an indoor flood scenario, the large amount of water continuously pour into the house, flooding the non-waterproof target objects. And in the outdoor wind scenario, the strong winds blow lightweight objects far away on the road, making the retrieval difficult for the agents. And based on the simulator of these three disasters, we make data sets with hundreds of scenes with procedural generation pipeline, also based on 3D World. And here's a brief introduction of how these disasters are simulated. This can be separated in this page, including the physics-based simulation and the image rendering. And for the fire scenario, we built a temperature system which maintains the temperature of all objects in the simulator and updates them according to these equations. And the temperature difference of an object in the next time step is determined by the background temperature and the temperature of other objects. And finally, an object will be ignited when it reaches the ignition point, and after burning a constant time, the state of an object will turn to burnt. And for the flood scenario, the objects are affected by buoyancy and drag forces. We calculate these two forces according to the right two equations. The water surface will rise with a constant speed, and when a non-waterproof object is submerged by water, it will be flooded. Then we render the visual effect based on the physics simulation. These pictures on the top shows the visual effect of the fire and flood. And in the hazard challenge, the objective of an embodied agent is to rescue a predetermined set of target objects and bring them to a safe place, such as a bag held by the agent or a shopping cart. As this page shows, at each time step, an agent receives an RGBD observation, semantic segmentations of the observation, and a blurred environment-specific observation, like the temperature in fire scenario and the water level in the flood scenario. We also provide a perceptual version of hazard, which excludes the semantic segmentation from the inputs. Given these observations, agent must make proper choices from the available agent action space at each time step, which will be introduced in the next page to finish the task. And they'll finally be evaluated by these three metrics, including the value, which is the proportion of the rescued object's value to the total value, and the steps, which measures the speed of the rescue, and also the damage, which measures how many objects are damaged during the rescue. During the rescue. And in Hazard, we use this humanoid agent with actions in these pages. For the high-level actions, we include explore action, and robust pickup action, and a drop action that helps agents put down an object. Therefore, once the agent reaches the object, it can use the pickup action to hold the object, and then use the drop action to position it in a safe location. The hazard also supports direct utilization of low-level actions, including the move by, turn by, which can be a certain distance or a certain degree, and also other low-level actions. The hazard challenge mainly focuses on the evaluating the decision-making abilities of the embodied agents. However, we also provide some additional settings to support comprehensive evaluation of embodied agents. For example, the perceptional version of hazard does not provide the ground truth segmentation as input, which requires the agent to perceive by itself. And the effect on agent setting will let hazards affect agents, which makes the challenge much more difficult. For example, the agent have its time limit, have its temperature limits, which keep it away from the fire. And we also provide an out-of-domain test set, which includes new objects to assess the generalization capability of embodied agents. Okay, and that's the introduction of the hazard challenge. Thank you for listening.
Okay, next is the ERS challenge, I believe? Yes. Yeah. Yeah. Are you connected to Zoom? Okay. You can, oh yeah, but you need to be connected to Zoom so people on the internet can see it. The link, yeah. Oh, no.
One moment while we get connected on the Zoom.
Less than, oh, no, it's not something.
Recording in progress.
Oh, and mute and then share screen. I think you'll need to unmute them. Yeah. Oh. Good point. Oh, yeah. Oh, thank you very much. Yeah, I'm Hao Dong. I'm an assistant professor from Peking University, and it's my pleasure to share our challenge, human center in building delivery. The integration of embodied AI into humans' life has been a trend, and we have already explored various types of embodied skill like manipulation, grasping, and navigation, and so on. But however, we have noticed that there is still a gap between the current EAI paradigms and the human's expectation. And we believe that the human-robot interaction should be the answer. And it also build new challenge and new topic to the embodied AI communities. So we propose our challenge, human-centered in building delivery, and it comes from a real business scenario, and a robot stay in a building for a long time period and serve a group of people based on their instructions. For this challenge, we built a virtual 3D story building, and it is inspired by a real polar research station from the real world. This building contains rooms with many functions, including a warehouse, a supermarket, medical room, office, laboratories, and so on. We have built a small community within this building, including 10 human characters, and each one had their own individual settings, profile, and behavior generated by large language model. We also provide hundreds of items for interactions. We have also built a robot prototype that can grasp, move, and deliver objects with 2 RGBD camera as the sensor input. Let's see a case for running example of this delivery service. First of all, we have the large model driven NPC, for example, John, go up and way out of his room. He asked the robot to bring him a bottle of water and put it in the office. So when we receive these instructions, the robot took the elevator from the first floor to the third floor to search for the water. Based on John's profile, when the robot grabs the water, and then the robot will navigate to John's office and hand over the water to John. Using this building environment, we can actually generate massive number of the tasks, and by sampling the items, characters, and in different behaviors. We also generate a lot of task case for evaluation, because all of the tasks are generated by LLM, so we can actually generate infinite number of tasks. But we also have a large number of tasks for evaluation purpose. And the evaluation metric is quite simple, just to tell whether the target object is successfully delivered in limit time or not. And we also provide a list of API for user to control in low-level way or in the LLM style. And we have also proposed a simple model as our baseline. We use the LLM to pass the human instruction and the profile to obtain the target objects, person, and delivery location. We use a LLM and a zero-shot object detection model to help robot to grasp the object. And after capture the objects, the robot should navigate to the target location. Here is some baseline results. We have achieved around 32% success rate. And we have also, for the challenge, we have invited many teams to participate. And we have a winner team called PDA. They are from JSU and USC, Xinrui Wang and Feng Wang. We will still working on this project, and we will release a new version of the environment, which may contain many new features. And yeah, so in the end, let's build a virtual human room community together for embodied research. Thank you very much. Okay, where is the team? So
Yeah, I would ask, for the social navigation challenge, that.
So
Yeah, sorry.
I don't know whether the team is there. So you go ahead and.
So, if team's not here, we can coordinate with, the organizers for me to get their stuff after the challenge. And we're supposed to be handing out awards, when the challenge has had an award, so, we have a lovely certificate if the challenge teams are here, and, please forward it to them and coordinate with me if they aren't here today. So, thanks to our sponsors for making the.
With that, I can see we're now going to be having the social and navigation challenge panel. So if I can ask the coordinators of these challenges to come up to the panel area here. We have questions able to be submitted through Slack. Do we have a Slack?
No slide, but yeah. And we also
So-
have the hazard challenge organizers who can join remotely if you're around.
Yeah, we are wrong.
So anyone in the audience, if you have questions on the Embodied AI organization website, there's a link to our Slack where you're able to ask questions of these challenges under the tag questions for navigation. And we'll be asking questions of the panelists from there. That's what we've got our set up. Okay. If we're all ready, I'll start with a fairly general one. So why is it that as a community for embodied AI that we still struggle at navigation? What is the big problem that we still haven't overcome by this point?
I think for.
Yeah.
Yeah, I think for navigation, the zero shot problem. The zero shot problem is still very challenging, and also the perception problem is also quite important. For example, if the robot scan the room once before the robot navigate in the environment, then I think if we have a 100% accurate perception model, that can solve a lot of problems.
From my perspective, I would say that we have solved the point-to-point navigation, but what we haven't solved is the semantic navigation and mostly long horizon navigation. I guess that's one thing that is we're still working on as a community, and that's something we need to think of.
And Kuihan? Anything you'd like to add, Kuihan?
Oh, yeah, I've seen the question in the Zoom. I'm reading it. Sorry. Oh, yes. Sorry, I didn't hear it very clearly. The question.
The question is essentially, why are we still struggling at navigation in embodied AI systems?
Yeah, I think it's a big question. I mainly agree with Professor Dong says, and it's perception is a big problem, and also for some long horizon, so we need some like hierarchical to like finish this long horizontal task. Like in the hazard, it's a very complex task, and it needs some strategy in the problem solving. So that's my point of view.
Thank you very much. Next question is on the sorts of challenges that we've been creating as a community. So there's been generally a lot of focus on tackling this problem in indoor environments where a lot of the time the challenge is finding the objects or avoiding obstacles. But what do we think about outdoor navigation and the fact that you also have to find reliable terrain that's suitable for your particular type of embodiment? Should we, as a community, focus a bit more on these areas rather than always pigeonholing ourselves into an indoor environment?
The reason we're doing that because we haven't solved indoor. I don't know.
Answers like GPS from and application, but for indoor environment, actually we are facing different trends. As a small object, we usually ask the object to press an object under that building. So actually we made the I think in our opinion, the environment should have more diverse tasks for people. I think we need and many people.
Okay. Wei Hang, do you have a take?
Oh no, I think the outdoor is much more complex than the indoor as the same kind of problem. It's from the perception point of view, also the terrain and much more factors to consider in the outdoor.
Okay, thank you. All right, let me see if I can summarize this one. It's a bit long. So essentially in our current research, we are primarily dealing with two types of simulators. Habitat, rendering a 3D map of a real world environment, or an asset-based simulator like Isaac Sim. However, there doesn't seem to be a seamless transition from world-based data sets that are based on a 3D scan and objects-based ones that actually allow you to manipulate the environments. Is this a correct assumption about how our current simulators work? And if so, how might this impact our development of embodied AI? The fact that with some highly realistic scans, we've got no direct interaction with objects, but anytime we want to add interaction, we downgrade our realism.
Yes, the latest habitat sim has the ability to add objects into it and interactable objects. I think people are aware of this thing and they are working towards it. So I would say we will have something like that very soon. Yeah.
I think for the long-term goal, we hope a single simulator that has more gap in the visual pieces and also one flux. That is our goal. But actually at this moment, I think this goal is quite challenging. Even though Isaac Sim and Omniverse have shown some promising results, but in the short term, I think a better way is to have two types of simulator. One is good for running the manipulation policy, which have a very small simple gap in physics and visual, but maybe it will take a longer time for rendering the data. And the other simulator is for
for the learning the high level planning tasks like navigation and like the high level interaction with the human, just like our PRS challenge.
Oh yes, it's also a step-by-step problem from the interactive the level, and also from the scene, like from the indoor to outdoor, from the single room to multi-room is like a step-by-step, and it's still a long way to go.
Ratio should be the less direction. But as what I say previously, then the long-term goal we should have a single simulator, but at least for this moment, if we want to learn such policy, then we can actually have two kind of simulator for different tasks.
So yeah, the long term goal is to be able to manipulate, be able to interact with the objects, but first we need to.
Yeah, I'm trying to, we're not showing up on the Zoom, so I'm trying to get the,
Oh.
okay, that's not gonna work. Never mind. Sorry, Anthony.
Like, the agent needs to navigate the object to be able to interact with it. So it kind of like navigation, say, is the first step, and then the manipulation is again dependent. So some be dependent on the navigation, because yeah, that's what I think.
And that because for mobile manipulation, when you already navigate to a specific region, for example, just in front of a door, then you start your mobile manipulation policy. And but while you manipulate the door, like opening the door, then your base actually won't move for a long distance.
So I'm gonna just a quick question. So on that, I think a big part of navigation, right, is actually getting into the spot, or manipulating an object, is being in the spot where you can actually grasp the object, and that's itself a very hard problem. It's not just object navigation, and so do you think there are other tasks for which navigation is like actually very important, or are we really just trying to do a manipulation task, and then getting towards the object is good, but should we be really thinking much more heavily about manipulation, or is there something we can use to like fill the gaps there?
I think we can tackle these two problems separately and then find a way to have some sort of a modular approach and like activate different policies when we do different things. So we can like utilize the navigation policies which have done good in the past and then plug it in the manipulation. But I think the manipulation target needs to be handled separately.
Yeah, I also agree.
All right, the next question I might start with Queen Hong. Many navigation methods created, trained, and tested environments that don't involve humans. Do you think that sets them up for failure when they are inevitably deployed in environments that have humans in them? Would you suggest changing the general training paradigm, or do you think this actually won't lead to any performance issues?
Thank you. I did not have not done any human experiments, so I currently have no idea on it. But I guess that it will be a great gap for human And I think the Habitat 3 has also involved a pattern like human and the agent, and and this pattern will I think it is very promising for the future human in the loop learning. Yeah.
Thank you. And from your experiences, what do you think is the human in the loop a critical part? Are we going to have our systems fail if we don't involve some human involved in our environments, or is it only a minor problem?
At a fair system is the policy that don't involve human.
Yeah, so like, because we've got these environments that are going to have lots of humans involved in them, do you think if we set up our navigation type challenges that don't involve humans just interacting in the environment, that we're going to set ourselves up for failure?
I think actually we can evaluate different subtasks individually. For example, for the
Speak a bit louder and into the microphone.
yeah, I say we can actually evaluate different subtasks individually. For example, for the physical interaction task like grasping or manipulating the articulate objects, then we have one set of the matches. For example, whether the object had been successfully grasped and then picked up. But for the human interaction, actually, it's a high level task. So for all the high level tasks, navigation or object navigation, visual language navigation, or even the demand-driven navigation, then we can have another set of the evaluation matches for that. But of course, we can also have in our challenge. Actually, we have achieved, the baseline have achieved 32% success rate, right? But in that success rate, we assume all the physical interaction have 100% success rate. We assume the robot always can successfully grasp that object, always can successfully open a door, or push the bottom of the evaluator. And that's how we can separate the evaluation.
So I think if we train end-to-end systems, that's probably going to fail when the humans come in the real world. But that's where I'll advocate for like modular approaches and not reinvent the wheel. So maybe if we like use a robot who's capable of collision avoidance, for example, then I think it can be plugged into our high-level semantic planning module, and then it can pretty well.
Yeah, so all of the techniques that get created as part of these various challenges get used as the high-level planner, but for your basic sort of dodge stuff that's moving around in the environment, use another system.
Traditional systems work pretty well, right? So why do we need trained module policies for that as well? We might combine everything.
Makes sense. I'm going to ask a question. So we've brought up a couple of times the issue of realism, physical interaction versus non, for the different types of scenes that we create versus of scans versus fully simulated environments. Do any of the presenters here think there's potential in the world of neural fields, Gaussian splats, particularly those that are able to include physics? Good. Those are able to include physics that might be the solution to this problem? Or is it just a potentially interesting source of technology?
To me, it's very interesting potential sources of technology, but I personally haven't tried any of it, so I don't really think that much.
Yeah.
Actually, I've tried some construction method to construct like outdoor scene, but I think the current technology is still not capable for the outdoor embodied environments. But maybe we can try from some simple things like single room or other kind of simple things.
So you're saying the problem is scale, or it's the realism factor that you've just not been able to get for your particular types of challenges?
You mean, sorry? You
Is
mean-
your issue with the technology one of being able to generate scenes at scale, or is it that they just aren't suitable for your sort of challenges, specifically the inclusion of hazards and things like that?
Oh no, it's another one. It's like I was trying to generate at a scale, but I currently is not successful on it.
Jonathan? No, okay. Right, lost my list of questions. Could it be of interest in injecting navigation tasks that cannot be achieved in any case? So the agent at some point has to understand and communicate to the human, like you're going, I want to get to this location, but there is something blocking my way, or I do not have the right embodiment to get past this problem. Would that be an interesting part of a future navigation challenge?
Yeah, I think the limitation of the embodiment may be a research challenge. And the future solution may have two ways. The first one is to utilize the LLM, VLM. We hold the VLM to answer question that whether the robot can successfully achieve that task. For example, an object that is too high, then I cannot grasp it. Okay, we hold the VLM can actually answer that. And other solution is if we don't use the LLM, then probably we have some other methods for that. For example, affordance methods. If we want to open a grasp an object, but unfortunately, then the grasp hole cannot be predicted. That is because when we predicting the grasp hole, we also basis on the condition of the robot location. Probably that should be the way. That is also what we call the condition aware information.
Kuihong?
Sorry, I have no further ideas on this question.
Okay. We were muted. That's my bad. Trying to mute and unmute whenever I go to Kuihong. So Kuihong, so you might not have heard the question then. So the question was basically, what is the most important design aspect that your team sort of came up with when you were trying to create your challenge? What was the most critical design decision you had to try and think of in terms of accessibility or challenge difficulty level? What was the most important sort of decision you had to think of?
Oh yeah, I think for our team is the critical problem is the difficulty of the challenge. Like we can design the challenge like the input signals or the task to set it to a proper difficulty. But I think it's really I think it's really difficult for a challenge like that. Like Hazard is full of dynamics and and it is requires agent to have this strategy. So we have to select which input signals we shall give to the agent and which are not. What task it shall complete shall to do. I think it's a critical problem for our challenge.
Cool. Thanks very much. And yeah, some questions from the audience. If there was anyone. Yep. All right, so for people online, so summarizing the question, are we focused on the right thing in having all these challenges purely in simulation? Will they translate well to the real world when we can perform machine learning on real world platforms now? Is this the right direction for us to go as a community to keep focusing on these simulated challenges?
For example, if we just use other type of camera model file or install the camera in different kind of, but now we can see that for navigate the state of the art navigation methods are basis of large model. So when using the large model, we don't even need to some method don't even need to fine tune the model. We just use it and then set up a group. Use that form of the vision, so on, and just make the application done. And using that in large model, we have also that the simple work. Even though when you evaluate as you develop something simulate like that, just not very realistic, but you just apply that model you want, then it seems to work out actually. Yeah. So I think so nowadays, then that's why I believe nowadays, even though that the simulation is not perfect, but a lot more, and the power of the scale data simulation, and I think that the simulated forward should be most quick.
Any take on this, Keynote?
Oh, hello. I think it's a problem of the simulator, and there's always be trade-offs, and I believe it is also it is always like important for the simulators, but we need to find like the we need to find a better simulator, and we also need to find the optimal trade-off point from the sim and real, and but I believe it is always necessary to for the simulators in the embodied AI.
Thanks very much. Time? All right. Thank you, everyone who has been on the panel. If everyone in the audience could please join me in thanking them for participating in the workshop. I'll move things aside.
Awesome.
Awesome. It is my absolute pleasure to introduce Embodied, who is the Senior Director of Computer Vision at the Allen Institute for Artificial Intelligence, and is an affiliate associate professor at the Computer Science and Engineering Department at the University of Washington. His research interests lie at the intersection of computer vision, natural language processing, and embodiment. And probably remember him from last year's CPPR, where he stood on stage and accepted the Best Paper award, and as well as a previous awards, including
presenting. Hello, okay. It's, if I unmute it is, oh, I switch on my camera. Sure. All good? Okay, all right, let me get started. Okay, so data has been a key driver of progress in AI, right? So we're seeing large volumes of data being critical to creating large language models, models in vision, models in the multimodal world. And we keep coming back to the same finding. As much as, as a community, we try to fight this finding. Every few years and every few months, we keep coming back to the same finding. Large volumes of highly diverse, but more importantly, high quality data result in very simple architectures trained end-to-end, giving robust generalizable systems. And this hasn't yet been our finding in robotics. And one of the reasons is that gathering large volumes of high quality and diverse data is extremely painful, right? Taking a robot in the real world, we do experiments in our lab and it just takes minutes and minutes to even perform one episode. So here's some really influential work that came out of Google recently. And this is, the first of many influential works in this line. This is RT1. And I found this line very interesting. They said, we collected one of the largest data sets ever, 130,000 robotics episodes, unprecedented. But it took them 17 months with 13 robots, right? So collecting this volume of data in the real world is just not going to pan out. The answer really lies in simulation. Simulation can give you high quality data, simulation can give you diverse data. But hang on a minute, we've been saying the same thing for a decade or even more, right? And if we look at our papers, simulation has not delivered. We have very poor numbers for tasks which realistically I would have expected that we would have been very close to solving by now. Basic tasks like explore this environment, go to all the rooms, tell me when you see my keys, right? You look at papers from all of us, we're seeing 20, 30, 40% successes. We're not building clean models anymore. We have all kinds of auxiliary losses to get this to work. We work in simulation, but we're collecting human data again. We're using modular architectures. This is very different from the findings in the rest of AI. And we've also now started making assumptions, right? We're saying, oh, actually, you do have access to the test scene at test time, but only for 5 minutes with a mobile phone. Or actually, I'm going to assume that I know where all the objects are placed. And so I'm kind of cheating in the task of navigation. So today I'm going to present two models. These are our latest models off the press, right? One is called Spock, and a latest model that's not even an archive called Polyform. These models are trained only in simulation, but at massive scales. There's no real world adaptation. These models have never been in the real world. They don't use any depth. They don't use any LiDAR. They don't use any map. They don't use any modular architecture. And they're only trained with RGB observations. They are not trained with any human data. And so all of the data is cheap and, in a sense, unlimited, as much as you can compute with. And as a result of all of these constraints, we're still able to produce agents that are proficient at reasonably long horizon tasks in navigation and manipulation, not just in sim, but also in real. And so here's a teaser. This policy has never been in the real world. It's been put on a stretch robot. It's seen in an environment that is not present in simulation, and it's able to go around. It's able to find this object, try to pick it up. It fails for a second, and then it succeeds eventually. And the key to getting this result or these results has been scale. Scale, scale, and scale. Scale up your environments, find new ways of creating interesting data, and scale up your models. Okay, so about 18 months ago, we decided to scale up simulation. Even though simulation came with the promise of scale, actually all of us were working in 10 rooms, 20 rooms, 30 rooms, 100 rooms. And so it was actually low scale, right? And so we said 18 months ago, we said the way to scale up simulation was using procedural generation. And so you have this little specification which says, I want a 1-bed, 1-bath apartment with this connectivity. And then we wrote a bunch of procedures that allow you to iteratively sample a floor plan, given a floor plan, sample some objects, place them, do lighting, etc. And this allowed us to create hundreds of thousands of houses. And we saw that as you increase the amount of houses in training and simulation, in simulation and in the real world on downstream tasks, your successes go up. So how can we extend this? How can we first expand upon this so that you can get even more flexibility to the user? And second, how can we extend this beyond apartments without having to write these procedures again? And towards this, at the CVPR, we're presenting Holodeck. Holodeck is our new framework to create rich 3D environments using natural language. So gone are the days of having this little tree structure, and instead you can simply specify a long sentence or even a paragraph of what you're looking for, and then Holodeck will create this simulator field, right? And so large language models are key to doing this. And we found that large language models can input this natural language, and importantly, they're very good at determining layouts that are consistent with the user query. And they can tell us what materials to put in, and then of course we can use off-the-shelf computer vision models to match text and language and start constructing the scene. They're also good at telling you what objects to put in, right? Unfortunately, this part requires an extra layer of constraint optimization. That's because large language models aren't really 3D aware. We were already surprised that they were 2D aware, but we did not expect them to be 3D aware. And so you have to put some constraints on, you want to make sure that objects are reachable. You want to make sure that robots can navigate between objects in the room. And adding a few constraints allows you to go from, from bland environments to this. So here's an example, 3 professors' offices. connected by a long hallway, and the professor in office 1 is a fan of Star Wars. And I will wait for it to pan around, and you can see that when you go to the professor's office number 1, you can see some Star Wars memorabilia, right? And you can keep doing many such user constraints. The system is fairly efficient. You can generate really, really diverse environments. You get tremendous amount of customizability. So you can say, well, I want to change this apartment. And this apartment is actually, someone has left the apartment, and the person who's now come, unfortunately, needs to use a wheelchair. And the model makes the doorways wider. Or you can say, I want to create an environment which is an aerospace exhibition hall. It sources the right objects, and so on and so forth. Of course, we are interested beyond navigation. We're also interested in manipulation, right, as a community. And so in order to get generalizable agents for manipulation, simply scaling up environments isn't enough. You have to scale up objects. But we've been using, at least in AI2 Thor, fairly limited number of objects over the years. And so last year, we released Observers. This is a universe of more than 10 million high-quality objects. And Observers, of course, has many more implications beyond embodied AI. It's become one of the most popular ways of building 3D models and has been adopted by many people in this space. But it also helps enrich our environments and really make them more realistic and reduce the semantic domain gap between sim and real. This is what environments look like before Observers. Nobody's house looks like this. Certainly mine doesn't, right? Because I live there. There's this stuff in this mess, and my kids throw around stuff. And so Observers allows you to create this. And this is more realistic. And this allows you to train robots to go and clean up your environment and navigate around obstacles. And so this really reduces the semantic domain gap that we've all been worried about. Okay, so when you're in simulation, right, of course, you get access to these environments, but what you really get access to is privileged information. You know exactly what objects are placed where, the depth maps, surface normals, the masses, volumes, all of this information. You do not have access to this information in the real world. You do not want to rely on this information at test time, but nothing stops you from using all of this information at training time. And so the way we source data is to write privileged planners. If I already know where the object is, I can use a shortest path. If I already know how high the object is, I can decide how to move my arm in order to manipulate this object. And so we write privileged planners in order to source lots of training data for many different tasks. And this is the way we think about tasks. You can have a behavior, you can have a way to specify the goal, and then you can come up with a natural language instruction and invoke the right plan. So of course, object nav is very trivial, find me a toolbox, but you can say, I'm not going to tell you what to find. I just want something where I can place my hammer. It could be a bag, it could be a toolbox, it could be something else, right? You could also say, find me the largest toolbox. And of course, you have privileged information on volume and weight and so on. And then of course, you can keep building this out to create more and more interesting training data. You can say, well, find me a toolbox, but if the toolbox is full, then find me a bag. So here's an example of a training episode. The instruction is pick up a pillow, and then this is training data. The robot goes around, navigates around objects, finds a pillow, and then grasps it and picks it up. And this is for the stretch robot. Okay, so now that we are able to source so much data, how do we train models? So this is a model called SPOC, which stands for Shortest Path Oracle Agent. It involves a transformer encoder. At every time step, we give the language goal description, and we give 2 cameras. The stretch is an interesting agent for people who haven't yet played with the stretch because it has a camera on the front, but its arm goes to the side, and so it also has a camera on the side. And so we input 2 RGB images at every time step. And the transformer encoder allows us to create what we call a goal conditioned visual representation. And then these representations are created for every frame. So every time the robot takes an action, you get a new frame. And all of these representations are provided to a transformer decoder, which then predicts an action. This, in my mind, is a very, very simple, clean architecture. This has worked in many different domains, particularly in language. And so we've adopted this.
Are you looking for the
Embodied
Zoom?
AI. Of course, we have to make small modifications.
Do you want the link?
Giving the previous action helps.
Oh, you
adding
download?
some
Oh, okay,
sort of
okay. I thought you were
temporal
trying to look
embedding
for.
in terms of the positional embedding helps a little bit, and so on.
What?
Okay, here's a result which I find extremely interesting. So This is a controlled experiment where we trained Spock using our privileged planners for a single task. This task is object goal navigation. Find me my keys, find me a plant, find me a bed, etc. At training time, this is trained with shortest paths, right? And so at training time, you already know where the object is in your planner, and you just take the shortest path, often like, just a few turns straight towards it. As you train with shortest paths at extreme scales, you start noticing that at test time, even though you don't know where the object is, the model is able to find the object. But interestingly, it's able to explore multiple rooms. And when it gets into a room and it doesn't find the object, it's able to backtrack and then move into another room. This has been very, very interesting to see. And of course, we don't train it on a single task. We train it on many different tasks, and we're able to create this large multitask model. So in Sim, you can start seeing that you can navigate to, all kinds of things like, these are synthetic tasks. Find the fruit in the kitchen, but then go near the fruit, which is at the highest Y coordinate. And as I promised, this also works in real. So you can go, you can start looking for apples, you can start fetching apples, you can find toilets. All of this is done with no real world adaptation. So on the left, you see it trying to find a green apple, and on the right, it navigates around his house and looks for a toilet. Okay, so what matters and what doesn't? So importantly, scale matters with a little asterisk. Scale matters, but it depends on how you source these houses. The crucial thing is diversity. If you start scaling your episodes, but keep your houses fixed or keep your houses at the levels that we used to work in, this doesn't work. You end up learning shortest path experts, and you end up not learning backtracking. But when you start scaling up diversity, then you start getting generalizable agents. Another thing that's important is context window. So lots of us who work on training manipulation policies tend to notice that you don't need large histories in order to decide how to pick up an object. That's because once you've got your arm in a certain position, your next action tends to be determined based on just a few previous actions and observations. But that's not the case with like slightly long horizon navigation. And we see going from window size of 10 to 50 to 100, and we've also gone up to 200, you keep getting improved success rates. And as has been seen in vision and language over and over again, better visual encoders continue to give you improvement in performance. And the best visual encoder that we found in this work was a SIGLIP model by Google. Interestingly, last mile detection continues to be a bottleneck. So if you only use RGB images, but this is just an experimental simulation, by the way, but if you provide the coordinates of the object only when it is visible, you get huge improvements across tasks. And this doesn't, and my hypothesis here is that agents are already learning to be proficient at exploration and navigation, but they often tend to walk past the target object. And when you start giving privileged information only when it is visible, they're able to make the right choices and go towards the target object. So that's one explanation. But I think the second explanation is that I think learning overall improves because the agent does not have to use its parameters for any level of object recognition. It can then focus on the tasks of navigation, obstacle avoidance, etc. And we see faster learning when we start providing last mile detection. So this isn't something that's that I advocate that we do right now. But it's a nice learning that is helping us make choices in our next models. Okay, so Spock has allowed us to show that simulation training at scale can produce proficient agents, but we still aren't at the level where we want to be. And one hypothesis that we've been having as we did Spock and moved from RL to IL was that IL continues to suffer from insufficient state space exploration, right? This is something that we've known as a community for many, many years. This has gone out, but it comes back. Okay. Okay. On the other hand, we know that reinforcement learning agents learn via interactive trial and error, and they are able to explore so much more of the search space. However, when we look at RL approaches that we work on as a community, particularly in navigation tasks, we tend to use very shallow GRU architectures. It's like RL work in navigation is stuck 5 years ago and never made it into like modern transformer architectures. And I think there's a reason for this. It isn't laziness. We've all been trying. It's extremely slow as you increase the size of your model. And as you go into larger and larger transformer architectures, we've noticed that you have a lot of training instabilities. And so we try to fix this problem. And our latest work is Polyformer. So Polyformer is a large transformer-based agent. It's trained with on-policy RL. There is no IL involved. It is initialized from scratch. And it achieves 85% object nav success across 2 embodiments, both in sim and in real. The architecture of Polyformer looks very, very similar to Spock. It's just drawn in a different way because it was a different paper submission. So at its input is a transformer state encoder. It takes into as its input an RGB observation. Polyformer was only trained for navigation. We just wanted to test this on navigation. Because it's only navigation, you don't need the side camera. And so this only accepts the front view camera. So you have an input RGB observation, you have a goal specification, and you create your goal condition visual representation. And then, as it was in the previous diagram, you provide these representations over time into a transformer decoder. The key thing here is that we started using KV caching. And when you implement KV caching correctly and you use it appropriately, you can get huge improvements in your training speed. And this was crucial because RL is very, very slow. Of course, there are a few small differences because we're doing RL, we need an actor head and critic head, but these are minor differences in architecture to Spock. There have been 2 critical pieces that are part of this training recipe that got this to work. One is hugely improving the number of parallel rollouts. And the second was having a curriculum on batch size. And so in the beginning of training, you want to make sure that your rollouts are very small. And of course, this influences your batch size. And every 10 million, you keep increasing the length of your rollout, which means you start with small batch sizes and you go up to large batch sizes. And this has been, these choices are critical in getting RL to work exceptionally well on object-oriented navigation. Okay, so this is what we have been able to obtain. This graph, interestingly, looks exactly like the DDPPO graph that we saw a few years ago for point goal navigation, when it was shown that as you go towards 1 billion frames of training, you start getting 99.9999 degree of success. And we thought as a community that, okay, now that point goal is solved, we have to change the goal specification, remove the the little GPS sensor, and we'll get the same thing with object goal navigation. But that hasn't happened until right now. So the horizontal line, which is the lower line, is a state-of-the-art past RL method. The second line, which takes it from 38 to 60, is Spock, which is what we were able to obtain with hugely increasing the amount of data and doing imitation learning. And when we use this same amount of data, but we go back to RL with a new training recipe, we completely break the ceiling. And it is my opinion that right now we're just compute limited. I think we can easily hit 90% with small modifications to the training recipe, as long as somebody gives me more GPUs. That is the real bottleneck right now. And this works. This training recipe has nothing to do with stretch. We have 2 robots at AI2, stretch and locobot, and it works well on both. Okay, finally, I want to end with a small extension to Polyformer. And this is called BoxNav. So one of the goals that we've had in this project is to really create what we call a foundation explorer, right? A foundation navigator. And so what we consider here is we'd like a model that learns to avoid obstacles, that learns to explore, that learns to navigate. But what we instead have created is an object goal navigator. We want to take a slight step up and create a universal navigator. And we want this universal navigator to then be, in a sense, promptable based on the task that you want. And so the change that we made here was to simply remove the goal specification. train this policy with no goal specification. So it has an RGB input, it has no goal. But sometimes we give it a bounding box. And when we give it a bounding box in the observation, if it is close to the bounding box, it gets a high reward. So what does this mean? We're training an agent. Okay, go around, keep looking around, search for this magical bounding box. The bounding box could be as big as the room. The bounding box could be as small as a little pixel. The minute you see a bounding box, you found some gold, go towards it, and you will get a high reward, right? And this turns out to be a universal explorer. Because now what you can do is you can source this bounding box based on the task you want using an auxiliary vision and language model. This allows you to do interesting things. So the task here is find me a book whose title is humans. And so here's a robot. It doesn't get a bounding box from vision and language model. It just says bounding box. Where's my bounding box? Where's my bounding box? And it keeps going around like a crazy person until it finds a bounding box. And that bounding box only occurs from an off-the-shelf model for a book titled humans. And I think this paradigm is very powerful because it can be generalized. You don't need to do bounding box. Any sort of image annotation that can be provided by an off-the-shelf model can now be used to train your universal navigator, universal manipulator, and so on in order to produce generalizable policies. Here's the second one. This is going to do multi-object nav. It doesn't know what multi-object nav is, but we showed a bounding box and then we make the bounding box disappear. And so like a crazy, like one of these dogs looking for the tennis ball, it says bounding box, where's the bounding box? And goes into another room, sees the bounding box, goes towards that agent. And here's a quick video showing you that, this is nothing to do with stretch. You can take this policy, train it with this same recipe, and now it can learn to avoid obstacles and, in the bounding box. Okay, I'm going to end with the same learning that I had on slide 1. In the rest of AI, we've come to this conclusion that get me lots of data, clean it up really well. Let's not go into hugely modular architectures. Let's have simpler architectures, Occam's razor. Let's train it end to end, and this is going to work. And I really believe that this is the way we should be thinking about robotics. And these projects are, I consider, steps in this direction. And with that, I will thank you.
You're perfectly on time, so we have time for a few questions. If there are any from the audience, we have some from Slack, but yeah.
In the scalability slide, you are showing scale as a number of training steps. How do the training steps relate to this within episodes?
So, right. So, this is, the question is on this, and correct me if I'm wrong, on this graph, we're showing training steps. How does this relate to the number of episodes? So typically our episodes tend to be, I would say, at the beginning of training, episodes tend to be longer. So you can have 100, 200 step episodes, and towards the end of training, the model starts getting more efficient, and so it starts getting your reward faster. I would say amortized over the whole thing, probably about divide by 50, and you get the number of episodes. One thing I forgot to mention is this is log scale. So it's not as quickly rising as you might think. Yeah, that's a great question. So the question is, in box nav, we're disentangling perception and control. And so are we now losing something there? So I don't think we're disentangling perception and control. We are still doing low-level perception because you need perception to do control. What we're disentangling is sort of high-level object recognition based on outside world knowledge. So for example, if I was in a bookstore and I asked the robot, can you go get me a book? I like to read, mystery novels. Can you get me a, novel that was on the New York Times bestseller? This requires outside world knowledge. but the robot still has to do perception. So the second part of your question is, are we losing something? And the answer is yes. And the reason is that when we take an agent trained on BoxNav, if you say, can you find me something to eat, right? The object goal navigator is like, okay, something to eat. This is going to be in the kitchen. I keep walking. The minute I see a kitchen, I'm going to take a right. And hopefully I will go towards something that's edible. In BoxNav, it doesn't have any idea what the task is. And so it is a uniform navigator. Maybe that's the right word. It'll go into the toilet first because it will maybe the bounding box is in the toilet. And so that is something that can be improved by saying, I'll give you a bounding box when I see a direction that I like. And so you can go towards that. And then I'll give you a bounding box when I see an object that I like, right? And so, and this doesn't have to be done with bounding boxes. You can do waypoints. And there are papers that are already exploring these directions. But this was something that we felt is a way towards universal exploration.
Yeah, how important is photorealism simulation when it comes to the real?
So when we train in simulation, the models work exceptionally well in the real world. We don't see degradation, but there are two asterisks. The first asterisk is that in order to get this to work, you have to use visual encoders that are trained in real. If we train every parameter in simulation, sim to real does not work. But when you use a SIGLIP model or a Dino model that's trained in the real world and frozen at training time, then essentially you're saying, these are universal visual encoders. They work as well in the real as they do in simulation. And we find that the embedding spaces are aligned within simulation and real, and that is sufficient to get transfer. They're aligned, but they're not exact. And so the second asterisk is that the key to getting sim to real domain gap to essentially disappear is extreme augmentation in simulation. And so you just mess up your image to the point of there's only some information there. All the, there's huge amount of jitter in terms of colors, in terms of brightness, in terms of contrast, and so on. And the models.
There's one more short question, so the question longer, maybe ask the speaker panel. So in the back.
Thanks for the talk. A question about the context and in navigation tasks. So you mentioned you need a very long context. I was wondering, is it that you need a very long context? You need to be very selective about what you remember. Could you actually get away with much shorter context if you were much more selective about which moments you remember?
Yeah, I think it depends on the task. So we're also interested in tasks like, can you count how many apples there are in the room? So you need larger context lengths unless you have external memory to write into. But if you're just saying, if you're doing BoxNav, you just have to remember, well, I've already been to the kitchen. I should not go into the kitchen again. We're also exploring interesting ideas on how do you have a dynamic context length.
Okay, let's thank the speaker one more time.
Four people, yes. That is including the moderator? One plus moderator, yes, it's including moderator. Yeah, you just need to speak very loudly. So we did just trying to make sure that we have some. With the Zoom, actually, so we're actually having basically the mics are getting the room. They're not getting to the Zoom. Only, I guess you're.
I'm putting it there, and it's on. So
I can hear it.
you can hear it. Okay, cool. Yes, in the interest of sound, please speak very loudly and into the mics.
Yeah, we'll just move it as close as possible for the podcast. Thanks. No one.
We're done. Yes. Okay.
Good morning, everyone. I'm Ade Famoti. I'm the moderator for this panel and also one of the organizers of the Fifth Embodied AI workshop here at CVPR in Seattle. We'd like to start with a warm welcome to everyone for being here at this panel session. So this panel session is themed Advancing Embodied AI towards seamless integration of perception and action. So in this panel session, we'll delve into the fascinating world of embodied AI. We'll look at some of the remarkable advances that multimodal foundation models have brought to the field of robotics. We'll look at some of the opportunities and perhaps challenges to the research and scientific community of embodied AI. And perhaps we'll also explore some of the opportunities that AI has brought to the field of robotics. So perhaps impacts like advanced higher level reasoning, perhaps lower level controls. So yeah, so before we start, a little bit about me. I work in Microsoft Research. I lead research incubations efforts globally in the Microsoft Research Accelerator team. My background is in computer science and autonomous systems, and my research interests caught across the intersections of AI, robotics, and simulation. So I'm also one of the leaders of the Embodied AI working group in Microsoft Research. So really pleased to be here. I've got a fascinating lineup of speakers. I've got 2 corporate executives from Microsoft and 1 executive from Sanctuary AI. I'll let them just briefly introduce themselves, say a little bit about their backgrounds, then we'll get started.
All right. Yeah, so all these executives, this will either be the most interesting panel or the least interesting panel of the day. I'm Ashley Lorenz. I'm with Microsoft Research. I've been in and around the fields of AI and robotics, autonomous systems for about 20 years. And when I first started working in this space, nothing in the robotics stack was learned. And we were sort of weird, in the engineering and in the systems engineering, because we were using kernel methods and support vector machines to start running classifiers on systems. And so it's been fascinating to see how much and what the really potential is for most or maybe even all of that robotics stack to be learned. When I think about embodied agents, I think about agents that act on our behalf. When I think about embodied agents in particular, I see the need for, of course, these fundamental capabilities of perception, planning, and action. And we've seen now perception evolve first, right? From kernel methods to do classification to CNNs, now to generative architectures, and even language grounded models, kind of at the perception. And then, now we also see an evolution at the control layer, right? From model predictive control to, I think it's been interesting to see methods like deep reinforcement learning sort of quietly reduced to practice, at that low level. And so now what I'm really interested in is, potential scalable foundations that connect perception capabilities with low-level control in this area of planning. And it's interesting to see architectures now that kind of have this perception and action learned, but still kind of explicitly constructed in the middle. One such experiment was recently conducted by Microsoft colleagues, manipulation example where GPT-4V was used for learning from observation. So demonstrate a manipulation task. GPT-4V annotates the steps along the task. And then those steps are then repeated on different zero-shot transfer to different robotic platforms that are essentially activating kind of motion primitives learned from reinforcement learning on the bottom. But in the middle, so learned perception, learned control, but in the middle, then you've got this explicitly constructed, almost like a PhD thesis worth of, kind of explicitly constructed action language in the middle. And so what I'm really fascinated and interested in is what kind of architectures can allow that perception action loop to be essentially closed with scalable learned foundations for perception, for planning and prediction, and for low-level control. So that's just to frame up my fascination and focus recently in the space.
Well, thanks, Ashley. I think you got us up to a fiery start. Thanks. Olivia?
Hi, everyone. Very nice to be here with a group of like-minded individuals, all furthering the discussion on embodied AI. As you've heard, my name is Olivia Norton. I'm one of the co-founders at Sanctuary AI, and Sanctuary is a company with a mission to create the first human-like intelligence in general-purpose robots. So if you're familiar with our Phoenix robot, you'll have a sense of what I'm talking about. We are, well, I've been in this space for 10 years now, over 2 companies, the first of which was a company called Kindred AI. It was founded on a very similar mission and vision, ultimately acquired by Ocado in 2020. And Sanctuary has been a redoubling of our effort to create these intelligent embodied machines. We have a particular focus and are somewhat unique in this space in that we are interested in the interface where the mind or the AI meets the world of work. So in the context of applications in labor augmentation, the hands, the dexterous end effectors that we provide our hardware platforms are this critical piece to allowing work to happen by these physical systems. The incredible impacts in the digital world of these transformer models over the last 7 years, with the particular acceleration in the last couple, has reinforced our belief that embodied AI is going to be the next major frontier for impacting the way that we live and work at a huge scale. So between declining birth rates, aging populations, a changing view on the world of work in people, we expect these systems, these intelligent embodied systems, to be a huge factor in global productivity measures in the next short while. So this is the application of all the work that this group is doing. We are very excited to be collaborating with Microsoft in innovating in AI models, in embodied research, areas like reasoning, like planning, like human interaction, and developing these AI models for humanoid robotic control. We do have a booth here starting tomorrow. So if you're interested in learning a little bit more about Sanctuary, I'd be very glad to have you come by and meet the team and learn more about what we do. And I'll pause saying thank you, Ade.
All right, thanks, Olivia.
Thanks, great. Really privileged to be here next to these esteemed colleagues. My name is Stephen Batish. I've been at Microsoft for 25 years. I'm a technical fellow and I manage a group called the Applied Sciences Group. We support the Windows and Devices division. We're a multidisciplinary team that works across the entire spectrum of the various fields. We develop most of the AI that ships in Windows, an example, and a lot of different hardware technologies. Our main goal and ultimate vision is to actually help create the next computer. And I think in this space, in the field of robotics, I think we can startly see that robots are potentially the next computing form factor that's going to impact our lives in many different areas, which I'm really excited about. In my former life, before Microsoft, I worked in bioengineering and neurobiology, combined with robotics. I built because I wasn't really a good programmer back then, so I built a hybrid robot that used a moth as a control system. So the moth was basically glued to the front of a car, a remote control RC car, and the moth would, using the evoked action potentials of the flight muscles of the moth, it would actually steer the car around and control it. So it was a really easy way of stealing a control system from nature, which was extremely sophisticated with an onboard power supply, an onboard vision processor, and a neural network that was quite sophisticated at the time. This was in the 20s. It was a pretty cool. But anyways, now we have artificial systems now that can replace such things. So pretty excited about seeing what we can do in that space.
All right, great. Thanks, Stevie, Olivia, Ashley. So we'll have an interactive conversation with the panelists here. We'll also pause at some point for questions so we can make it more interactive. Perhaps without further ado, I think a great place to start, I'll start with you, Ashley. So Ashley, you would agree with me, there's been tremendous innovation in the space of embodied AI. We've seen remarkable progress across several dimensions. What's driving this progress, and what more do we have to do?
Yeah, I kind of opened with some fiery, I guess, comments on this before, but the advent of the transformer architectures and just generative architectures in general that are able to be scaled with data. We saw a really interesting talk before this one on use of simulation environments to create data sets. I think those are really interesting. Of course, we've got the sim to real problem to worry about as well, and thinking about contact physics, especially for things like soft body manipulation, folding a tablecloth and things like that. So I will agree that in general we need to figure out how to get these scale effects, especially for at that intermediate planning layer in these embodied AI architectures.
Got it. Okay, sounds great. So Olivia? So I think some of the emerging morphologies we're seeing for embodiments, embodied agents, embodied AI, they're increasingly humanoid form. And I know Sanctuary has this highly dexterous humanoid robot, Phoenix. So I think it'll be interesting for the audience if you could describe how you're thinking about bridging the gap between perception and action.
Yes. Let me start with the humanoid form factor. I suspect that folks are generally following this thread, but we, as an organization, are really focused on this world of work, on augmenting labor areas where we don't have the folks to support those roles, where we are looking at safety-related applications and you don't want people in those jobs, or they're just fundamentally things that people don't want to be doing, that they could be doing something more interesting. And all of these applications are in this perception action context that is human-centric. So the objects and the environments are defined by people for work by people. And the humanoid form is the perfect form for that design constraint. And so that is one of the reasons to bind ourselves to this humanoid form factor. The multimodal data acquisition capability of a hardware platform like Phoenix is, of course, just very interesting from an academic perspective as well. Vision, touch, audition, and proprioception, providing that robot first-person perspective that allows us to learn new skills and automate activities that the systems can perform. We, as with everybody in the audience, the last talk, suffer from the same bottlenecks of data acquisition that everybody else does. We do some of it the hard way in the sense of a second per second data acquisition approach, teleoperation on physical hardware, but of course are always looking for opportunities to augment the data that we have in terms of deriving the most value from perhaps limited amounts, and to search for alternative, perhaps lower quality, but still valuable data sources. Simulation is a great example. Certain tasks and applications are suited to leveraging simulated data, and some are less so, to Ashley's point earlier around soft body and contact physics. The data variety piece is something that I do just want to touch on, because we also believe that this is an incredibly important inflection point in regards to developing these large foundation models, large behavior models for a system like Phoenix. And we expect that variety to be coming by virtue of deploying in real worlds, in commercial applications, in operations, out in industry. And we began this process last year. We began in a front of house and back of house retail context with a large retailer in Canada, and are seeing that translate now to manufacturing, assembly, and automotive applications here this year. So all of the same data related challenges, but looking to that final application space to help direct.
All right.
Can I chime in?
Sure.
It's
Go
really
for
it's a pleasure and a privilege to be working with partners like Sanctuary and others. It is interesting to think about whether the humanoid form factor is kind of an end state or a waypoint in form factors. It does seem to be relevant right now that we have all this large scale language data, and it contains all this inherent knowledge about operating in human-like environments with human-like affordances and capabilities. And so as a waypoint, it's really interesting time to be looking at the humanoid form factor, given the kind of implicit alignment with a lot of the large-scale language data that we have right now.
Very well said. Yeah.
No, I really like that. We're going to come back to Phoenix. There are several folks in the room, I'm sure, who perhaps will love to learn more about this highly dexterous embodied agent. But I do want to, so Stevie, perhaps this one's for you. So I think a lot of folks in this room will love to make this real. So we're in a research environment, but let's talk about how to make this real. So how would you describe the sort of evolutionary phase we're at for now, and perhaps the sort of computational or hardware requirements that we need as a research community to unlock advances in this space?
Yeah, that's a great question. Yeah. In my intro, I talked about building the next computer form factor. And if you actually look at all the various forms of computers we've had in our history, you notice that they all follow a very particular pattern. Every one of them, even all the way down to even the slide ruler, you have a step function increase in compute, that allowed us to essentially write software that abstracts the functionality of that compute. And changes how people interact with that computer for the most part. And that allows us to essentially build a different type of form that does different things, goes in different environments. And you see that like over and over again, as you go from, hard-coded computers to vacuum tubes, to when the transistor came along, to GPUs, every one of them basically introduced, a step function increase compute. Today is no different. Today you see, especially with tensor accelerators, a massive increase in compute, not just in top speed and ability to inference and train large models, but also at the same time to do compute efficiently. And I think the combination of high compute with computational efficiency is going to change the field of robotics drastically. So if you can imagine, especially in a humanoid robot, the amount of data that floats around inside a machine, the tactile sensors, the vision, all the encoders, the muscle, and how fast the computation has to happen so you get a nice closed form compute and control system. And so having local compute on the device in conjunction with cloud, of course, allows you to design a computer, but not just high computational workloads. Again, efficient, because we want these things to be mobile. You can't walk around with 200-watt processor moving around. It's not very efficient. So as an example, in fact, today we just GA'd kind of a new generation of silicon in the Windows ecosystem. And it is basically defined as a neural processing unit that can do about 45 trillion operations per second, but does it under 4 watts, which is tremendous to think about. So before, you imagine, we used to, be happy with, 2 teraflops and about 20, 30 watts of power. Now, you have a massive step function increase in compute with computational efficiency. And I see no end to that sort of thing. In fact, a lot of our computational scaling laws have kind of shifted towards domain-specific silicon innovation, such as these tensor accelerators, that are really just designed to handle, neural network workloads. And they do it well. They may manage data well through the system. And as a result, you can do some pretty profound things. So I think that's going to have a profound impact in the field of robotics, especially as more and more of the robot control system shifts towards neural network architectures.
Oh, that's fascinating. So I'm going to pause, and perhaps if there's any questions or comments from folks in the audience, we'll take it, and we'll go back to the panelists for some questions. Yeah, go ahead. Yes, go for it.
Yeah, so with that, offline reinforcement learning and imitation learning, does that make simulation kind of less important here? Because it seems like the winners in the space are benefiting from scaling these real world, offline training data, like Tesla, for example. And then does that imply that the challenges in this workshop could take more of getting these offline recordings as data sets as opposed to the simulation?
Do you want to go? Oh, yeah.
Yeah. So do you want to, for the Zoom, can you repeat it?
I think you repeat it.
Okay.
The microphone, yeah.
Yeah, so for folks on the Zoom, the question was more about simulation versus data sets. Right?
Versus the offline data.
Offline data sets in an RL context, right?
Yeah.
Who wants to take that?
You want to start?
Talked about that yesterday.
Yeah. It's a recurring discussion in this workshop.
I was just saying, it's absolutely both. And the companies that we've seen that are doing well in the space use a combination of simulation to bootstrap and learn, but real world data brings you diversity and scale, especially when it's actually put to good use. So we've talked to a number of different companies that have started that flywheel there. But I think in conjunction to the real world data, you have kind of simulation as well to help manage things. And certainly, I think you've seen that, even just simulation alone isn't the only solution.
Correct.
And you've found the limitation of the result of that. Yeah.
Correct, yeah. And one of the other factors that features strongly for us, as you're making learning architecture decisions, simulation is a huge factor. Validating new morphologies is another big piece for us as well. So it's not a single a single benefit that is being derived from sim. It's an aggregate. Yeah.
Ashley?
I think they covered it well.
Okay. Anthony?
We had a question from the Slack. What does human-like intelligence mean empirically? If you could repeat that for the Zoom.
For the folks in Zoom, what does human-like intelligence look like?
Mean empirically.
Yeah.
Let me describe how I think about this, but there are many opinions. So I'll start by caveating. In the context of the work augmentation, the labor augmentation focus that we have, it's really in this space of, are these systems behaving as you would expect a person to be able to do in the context of the SOP, the operation, in the context of perhaps the edge case, some sort of failure mode that comes up, applying common sense to the decision-making in the constraints of the operation. Broadening that to something more definitional. Anybody want to take a cut at?
Well, yeah, it's interesting because I think human-like intelligence, or the aspiration to achieve human-like intelligence, has been an inspiration for the field for many years. But as we sit today, I often wonder if it's a bit of a red herring. Relative to, so I think a few things are important. So the ability of a system to accomplish human goals in a variety of different environments, under a variety of different conditions, variety of different tasks, I think is important. The ability of systems to do that in effective collaboration and with effective oversight by humans is also important. So those are the two things I think of as most important. Now, in some cases, I think it's good for systems to be able to do things in a human-like way so they don't freak us out. But this is kind of I think a nice to have in some situations versus the penultimate aspiration.
Yeah. So perhaps maybe another round of questions so we could spark and elicit some more questions or feedback. I'll go to Stevie. So Stevie, 4 to 5 tops, that's pretty non-trivial. Can you speak a little bit more about these NPUs, neural processing units, which work based on tensors and array of arrays? It will be fascinating for the audience to learn more about this.
Well, yeah, I mean, as I was mentioning, we're, I think this year we kind of crossed that threshold where we're able to run, these transformer models at very low latency scale. So for example, we run, if you're familiar with the small language model Phi and Phi3 that Microsoft just released, which is incredible performance in terms of its performance relative to some of the much even larger language models that are out there. We are able to execute that model on these devices, again, under 4 watts continuously in real time with a first token latency of less than a second. And that is pretty impressive, especially when we start shifting toward multimodal models that want to incorporate, even a more diverse functionality and performance as a result of that. So I'm pretty excited about it. They're more difficult to use than GPUs are and CPUs are. But the tools are out there. They've been kind of brewing in the ecosystem for at least 15 years. Microsoft has a inferencing runtime called ORT, Onyx Runtime, that interfaces with these various neural processing units quite well and tries to make it simpler and easier to use. So I think more and more people will use it. I can imagine, just like we used to have the Intel NUCs that people were kind of enamored by, these little small computational devices, that people are going to have these kind of, high-powered AI boxes that they're going to be able to use to prototype up all sorts of things on the robots.
All right, thanks, Stevie. So, Olivia, it'll be interesting to learn more about Phoenix for the audience. We've come a long way. There's several new paradigms introduced since the early days of humanoids. For folks who are familiar with the Televox or Electroman, we've come a long way. But can you speak a little bit more about Phoenix? Just, give us some polish, a little bit more color about Phoenix.
Yeah, certainly. So this system stands about the same height as I do. So 6 or 5'7", 6, I wish. And it's a very fast actuation. It provides a high degree of freedom hands, so 17 degree of freedom hands, verging on the degrees of freedom that you'd start to see in a human hand in terms of the geometry. One of the things to call out is, and this is a little bit different from other form factors, is that all of the vision related sensory information is coming from that first person perspective in the head. So one of the questions that we often get is, wrist cameras or finger cameras or other ways of providing additional information to, close proximity grasping type of tasks for manipulation. And this brings up the whole discussion around touch sensing and the way that touch sensing provides us as people with an incredible awareness of our environment. If you anesthetize your fingertips and attempt to do something like light a match, you can do this visually. It takes some practice because you have to cage that object using your eyes. And you're operating at about 20% of the performance of your normal unanesthetized sort of physiology. And this is the same type of thing that we see in systems that are equipped solely with vision, in the sense that as soon as they're working with small objects, you're running into occlusion issues. Everybody has probably dealt with this, and you need to either move to a different modality that is closer to the object, or you need to be providing that touch sensor information of the type that we get. So compliant touch sensors providing force at a granularity that is useful for doing in-hand dexterous manipulation and object reorientation. So that's one of the key aspects of Phoenix that is worth highlighting and is sort of unique in the field.
Got it. No, that's great. And Phoenix is not in the building.
Phoenix is not in the building.
All right, I think we're running on time. I wanted to throw one more at Ashley. So Ashley, you've been in this field of autonomous systems for a while, so I'm going to pick on you. We've seen tremendous advances going from classical theoretical robotics now into embodied AI. Now we're seeing language condition models that are now this evolution of action as a language. Can you speak about what the future holds? We want to hear a prediction from you.
A prediction, wow, these are really hard these days. Yeah, I think just on this note of action languages, it's really interesting to think about parallels with natural language. And we've got natural language systems that are clearly multilingual. And maybe the promise, of course, there's things like low resource languages that we have to figure out and get right. But we can see the promise for something like a universal language, or at least a universal translator among languages. And so one interesting question as we enter the embodied AI space is, do we see the potential for that in embodied AI, something that is fluent and universally fluent in action languages, whether that's in my household or industrial manufacturing, or even some of the consumer experiences that Stevie works on. And so I think this is a really fundamental question. We're going to have things that are kind of domain specific, or do we see the potential for a kind of universal action language? That's not a prediction, but it's a question that I find fascinating. And I think it's relevant to the kind of architectures we'll consider in the space.
Absolutely. No, thanks.
I just wanted to add to, I mean, I think just to add to Ashley's point, I mean, we're moving in the world where we're moving into a much more agentic world. Agents are going to be the mode and the programming model of the future for a lot of people. And those agents are going to be manifested in all the different form factors of computers that we have. So you'll be able to have to interact in a natural human-like manner with these agents, and they will be able to accomplish tasks for you in an automated manner, whether it's in the virtual world or in the physical one. And I think that's kind of the exciting world that we're kind of moving towards, I think, fairly quickly.
Okay, so we're on time, perhaps. Maybe we're going to take one more question. I'd like to do a roundup and summary. We're on time. Okay. I do want to say a big thank you to my panelists, Ashley, Olivia, Stevie. Fascinating discussion. Thank you to the audience. And I do want to say special thank you to my fellow organizers and lead organizers, Claudia, Lucas, and Anthony. So let's continue the dialogue as a research and scientific community. So the innovations in embodied AI is evolving and emerging to be a team sport. So we're all going to solve some of these tractable problems together. So thank you.
Thanks, great job.
Okay, next up, we're going to have, thank you, Ade. Next up, we're going to have, again. We're still there.
为什么你是蓝色，你是黄色带着我是蓝色？因为我是天天的那个。哦，我是弯背的，对。
Ryan, I think, can you hear us?
Yep,
I think you can present.
因为我现在公司要改，但我不知道他会打到这个。他问我公司的，然后就想问他。
Blake, can you mute? Thank you. Okay.
Can we hear, Brian, can you,
Yep.
Brian, can you hear it? Okay.
Yep, can you hear me?
All right, we can hear you. I'm gonna put you on the speaker.
Cool, great. And I assume you can see my slides and everything.
Yes, looks great. Yes, looks great. So this is Brian Nixter, who is going to be talking to us about foundation models for robotics and robotics for foundation models. Take it away.
Yeah, thanks, Anthony. Yeah, so I'm basically going to go through a couple recent lines of work that are about basically, how deeply can we use foundation models for robotics and how can we pose robotics in a way that can benefit the most from foundation models? And then also what kind of lessons from robotics can we apply to improve foundation models and downstream performance? So a lot of this work was done at Google DeepMind, but right now I'm at Physical Intelligence. I'll talk a little bit about that at the very end. But yeah, so foundation models obviously have made just kind of huge leaps over the last 5 to 10 years, taking in the internet's worth of data and translating it to downstream, really high quality performance on reasoning tasks and a broad range of very complicated tasks. Now, this is sort of this like, I think some people have said like almost an alien technology dropped on us, especially as roboticists, that there's suddenly this vast knowledge base that we can use to enable us to do all sorts of tasks and get a lot of generality that we didn't think necessarily was possible for robots, where we don't have them in a wide variety of circumstances right now in places in the world. Now, they've obviously touched so many different things, from starting from just the language models where, now they can act as a very high quality doctor, to doing VQA tasks, which bring us even closer to grounding for robotic tasks. But we can also take in audio, start being more embodied, like within a phone, with a lot of the recent announcements around bringing AI to more physical worlds. We can generate images, generate videos, and even generate audio. So I think a lot of these things are extremely natural for the way that a robot would interact with the world. It needs to be able to see and hear and move. But there's also a couple challenges that exist there. Like a lot of these don't have real interaction with the world. They're always this very pulled apart use case versus having had experience in the world where you change something and your decision really affects it. So this is some problems that I think like robotics can really bring. We do a lot of work on optimization and planning, and I think these are areas where we can sort of help downstream foundation models. But there's I guess at the core of it, we have this like wave of this technology going, and I mean I think I've used this like image a bunch of times, but I really believe that at the crux, we want to just use as much of it we can to propel robotics forward. But I also think robotics has a chance to sort of like prop up foundation models and fill in these gaps, this like embodied experience, the knowledge of the physical world, the knowledge of decision making, and the like this actual experience in doing it. So I'll talk a little bit about some of these like problems that foundation models have, and ways in which lessons from robotics or data from robotics has been able to improve them. So one of the first questions that I really want to think about is, how can we make robotic control as close to foundation models as possible? So, if we take some early work like SEICAN or others where we do this sort of high level reasoning, it's pretty clear how to pose robotics in the space of language or in the space of vision language models, where you have this high level task and you output something that the robot can do. So this makes a lot of sense. There's a clear natural language for it. But when you get to something like, say, manipulation or navigation, it becomes a lot less clear how we can get the most out of robotic control. So a couple ways we might be able to do this is sort of like a RT2 style, where you just act like actions are language and train the model to do this. Now, I think like one framework that I like to think about here is if you're the human, you as a human are put in this circumstance, what control modality would you be able to use? And I think this is a good proxy for what a foundation model is going to be able to use, where we're going to get the most out of the foundation models. So here, if I then ask you, you have these two blocks and I want you to pick up the red block. In the RT2 framework, I would say now just put out some numbers for me, like, the move in the X, Y, Z, this amount. This is it's not super clear exactly how you would be able to do that. You don't know this mapping to actions. It would take you a lot of experience to be able to do this at a really high rate. Now, if I said, you can respond in natural language, you might be able to say move to the left or right, but actually like the blue block is a little right and a little forward. The red block is a little left. So I think we really need to think about what sort of framework we can build that allows us ourselves to be able to control a robot. And if we can do that, then probably a foundation model can do a lot to learn from it. So the idea that that I'll talk about here is we can actually use visual prompting. So if I now draw on this image and I ask you, which of these actions, which of these arrows would you follow to do it? It's extremely clear to you that for the red block, you do 1, and for the blue block, you do number 2. And indeed, we've seen, some previous work, one about what CLIP understands about red circles. You can actually visually annotate images, and VLMs understand them pretty natively, without any sort of, this is CLIP, so it's not even a more complicated VLM. And it works quite well to identify these fine features that are otherwise a little bit difficult to explicitly understand. Now, these are a little more like object recognition tasks, but on the case on the left, the path actually matters too. But I think this is something that we can see that we natively can understand, and that a foundation model can probably understand that this is the trajectory they want to follow. It's something more nuanced than necessarily just object recognition. So the technique that I'm going to talk about today is called pivot prompting with visual iterative optimization. And there's a couple of things going on here. One is this idea of visual prompting, and the other one is something that's more akin to like CEM, where we do an iterative optimization. And the way that this works is given a robot, so maybe the robot is an arm with a wrist camera or something doing navigation, and I say go to a specific task. I basically want to sample a bunch of actions that I could potentially do. So this is sampling in this action space that I presumably have well represented. I then annotate the image with a visual representation of that action. So you can basically project that action into the camera frame, that this is the movement of the end effector, or this is the movement of the vehicle that's driving around to be able to do the task. I can then ask a VLM, which of these ones should I do to be able to say, pick up the red block? Which of these should I follow to move to the green block, or to avoid something, or to, navigate between them? And a VLM can actually, at a decent rate, predict, these are the best arrows for this. So it picks maybe arrows 2 and 7 for the red block and 3 and 5 for the green block. And what we do is, well, first of all, sometimes it makes mistakes, and other times this is still, not the explicit action to take. So this is where this iterative optimization, this almost like CEM-like approach comes in. We actually fit a distribution to the response of the VLM. We resample it and then do this task again. So we iteratively basically hone in on the optimal action for the robot to take, and then we execute it. Now, what this looks like in the real world, you can kind of see the distribution converge on this microfiber cloth, where at first it answers a couple ones that are over it. We fit that distribution to it, and then we eventually select something that moves us in the correct direction. And it's important to remember that, like, at the underlying level, the action that's being represented really is in the action space. We're just projecting into the camera space for the VLM to understand it. It's also important to realize that this is a actual trajectory. It's an action movement. It's not just necessarily a final object recognition. You really need to like move around things at times. So in the navigation case, and I'll show some examples where that matters. So this is what's nice about it. This is very general. All you really need is this like sampleable action space and then some way to put it in the camera frame. So we, as part of this work, we put it on 5 different tasks, 4 different types of robots. One doing navigation, where you have some ego frame view and and you can turn or go forward. One where we have a third-person camera view for a robot arm, so the action space initializes at the end effector. We can also do it in a wrist camera frame. We can do it in something more like a transformer network style, where there's just like a pick and place location. Or we can even do more referring expressions from, say, the more VLM community. Now, when we actually apply it on the robot, you can see that it works pretty well. And this is, again, all zero shot. Nothing's trained to do this. We can say find tissue paper. We can also say avoid the obstacle or something like that. And now this is where this like object recognition varies from something more from pivot or visual prompting. You can actually represent something more than just a final location. You represent the entire path and then optimize over it. So this is like a very nice, I think, general approach to being able to get actions out of the model. We can also do manipulation. So here, where to put the orange, it's very clear that you should probably put it with the other oranges. And we're able to extract the semantic knowledge out of the VLM and do it zero shot without having to train anything or collect any data. We can put the grapes there, we can do the banana, and it can do this relatively robustly, in part due to this iterative optimization, which I'll talk about next. So again, the way it works is we sample some actions, ask the VLM, fit a distribution, and then do this repeatedly. And so on each of these plots, we show both how many steps we do of this iterative optimization, and also we can do this over multiple parallel calls at each iteration. So sample from this action distribution a bunch of times. And each of these are ways, methods from sort of robust optimization in order to fix mistakes that the VLM might make. And so in each of these cases, we see that the performance actually improves with number of iterations. And for the most part, it improves with the number of parallel calls. So at times, down is better. I think the top two rows, so we have referring expressions where we want to be closer, and indeed we get better, and we're also more accurate, which is the second plot. The number of parallel calls seems to help kind of across the board in each of these. So really clearly, we're like robustifying this in a very general way. Now, another thing that I'm sort of particularly excited about within this framework is that it scales really well with model size. So as the VLMs become more performant, we also get zero shot, a much better answer. So not only can you kind of like improve in this way, but we can also go and fine tune the models and have them do even better on this task. So I think this is something that we can really look at in the future is basically, what do you get zero shot in this task? And then how well does it do fine tune? Because this zero shot performance is going to be in some way indicative of both high level performance fine tuned and also to a degree, the ability for the model to sort of generalize to new tasks when you go and deploy it in the world. There are, however, some limitations that if we look at it right now. So these are places where I'd say foundation models are somewhat limited in their current form. They haven't had this sort of interaction with the world. They haven't had this embodied robotic experience, some of the common sense that we have from really interacting with the world. So if we look at the progress of the episode on the left here, this is basically, you can find some really key points. So at first, on the approach to the object, the performance is quite high. But it degrades as you get closer and closer to the object, in part because it's hard to see what's happening, and it's hard to really distinguish where to make the grasp point. Once it's picked up, it improves again, or once it's grasped, it improves a little bit again. But then this like lift it off the ground, so here is like pick up an object, the performance overall decreases. And you can see how this is kind of hard. First the image is fairly occluded. And by the gripper or by like visual annotations. So I think there's something in this. We need to really like fine tune these models or add this type of knowledge, this potentially video data, some way to get this like kind of embodied interaction experience into the models to improve these particularly hard things. And you can see this really on the bottom here, where maybe with the optimal many iterations and many parallel calls, we are able to approach the object at 100% across a few trials, but the grasp still isn't at 100%, and this is like a relatively easy task. So I think we see that we move in the right direction with this, but there's still a lot of missing 3D knowledge, interaction knowledge within the underlying foundation models. I'll quickly talk about a couple other works that sort of have leveraged a similar thing. So this work, Convoy, has a similar setup, but in this case, the visual prompted results then go down to a motion planner, which can resolve a lot of the errors that we would see. So this motion planner obviously has more experience or has more understanding of the dynamics of the world. And I think we need to think about algorithms in this way where we can sort of pair them with more optimization and knowledge that we gain from robotics and interaction through the world. Another thing that we see that fails pretty badly, both natively in foundation models and similarly in Pivot, is this like spatial reasoning understanding. So it might know, okay, you can approach this way and get close, but the actual, you're very close, you're a couple of centimeters away. This depth and general like semantic reasoning is something that's been fairly well known to not do very well within VLMs. Now, there's a lot of issues with some of the pre-training that can cause this, but in general, this is something in robotics we can do quite well. We have sensors that track, say, depth. We have maps and occupancy grids. So in this work, what we did was we built a semantic filtering pipeline where we generated data with spatial reasoning with both relationships, depth estimations. We also used depth data from collected on the robot. And then we trained a VLM to be able to do more semantic tasks. And you do quickly see an improvement overall in the ability of that VLM to do spatial reasoning tasks, depth estimation, and it generalizes to things that it hasn't seen before. One, I think, like very important thing to highlight from this work is where we really saw the most gains were on robotic data, where we had good depth data and like well understood scenes. So I think the more that robotics can kind of collect this wide range of data and then trickle it down into foundation models can work quite well. Now, another thing that I think we've seen in foundation models is that, and particularly in language models, is that reasoning starts to work fairly well at some scale. So we see in, say, chain of thought that if you break the problem down into several reasoning steps, the performance overall improves. We also have seen within the, I guess, both through something like CodePilot, but also works like Codis policies within robotics, that language models can code quite well and use this as a way to interact with the physical world. Clearly, like these reasoning capabilities through code work fairly well. So what's nice with code is it has this like very general, I guess, structure that allows you to build fairly complicated programs and then run things explicitly and get, a deterministic, clear computational number. But some tasks are really hard to do in this way. So, this tennis ball tasks might be a little bit easy, but if we made it more semantic and said, for maybe the second one, if there were apples, oranges, and other objects, that how much food does the cafeteria have? I actually can't see the thing over the Zoom window, but essentially, there's a lot of things that are very difficult to express through code. But somehow, if I'm given a very complicated task, I often might solve it through writing code. So there's something in this sort of like interweaved knowledge, common sense, and code. And so the idea in this work, and we call it chain of code, is that we use language models to both write code to solve general purpose reasoning tasks, but in times where it's maybe difficult to express something in code, we can simulate the output of that code. So I'll talk through what that means in this next slide. So this work, chain of code, has the language model, as I said, both write the code, but also try to execute the code if it's not executable. And so what this looks like, and if we look at this list below, for example, how many countries have I been to, and a list of a bunch of places, if you just throw it into GPT as a question, it makes a fair amount of mistakes. It's somewhat stochastic whether it gets it right, but for the most part, it doesn't get it right. this is like a really long list of places that you might have traveled to. And it's difficult because you need to track every place and which country it is. There's clearly this like back and forth between like counting and some more like arithmetic, and also this common sense knowledge. Chain of thought improves a fair amount. You're able to kind of write down, all these like locations and the countries and what cities are there, and then make the count. And overall, it gets closer in its estimate, but I still see it make a lot of mistakes. So this is where something like tool use makes a big difference, but it's a little bit difficult to do unless you really are working back and forth between the code and these reasoning steps. So this is where chain of code comes in, where the idea is to first generate a set of code to run to answer this question. So in this case, you make a list of all the places, and then you loop through those places, but you get to something very semantic. What country is this place in? Maybe you could have some map API that you look up, but you can imagine a much more general semantic question where this doesn't hold very well. So instead, while we're like running this program, instead of erroring out that this this function doesn't exist or is too hard to write semantically, we can instead simulate it with a language model. And the language model can do quite well at this. This is something that was known from, for example, Scratchpad prompting previously, that you can simulate the output of code. And then we can amend the program state and continue on. So the way it works, again, is we generate a overall reasoning trace in code, and then we go through and execute anything possible with the Python interpreter. And if not, then we have the language model generate a trace that it believes is reasonable. Now, if this turns out to work really well, it has the state-of-the-art on Big Bench Hard, which was a subset of very challenging reasoning problems from the Big Bench benchmark. We get a pretty good gain over chain of thought, and particularly we actually outperform human raters in like I guess 18 out of 23 tasks, so a very large proportion of tasks. Compared to something like just writing Python code, we actually see that it performs, so this is this one here, it performs 20% worse. And even, just writing Python code actually does worse than, or I guess this is compared to human baseline. But compared to, so chain of thought outperforms human baseline across in general, but just writing code doesn't work for a lot of these tasks because they're fairly semantic and common sense. And I'll break it down by those in the next slide. But we actually see that our approach, that this interweaving of common sense and code together, performs much, much better than both humans and chain of thought. Now, if we break it down by the type of task, we see that in, for example, the tasks that are like fundamentally natural language processing, we perform about as well as something like chain of thought. But importantly, we don't lose anything, even though we're expressing it in code, which we might think of as a less natural way to do this versus just writing down your reasoning. But the syntactic structure of code is so general and useful. But then on more algorithmic tasks, we obviously perform much, much better. We actually perform better than even the best humans do on average. So this ability to leverage code is extremely powerful when you get to those more types of tasks. It performs really well compared to even chat models that use tools. This is, I think, in a large part because this like explicit code structure provides a lot of powerful reasoning abilities, and it performs well for both small models and large models. We can see that as the models scale, and that's like the x-axis in each of these, chain of thought famously only emerges at scale. So you see that the blue lines, for example, do about the same as direct prompting without chain of thought until you get to the really large scale, really performant models. But chain of code actually performs well, whether in the small models or the large models. And a lot of this is driven by the algorithmic tasks, where this like coding emerges a little bit earlier and with less performant models. Though to a degree, I guess it's the coding and the semantic reasoning, because you can see this red plot does a little better, but our chain of code performs much, much better sort of at all scales here. Now you can also apply it very naturally to a robotics tasks because robotics often has a lot of kind of semantic and algorithmic reasoning together interweaved. You also have these APIs that you might want to call perception and control ones, and you want to interact with the user. So here's a task where we're sorting compost and recycling across two. So here you really need to both call these APIs, but also reason about, given the detection, what objects are there that an orange peel is compostable, for instance. So what I'm working on now is thinking about if we scale these ideas to really bring general purpose AI into the physical world. And so I'll just a very brief slide, but recently with several colleagues founded a company, Physical Intelligence, and we've been focusing a lot on how can we scale robotics data, how can we scale robotics foundation models, and the research breakthroughs we've seen to be able to do new tasks. We see shirt folding working pretty well, dexterous tasks, busing, which requires some semantic knowledge of what to throw away and what to bus. We can see fine-grained control. So we really believe that at some level, this scale will both allow robotics to thrive with foundation models, but also contribute back to foundation models as they're a big source of high-quality data and interaction with the world. So in summary, I think we should really think about both the strengths of foundation models for robotics, but also robotics and things like optimization and robustness and reasoning and planning that can contribute back up to foundation models. And I think that's it, but I'd like to thank all my collaborators and colleagues for. And I guess I have a couple minutes for questions.
Yeah, so we have, we'll take some questions from the audience, but I wanted to start with one from the Slack. What can you do at Physical Intelligence that you couldn't do at Google DeepMind?
I mean, I think there's a degree of really like scaled focus in this idea that's very important. I think DeepMind has a lot of ability to do exploration and obviously very good access to foundation models. But one thing that we think is extremely important is the ability to put robots out into the world to really experience and interact with the world and build up this general purpose data and experience, I guess, repertoire. And I think that's something that can be relatively challenging otherwise.
Any questions from the audience?
Foundation model, what do you think would be the most important bottleneck here? Is it the data or the model itself, or is it cover which one you think is
So the question for the Zoom folks is, what's the bottleneck with foundation models? This is the data, the model, the code.
I mean, I think it's probably a mix of each of these. I mean, I think on the I guess let's say code level, there's inference speed and things like this. I think these are very approachable problems, but still big ones for deploying in the world. I think there's a lot of missing data of this interactions. I mean, this is sort of the nature of training on this large scale internet database versus actual interactions with the world. And I think that contributes both to the overall data, that there isn't this experience, but also the models that aren't necessarily built to understand natively this type of embodied reasoning, so to speak.
All right. Well, I think we're at time. So thank you very much. And we really appreciate your presentation.
Thank you.
There's something going on there.
It's a strange loop. And I think I have to be unmuted here. Is that right? Yeah, that's right. Okay,
Well,
good.
introduce you. One moment.
Okay.
I jumped into the opportunity to introduce him because I knew I would have such an easy job. You know, I didn't even have to do it right now. But well, let's please welcome Richard Newcomb. He's a hello. Well, he's a VP of Research Science at Meta Reality Labs, and he's leading the Surreal team in Reality Labs research. I really want to have all the time for him. Yeah, you can hear me? No, good. So please take it away. It's a pleasure to have you.
All right. You might be able to hear me or not. Certainly you're getting loud when the Wi-Fi has come back. Apparently this is a Wi-Fi issue, not a microphone issue. Okay. So very pleased to be here. Thank you for inviting us along to this very broad, space of really the future of AI. I'm going to talk about always-on contextual AI, and in particular, from a point of view of the kind of devices that are coming next. And this is the wearable space of egocentric capturing devices and also egocentric computing devices. Very related to robotics. So hopefully we'll see some great themes along here when we start getting into how we actually solve for the always-on problems, and in particular on the small form factors with sort of limited sensing and compute. Just a quick overview here. I'm going to start by taking us from where we are with AI today, which apparently is here and solving the Turing test and all that sort of business. So that's done, good. To contextual AI, which is a different beast altogether. And I'll claim that that's probably a more useful kind of AI that we really want. I'll take us into sort of like the introduction of Project Aria, which are the glasses that allow us to capture egocentric data, eye tracking, head tracking, and lots of other good stuff in a glasses form factor, and what that means to sort of like helping us solve the data gap to essentially enabling contextual AI. I'll then talk about building models of reality, and in particular, sort of a very 3D centric view of predictive models of reality, both world models and user models, and in particular, using a lot of spatial AI that's been maturing over the last sort of decade, and like I say, has a lot of overlap in other disciplines. And if I have chance, which I doubt I will, then I'll bring us onto the new problems that we're trying to solve with new data sets that are coming as well. Okay, so let's start with the big picture. Certainly during Turing's time, before there were any kind of graphical user interfaces, mobile phones, internet scale data sets, or any of that, he is certainly prescient in pointing out that what we really wanted were not machines that we'd program one-off, but that would learn from experience and potentially continuously through their lives. And that's fair because at that time, of course, all there was were humans interacting with each other. There was no model of the graphical user interface that would come to dominate our human-oriented perspective on computing today. Well, it looks like we're back to sort of like where we were maybe in the 1940s, and people are thinking again about the future of computing, not through the lens of literally 2D screens, but through embodied AI, robotics and all. So that's good news for all of us here today. Another important figure, of course, is Kenneth Craik, who you all know, who in particular pointed out, and again, these are sort of like, from the old times, but they're exactly right, over 100 years later, that if an organism is to carry a small-scale model of their external reality and of its possible actions within its own head, and its ability to, again, try out its various actions, predicts the consequences before they arise, and utilize the knowledge of past events to predict future events, and in every way deal with the reality that the creature faces to make it basically safer and more performative. Now, Kenneth Craik, when he was writing that in 1943, right around the time when computing as it was being developed, again, had no perspective on where robotics was going to get to, or the kind of language models that were going to come over 100 years later and solve a lot of intelligence problems. So we have to kind of map our idea of a predictive model of reality that's in a creature's head now into this new space that somehow does solve it if you get enough data, and doesn't look really much at all like creatures and their brains. Okay, well, anyway, AI is here. And so like I say, good job, everybody who worked on that. It looks a bit like this. You type into a text box anything you want, and somehow it gives you an intelligent answer based on simply predicting the next token. And so it goes. There's a predictive model right there, and it was trained on internet scale data. And that's very useful. And certainly, I think it would be wrong for us to imagine that it might be impossible to do it again with all the other modalities. But there certainly is a problem in that something is missing in the data sets that exist online. And whether or not they could ever capture the kind of human experiences that would allow us to build predictive models built on that kind of technology is, I think, tenuous at best, if not, questionable as to why on earth anyone would put their life experience on the internet at the scale of kind of like what the internet is with respect to text and images. So what's missing from AI today? Well, it's your real life context, and our job is essentially to get there. That's where wearables come back in. They start to close the gap by being able to give sensory perception to the kind of AI that exists today, whether it be imagery through things like Ray-Ban Meta or certain various microphones that might record what just you're saying, or in otherwise like observe the world from your egocentric perspective, as we call it. In fact, if people are using health apparatus like rings and watches, if you're a sports type person, I see Lourdes is in the room, she's a runner, I'm a cyclist, we use contextualized AI all the time from a point of view of continuous capture of our performance metrics, how many watts I'm putting out, how my sleep's going. So we're actually used to this kind of like pervasive capture. And the question is, of course, could it extend to this sort of much more extreme modalities that have much richer data like imagery and video? Well, that's where Ray-Ban Meta come in, and certainly it's a product, you can buy it, and it certainly lets you ask questions about reality. You say, hey, Meta, look and see, and then it does visual QA. Again, that's the sort of great thing that's happened in the last sort of 10 years from when visual QA was first introduced as a problem to where it really is already deployed in products. But I'm not interested in this kind of like triggered version of AI where you have to ask a question and only then it turns the sensors on, because my contextual AI is defined by what I think is going to be useful, and I think you'll agree, is about all of your context, even when you're not interacting with an AI. So for it to be useful, it really needs to have a timeline, if you like, of all of the things that have been happening all of the time, and it needs to do so in a privacy-aware way, and it needs to be able to put that together with all your digital data, and then you apply the AI and reasoning system. And I particularly claim I don't really think AI from a point of view of the reasoning system is really problematic, actually. I think if anyone here has interacted with ChatGPT today, there are several ways of having interactions with it. The main problem is it literally has no context about you. So it's going to make really dumb mistakes. It's going to generalize with its kind of a world model. Whereas if it did have access to your continuing life, then actually there's a good claim that it could. Think of your life as a novel being played out, one sentence at a time. It's fine, there's lots of people who have written about things over the last 100 years, and they have been consumed by these LLMs. But getting the context from your actual physical interface to that system is the real problem that I think embodied AI has to solve. Okay, so always on contextualized AI is what we really want to get to, not just sort of interrogative, reactive AI. And we need to go from these internet scale data sets that don't have the data manifold that we need to contextualized AI. And this is where Project Aria comes in. So Aria is essentially, and by the way, go along to projectaria.com in case you want to try and get a pair. They're free for industry and academic researchers. Otherwise, there's data sets there. It's a pair of glasses. You can wear them. They're wearable. They're light enough. They have no display. They're literally just there for doing research. And they have eye tracking and head tracking and microphone arrays and IMUs and all the good stuff that, again, maps very well onto sort of like the robotics domains as well. And in 2021, when we started to hand these out and get research teams across the planet working with us and independently producing their own data sets, we were, excited to see for the first time the kinds of data in this real diverse domain. And it's very different from internet scale data. Photographs are photoed from a point of view of purposefully capturing a thing. That's not what egocentric data looks like. Your head and your body are moving around to keep you, mobile, interacting with the world. And that's a very different problem. Like I say, we've been interacting with a lot of labs, and I hope if you're not on here, you can join us soon. There's a lot to do. And its general mission, Project Aria, is to help accelerate contextualized AI by advancing the wearable machine perception and AI research that can't be done without this new kind of data. Okay, so what does a diverse data set look like? Well, if you haven't had a chance to do this in your own life, why not take a pen and paper and write down what a day in your life looks like? Because in a sense, that's where your AI has to work. This may or may not be my real life. I'll let you choose. I woke up at some point, it was around 6 a.m. I might have read the news. Actually, the first thing I did was put my glasses on. I walked a dog, I don't have one. And eventually I started work and so on and so forth until I went to bed again. Now, these are the events that happen, all the time in our day, and every single point actually is augmented by ever finer grain things, events. At some point, they are physical events. We interpret them in a semantic way over a context window, and we reinterpret them. That thing that was a nice dinner turned out to be a mediocre dinner when you got sick that night. Your best friend who sort of betrayed you was no longer your best friend. So what we have are physical interactions that can be reinterpreted again and again and again. And our job effectively is to collect the context, not as it's understood in that moment, but as it may be understood, indefinitely. That means it needs to be captured at a very low level of granularity without interpretation, much more like physical events, actually. Okay, now just picture this. Excuse me. I think we can all agree that LLMs have shown that you can do next token prediction. So here's a big picture of embodied AI. Build systems that allow capturing of that kind of fine-grained context, and then allow systems to essentially predict the next token or fill in. It's a masked auto encoder type problem. And I personally have no doubt that if there were enough data sets, enough scale, then we would be able to start to predict over events, over horizons of certainly hours, days, if not weeks, years. Why? Well, I don't know why not. In the same way that we are within a manifold, for you to exit that door there at some point, you do have to walk through one of these doors. The predictability of humans is actually a much tighter distribution than I think we really have thought about until perhaps recently, where language models from the internet scale can kind of do a very good job of capturing intelligence through next token prediction. Okay, so can we just get the raw data and basically give it to these LLMs? This is this question of like, will LLMs get us there if they are enhanced with multimodal data? Well, this is a nice study, 2023. It's been updated since by a few different groups. I claim that the answer is absolutely not. The reason is because there's a big problem with simply trying to augment LLMs with the modalities that come from things like eye tracking and so on. And not least because the data sets cannot exist at internet scale. They'll probably never exist at internet scale, at least not for the real world distribution. Okay, two things, data and compute. There's two different types of data. There's the data that's needed to train a future LLM or other AI model in your data center, and that can be very big. But at some point, the distribution has to match what is possible on a wearable device or a robot system. And they can be very different, because whilst you might be able to capture megapixels of video for offline processing, possibly, then certainly you can't use that same data distribution on the device. So actually, it's not the same distribution in a very serious kind of way. The on-device inference versus offline inference problems are very different. And you can't take a cloud and put it on your compute device on a wearable. And you can't even stream the data off the device. There's too much data there. I can go into the details in a second. Same is true for compute. You might have an absolute army of A100s somewhere harvesting gigawatts, but actually at the end of the day, you've got to do the inference on the device in real time when you need it. And in fact, I think what we're going to see is that these two are interrelated. What we really need are devices that allow us to tokenize in real time reality, so that that is compressing what is exactly going on. And that's what will be computed with. Okay, excuse me. So data constraints, let's get serious for a second. Take yourself a Project Aria device and ask, okay, well, maybe my A100 farm is big enough to do some sort of like massive multimodal LLM learning with it, like next token prediction and so on. Well, here we have a look. We've got SLAM cameras, RGB cameras, eye-facing cameras, IMUs, microphone arrays. There's 7 microphones on a Project Aria device. Even when you're, reasonably compressing that data, you're looking at nearly a terabyte a day per person, just for an 8-hour day. Now, that's not very diverse from the point of view of a sample distribution of reality. We're used to data sets from the internet scale that are more on the order of millions of people over decades of input. It's very compressed already by the time that somebody's making a Wikipedia page. This is raw data and it's redundant. And even when highly compressed, essentially it's too big to store. If you do want to have interactive data sets, lots of people interacting with each other to understand what the distribution of that kind of data is, you're talking about petabytes of data per year, just for a year of interaction of 100 people. These are tiny numbers of people with tiny sort of like very narrow perspectives on what reality is. You can't scale this to the equivalent of internet scale egocentric. So in a nutshell, no, you can't store the data from egocentric at vast enough quantities. You can't actually input them into context windows, no matter how quote unquote infinite the context length is. Seriously, there isn't enough working memory to put it in there. You can't transmit it over, comms in real time unless you are happy with like 10-minute battery lives for your devices, which means then, of course, it's not going to be on. It's prohibitive even from the point of view of the sensors themselves. The underlying capture of a mobile phone video will take a good fraction on the order of 10% of essentially your phone battery if you were to leave it on for an 8-hour day. Now that's doing nothing, just the raw data, not even compressing it. Then add on compression and transmission or computation, and suddenly your 10-watt-hour battery is going to die in your phone. And yet our mobile phone is 10 times bigger than the battery that can go into a wearable of the size of a Ray-Ban Meta. In fact, it's over 10 times bigger. And of course, there's privacy concerns. That raw data has bystanders in. And whilst I might consent to my timeline being captured and used with AI, you didn't all consent to being in my sort of like context window. So let's get away from raw data, which brings us to building a model of a person's reality, the user's reality. This is back to Kenneth again. I think if we just flip a few things around and replace the word creature with AI, what we know is that what we really want is for an AI to build a predictive model of the user's reality, and then all the rest is true. So the question is how we're going to build a predictive model, because that predictive model can be highly compressive. And effectively, that's the main job for us to do in embodied AI, I think. Okay. So what we're going to talk about is a 3D world model, a user agent model, and the way in which the two have got to interact. I'm not going to cover absolutely everything here, but I'm going to try and cover a lot of how we can get that 3D world model and how we can do it in real time. We've been talking about 3D models, 3D world models for a while. Remember, all of this has got to be obtained, built, and kept up to date by the glasses devices themselves or other egocentric facing data. We don't want surveillance from, for example, devices. I want to own, if it's my model of my reality, without it needing to be shared necessarily. So we'll talk about that. We'll also talk about the user agent model. And again, we'll start actually from a full physical point of view. I really want to know where my body is, the full pose of where I am, what I'm doing in reality. But I'm also going to talk about it from a point of view of a user's personal timeline. So this is where, for example, what they say, where they are, what they're interacting with, and those sorts of things are highly compressive of the user's reality state. And so you can probably have a think of these types of things that might be important. We call them functional primitives. We want to know not all of the raw data and how it might be interpreted. We want to actually try and capture primitives that then, when they're reinterpreted later in context, in a short window, a long window, maybe months, years, then actually they can be reinterpreted. So I'm not going to put an exhaustive list there, but think of how compressive reality might be if we make judicious use of functional primitives like this. For example, and this is usually thought of from a point of view of digital data, who can have an estimate here of how many bytes per day for everything that you, on average, may write, whether with a pen or with your keyboard or with a mobile phone, everything you read, whether it's on a poster or on this screen right here, everything you've said or spoken to someone, and everything you've heard spoken to you, all of your physical, basically written and spoken interactions. Who's got an estimate of how many gigabytes, megabytes, how much is it? There's a secret prize for anybody who can get within an order of magnitude. You're on the right track. It's approximately a megabyte a day. If you're really sort of like allowing for all sorts of keystrokes. That is to say, when you press delete, you include those things and so on. Honestly, these are tiny numbers. And when all utterances, so not just spoken words in terms of sort of like pure syntax, but also sort of like the markup, the inflection, the intonation, and so on. But it is absolutely tiny. And think about that in comparison to the raw data that actually may be substantially more than that. Same is true for everything else. So everything you've touched and held, you only have two hands. You can only interact with so many things at a time. And you can only see so much at a time. In fact, this is one of the biggest differences with where I think computer vision was to where we're going to get to with embodied computer vision and AI. You have a 2-degree field of view fovea, and your eyes foveate via saccading around in space. That 2-degree of free fovea is where you see high resolution, i.e. to allow you to read. Everything else within your around 120-degree field of view is incredibly low resolution. When you take a 2-degree field of view and try and obtain 1.5 arc minutes, or what is necessary to see 20/20 vision,
you need about 128 by 128 pixels. Think about that. That's actually what you need. Now, you also only saccade up to, or fixate up to about 8 times a second, especially if you're speed reading. That means that your eyes are ticking around, going tick tock, tick tock, tick tock. They're not going at 60 frames per second. You can perceive motion and you can interpret it, but actually what you're looking at and changing is more on the order of up to 8 things a second. Think about that for a second. Incredible compression from humans. Of course, we evolved this because we have limited compute. We've got to get stuff done. And your entire body pose, be generous, give yourselves 200 degrees of freedom times a certain sample rate, multiply it through by an 8-hour day. It's still tiny in comparison to the raw data that would come from, a 12 megapixel image. Okay, so we're on the right track and we would like to have a model of interaction. Okay, our team has been working on this. We've been calling this live maps for a while, and it's really around building essentially the system that captures the environment, keeps it up to date from a 3D point of view, captures the user and keeps that state up to date and keeps the interaction between these two models all up to date, and does so in an online fashion, i.e. no offline processing. And remember, this has to be done using just data from a wearable device. This is what we're going to go through. Okay, building context with spatial AI. So this is what we've just seen here. This is actually Julian Straub, one of our lead researchers in this space. And that's him walking around his apartment somewhere in Seattle here. And the model, as you can see, it takes just a few seconds to start to build it. Now, this is really classic stuff. This is SLAM and reconstruction in an online mode, together with some very new stuff of being able to infer entire body state. What you'll also see is those sort of like trails that are going on. Those are the objects that Julian is interacting with in his environment. And in a sense, everything you see there, of course, it's not photorealistic, but that is the state of his reality. He walked into the kitchen, he picked up an apple, he took it to the table, he put it down, he picked something else up, he took it to his bag, and it went on and it went on. And this dynamic scene graph essentially is the compression of what otherwise would have been for that clip, at 12 megapixels, actually megabytes of data. It's like less than kilobytes of data, in fact. The underlying world model that we talk about, the 3D world model, consists of essentially this kind of set of external maps. If you've got them, use them. Google's done a great job, and other mapping teams have done great jobs of saying that we know exactly where this building is. The question is, can you connect it to a location system so that when you, with a pair of glasses, are about to walk into this building, it knows that? If so, that's great. Connect location maps from SLAM systems with external maps. Then essentially build physical surfaces, because whether it's a robot or a user, knowing where the physical surfaces are in reality allow you to predict what might happen there, but also essentially be able to track more effectively the sorts of interactions that are happening in a space. They happen on this surface, this is my desk, etc. Which brings us to the point about building structures and other kinds of 3D indexing. Essentially, if we can tokenize reality at the level that humans already describe it, at least at a coarse level, things, spaces, then actually we're already doing a great job. There's nothing stopping, us then anchoring other bits of raw tokens from various multimodal encoders onto that stuff. But there's really no reason not to make use of the fact that a chair that's rigid from a point of view of a user who picks it up in this room and moves it somewhere is like, not a useful atomic thing. Let's just give it 6 degrees of freedom and then start to track other properties on it. Now this might all emerge from giant data. The problem is, see for reference the beginning of the talk, that data is not coming from the egocentric perspective. We cannot capture egocentric data at internet scale. Okay, then the dynamic model of the user and their interaction with the environment. For the location maps, this is really sort of like the core technology that's needed for 3D embodied AI. This is a real-time visual inertial odometry system that works from just the IMUs and the SLAM cameras, so low resolution cameras that can be always on, and essentially provides a centimeter to millimeter accuracy trajectory of the device, and hence the person's head if they're wearing it. Now you're in trouble if your head and your glasses are not near each other, and they should be. There's a problem for where the rest of your body is. But this is where everything starts. If you have this is a space-time frame of reference that we can use. Again, this is sort of like an inductive point of view. Let's use space and time. Let's not have it need to be emerged from machine learning models. And now we can start to anchor things in that space. The first thing to anchor are the physical surfaces. Now, what seems like a very long time ago, although it was only 2018, 2019, we were building dense 3D models using structured light cameras but I just came from the XR Nerf workshop earlier today where, effectively it's now perfectly fine to take a pair of ARIA glasses with no depth camera on and produce beautiful photorealistic 3D models, static, of that environment. And a lot of people are well underway trying to make these dynamic models. There's big problems with that due to the amount of data that's actually there. But yes, building surface structures and even photorealistic ones is a generally solved problem at this point for the level of what we would assume is good enough to get on with the rest of the problems. The thing is, a lot of those techniques are offline, and what we want are online inference techniques. I can't wait for all of the data to come in before I start reconstructing it. I need it right now. And so what our team has been working on is a new generation of essentially egocentric foundation model informed fusion techniques. So everything I'm going to show you here again is using only data from ARIA. The way the technique works is that essentially we take the multi-camera video from ARIA and we take the point cloud that comes essentially for free from the SLAM stack, and we push that into what we'll see is essentially a convnet that will predict directly the occupancy of a volume. It actually also predicts the objects in space, but I won't talk about that here. This work is now online if you want to take a look. I think the most interesting thing about this work is that it's trained purely in simulation using the ARIA digital twin and ASE data sets that have been released on the Project ARIA website. That's quite a big data set. It's hundreds of hours, but it is simulated data, and then it transfers over to real ARIA glasses. And the technique, in brief, is we take the underlying inputs together with essentially the SLAM. Sorry, thank you. 2 minutes. Together with the SLAM map, and we use already backbones that have been frozen for 2D image techniques, and then we back project that into a volume and allow a UNet to essentially decode it through end-to-end training with the simulated data to a bounding box head and also an occupancy head. And then we just push that through good old-fashioned TSDF fusion. Okay, static indexing. This is simply enough. If you've got a point cloud and if you've got techniques that give you beautiful segments like segment anything, or in this case, master 2 deformer, you can color those point clouds, cluster them, and away you go with respect to producing bounding boxes of objects. And this works very well in practice. Again, you can see all of this is happening incrementally as the system works online. Dynamic indexing is a new area. So this is where essentially if you've got hand tracking from egocentric cameras like from ARIA, then the problem here is even if you don't know what the object is, can I change the state of that model so that I can keep track of it? And that's what we're doing here. And this actually just uses a very simple 3D technique, which is if I know where your hands are, and if I can tell that what you've just done is change whether or not you're holding something or not holding it, then I can start to trigger very simple mechanisms for detecting if that object is the same object or a different object, actually just at the visual image level. And so then you can essentially start to keep track of a library of those things. And because your hands are in 3D, then effectively those objects are being tracked in 3D. So that's a nifty trick, and certainly a new area that very few people are working on. Finally, human state. What I'm going to say about this is that this is really a very exciting area, because if you start with hands and then start to ask, well, the rest of the way that the world is moving by all the humans is because their bodies are moving and then their hands are moving the rest of reality. So from a point of view of keeping a model of reality up to date, getting the whole body state decoded from just egocentric data really is a key area of embodied AI. Robotics have a slightly easier because they have the proprioception. We need to sort of like infer all of that just using the cameras. So what we've done is we've built a very nice data set that's just been being released online. I think you can type that into Google and find it now on the Project ARIA website. And what we did is we took a pair of ARIA and we paired it with an Xsense full IMU bodysuit to generate the world's biggest in the wild human motion data set. This is indoors, outdoors, day, night, and it also includes a third-person perspective of a second ARIA wearer watching all the time. The first ARIA wearer, so that's some interesting data, includes narration of the things that they're doing. It's useful to know that sort of, your wrists move something like, 2 and a bit times more than your head. I don't know if you ever wanted to know that stat, but we do know the stat that your wrists move more than your head. It makes a lot of sense. And that's a beautiful data set. Now, given that data set that ranges, like I say, indoors, outdoors, over hiking and so on, we've been able to train a diffusion model that decodes directly just from the SLAM pose plus the point cloud that comes from ARIA, together with a clip embedding of the RGB, essentially the entire body. And this was very surprising, effectively because that RGB camera hardly sees the rest of the body, but there's just enough information in the VIO trajectory that's got a lot of dynamics together with the context that comes from CLIP and the underlying point cloud that we provide as well, local point cloud, to decode. This is Lingmi, the lead researcher on this. It's actually on archive now. This is actually my favorite sequence as a cyclist. I hope this one shows. Let's see. Oh, it may not show. This is my favorite sequence of essentially a person cycling and decoding. You'll have to come and see me later if you want to see that. Okay. In a nutshell, that's it. I guess these shouldn't be highlighted. I said we wouldn't get to the new problems. We didn't. You'll have to come and see us later on. Thanks, everybody, and I'll take questions.
5 extra minutes. If anybody has any questions here from the audience, otherwise we have a bunch of Slack. Go ahead, please.
Yeah, do we have an estimate of like when you're considering only the 12 view, and if you would save it instead of like the 12 view, would it be more manageable?
You know, I'm glad that you said that because that is exactly what this section was about. And so, yeah, in a nutshell, I'll just show you when you've got eye tracking, as you do from ARIA. In this case, this is shown together with Segment Anything, just to start to highlight the power of, online foveated segmentation. But when we think about the raw data, which is what you're talking about, this is where it really gets exciting. If you start to drive imaging systems in egocentric wearables like ARIA through foveated capture, you can get on the order of 3.6 thousand, times reduction in the amount of data for the principle that I said. Now, you might want to capture a low resolution, rest of the non-foveated region, and you can do that actually quite well. Actually, if you just take a 64 times downsampled version of the 2 to 4 megapixel ARIA RGB camera and then push that through H.264, you're back at kilobytes of data. It's very good at doing keyframes and so on. And then that high resolution bit from the fovea driven by eye tracking is tiny amounts of data as well. So yes, by the way, if you've got ARIA, you can do this yourselves with the the eye tracking that comes from the machine perception services. If anything, I've been most interested by the fact that very few computer vision people seem to have thought about eye tracking and humans and how they see relative to the big problems of big data and particular multimodal data. And yet this is exactly what may get us over that next hump. We can capture lots of this data and even give it to our multimodal predictor models if it's in this form, but not in the full capture form. That's a great question.
So your motivation that we are actually able to keep track of timeline and mention some amazing progress like in tracking of the human states on the motion level and also making the prediction for that. So is there any ongoing research as well to keep tracking on both say the motion level as well as sort of high level task level?
Yeah, that's great. So yes, and one way of thinking about this is that if you start to take those physical events and start to align them with effectively textual summaries that are a small enough sort of granularity, and then bunch that all together with when it happens, and then simply give that, Richard walked into the room. Richard picked up a can and Richard drank, and then Richard turned his head and gestured, and then give that to an LLM today. What does it do with it? Well, exactly what it would do with director's instructions, to a play. It does very well, and it does things like summarization and so on. So you can keep track of the higher level, not by having to, in real time, implant what it is being interpreted as, but literally after the fact. And that's the power of sort of capturing at this lower level of events, that you don't have to spend all of your time trying to interpret in a narrow window what might actually only a few seconds later be absolutely obvious what is happening.
One more. There is one from Slack. How do you estimate the megabyte of sort of compressed data? And the question goes as is that culturally standard? Like if you go to different cultures, you expect different amount of.
Oh yeah, so it's actually significantly less than the chap over there who said 20 kilobytes. It is between 100 kilobytes and a megabyte, even when you add in all sorts of variations for speakers. And it's not massively culturally different. It can be a lot smaller than a megabyte, let me tell you that. I added an extra 0 on there simply because it's so ridiculously small. The reason is we evolved to not be able to easily hear whilst talking. We evolved to essentially have two hands that require attention mechanisms to be able to interact with reality, because we only have one body that can manipulate the rest of the world through or act in the world. So it's very real that effectively these things are, these are social across the planet, because it's part of being an embodied creature with this type of morphology. Yeah.
Well, thank you so much for
Oh, I can't do a split screen. I think you can. You probably just need to set up. It's probably easier just do it without a split screen if unless you have timings or something.
I had the notes, but
No,
I'll wing it.
You'll wing it? Okay, okay.
I think I got it.
Okay. And
Oh, perfect. It's working.
okay, it's
Does a Zoom look like that?
Zoom looks like
Okay,
this, yeah.
great.
Perfect. So it's 2 p.m. So why don't we get started? It's my pleasure to kick off the interaction challenge speakers with the ManiSkill challenge. These speaker talks will go from 2 to 2:30, and then we'll have a speaker Q&A where all the speakers can stand here, and we'll field questions from the crowd and hopefully have some fun discussion. Take it away.
Thank you. Thank you. Hi everyone. My name is Stone. I'm a PhD student at UC San Diego, advised by Hao Su. I'll be covering kind of two things today. One is on the vision-based tactile challenge results, and I'll also be covering some of the new features in our new simulator ManiSkill 3, which is the fastest state visual GPU simulation in robotics. Without further ado, introducing the ManiSkill Visual Tactile Challenge. The goal is to train a policy capable of relying on just visual tactile sensing data to perform tasks like charging a phone, opening and locking more without actual rendering cameras or like state-based information. The two challenge tasks this year we propose is peg insertion and lock opening. Oh, sorry, this is covering a lot. Where both these types require a controller or policy given only the visual tactile inputs you can see below in those images. The challenge is quite difficult since for the test setting, the peg insertion task, you aren't told what shape of block you're holding. And for the open lock task, you're not even told what shape the key is. There could be 2 keys, 3 keys, you don't know. You have to use trial and error and tactile sensing to be able to solve these tasks effectively. So this is what the real world setup kind of looks like. There's kind of like 4 dimensions of control. There's 1 rotational axis and 3 axis translation stage to kind of move this robot gripper up, down, left, right, rotate in 1 angle to try to open locks and insert pegs. And attached to that gripper is 2 what are called gel site mini sensors, which provide that tactile information. This challenge has a custom simulator based on FEM and IPC supporting intersection-free and inversion-free simulation. It can stably simulate the elastomer, which is the gel site mini sensors, large deformation during reinforcement learning training, and also supports diverse 3D geometries via mesh-based representations.
Oh, sorry, there's just something blocking the way.
Oh, sorry.
No, you're good. Where's my? Oh,
I think I can close.
You can get it. Yeah.
Apologies. Zoom is very fake. Perfect. Great. Okay. Hopefully I can hide this too sometime. Yeah. Great. Okay. So in order to process this data, we provide all competitors an efficient tactile signal representation, which is effectively just a point net operating on reference positions and current sense tactile information. This is a permutation invariant thanks to the point net architecture, and it's fairly robust to tracking loss and achieves fairly good generalizability. In fact, the generalizability is quite good because our sim to real gap is quite low. Here is a direct transfer of a simulation policy to the real world of the peg insertion task. And the success rates are fairly similar. So we are fairly confident in our simulation to be able to accurately model this tactile simulation. Before I announce the winners and conclude some about the results, I would like to thank the 18 different represented institutions that participated in the challenge this year. We hope to get even more competitors involved with these sim-to-real type challenges as they provide great accessibility for labs and students without access to expensive hardware. Without further ado, congratulations to these key teams. Second place, Team Luban from Zhejiang University, Team Touchnet Innovators from Tongji University and King's College London, and congratulations to first place team, Team Illusion from Guangxi University. The overall results is as so. For the peg insertion task, the best success rate was 70%. Thank you. And the best open lock success rate is 40%. So clearly lots of room to improve. And turns out the best solution is the one that scales best. Behavior cloning and task-specific RL tuning. Yeah. So we plan to kind of launch the next version of the competition somewhere around the end of the year. And we'll also include a new sensor design track. If you're interested in more technical details about the future challenges, you can email that address there, or you can also scan that QR code. This QR code will show up again at the very end of my presentation. And big thank you to all the organizers and students who helped develop and organize this challenge as well. So on to the next part, I'll also be kind of showcasing ManiSkill 3, a massive upgrade from previous iterations of ManiSkill that include incredibly new features and results primarily around parallelizing almost everything onto the GPU for robotic simulation. So the first big feature is GPU parallelized state simulation, similar to Majoko's MJX or Isaac simulation. But the main difference is that we support very, very fast state-of-the-art parallel rendering speeds. More details on that later, but on the right there, for example, that's actually a visual policy trained in about half an hour with reinforcement learning using pure RGB inputs, no state. So yeah, I'll cover more details on performance benchmarks and comparisons of other simulators in terms of rendering, but this is now possible actually. Different to also improvement is we have a ton of new tasks and robots spanning quadrupeds, humanoids, as well as standard manipulation tasks. We even have humanoids developed by new startups. There's a little Stompy robot from K-Scale Labs. There's a couple other robots in there from Unitree, quadrupeds, all sorts of things. We also support large-scale complex scenes like those in Allen AI Score Simulator, as well as the replica CAD dataset. And for the first time, these tasks and these complex randomized scenes can now be simulated entirely on the GPU. We also support a very interesting feature known as diverse parallel simulation on the GPU, where each parallel environment can have different objects and articulations of different degrees of freedom. We provide a very simple and easy to use API to build tasks with this property, enabling more generalizable robot learning. The task on the right, for example, is actually a task core from our very first ManiSkill challenge in 2021, and it used to take like many, many hours to solve. It served as a fairly good benchmark until now. These days, we can use GPU parallelization to simulate every cabinet in our dataset 20 times each, and learn to pull open every cabinet on the order of minutes or hours instead of days or weeks it used to take before with reinforcement learning. The policy shown there is actually an RL policy trying to open every cabinet. Another example is learning generalizable manipulation for, let's say, cleaning a house. The video on the right is a recreation of the Habitat Rearrange challenge from a few years ago, where a fetch robot must clean up objects in a room and place them to designated locations. And here we're just rendering every parallel environment. Each one has a slightly different room layout with slightly different objects, placed different places. And this is kind of like a bird's eye view. And some internal lab work that we want to release hopefully at the end of the year. We are training a visual RL policy from depth images to kind of solve this task completely on GPU simulation. And again, our new diverse GPU simulation software is able to enable this training at scale much, much faster than before. The last kind of highlight of the new simulator is everything is open source for the first time ever. So ManiSkill itself is like a task and APIs plus assets. This is open source. SageGen is the underlying rendering system and kind of simulation framework that's been developed since 2020. In our lab, also completely open source on GitHub. You can find it online. And for the first time, also PhysX, which is the physics engine we use, was recently open sourced by NVIDIA. And so our entire simulation tech stack is open source. If you ever have a bug, we can always figure out what's wrong. Yeah, and so we really want to embrace the open source robotics community in this way and get companies, startups, academic labs all involved in improving performance, usability, and more in the simulation. So for more concrete numbers, just for example, with a fairly big camera relative to simulation standards like 256 x 256, we can render close to 20,000-ish FPS on a 3080 GPU and much faster with better GPUs. No task-specific rendering code is done here. And this is being compared against Isaac simulation, Isaac Sim. We have much better memory and FPS performance, and we support rendering RGB, depth, and segmentation at the same time at this FPS. Just for a quick demonstration, on the right is a task where a robot has to try and pick out an object out of clutter. Note that each panel environment has different geometries and a different number of objects. So now we're just going to render 4 of them at a time, 16, 64, 132 of them at once, and so on. You can even run about like 1,500 of these in parallel, each one with RGB, depth, and segmentation being rendered at the same time, all quite fast. Obviously, I'm not going to show the 1,500 one here because I cannot possibly fit such a large video, but you can try this yourself right now. This is released. Another big feature we want to come to the ManiSkill 3 is just trying to support more reproducible robotics research and digital twins. We had a recent collaboration with people at Stanford and Google DeepMind working on what's called the Simpler project, where we built evaluation digital twins of environments in the OpenX dataset. So for the first time, you can evaluate policies like RT1, RT2, and Octo in simulation without having to have the actual hardware at home to try to test these things. And again, trying to support open source robotics and reproducible robotics. Yeah, and so for the that kind of, that's an example of the digital twin. So to conclude this presentation, the big takeaway is not just the new platform or like cool visual tactile simulation, but the fact that there's great progress as shown in past talks today, and this talk in sim to real and real to sim in all modalities, especially vision and tactile simulation. And as the domain gap shrinks, I believe that simulation will become a bigger and bigger part of the future of robotics evaluation and training. So we are hoping to steer this training platform and our challenges in the future towards this direction of sim to real, and by improving visual data collection speed and diversity and embodied AI. Feel free to scan this QR codes, but thank you.
Have the Arnold account.
Test.
Got it.
You have to reshare.
Sorry, we're running the wrong Zoom. Yes, okay, where are we? So Arnold includes 8 manipulation tasks situated in the virtual household environments, such as rigid object manipulation, articulate object manipulation, and the fluid manipulation tasks. We also, like for each task, we provide template-based language instructions specifying the goal states, such as lift the bottle 30 centimeters from the ground and pour 80% of liquid to the cup. And to collect accurate demonstrations, we first obtain human annotated task configurations. Then we use data augmentation to increase the diversity and scale of the configuration. Finally, based on the configuration, we use a key points based motion planner to generate 10K demonstrations across the 8 tasks. The manipulator we have in Arnold is the SEC7DOF Franca Amica Panda robot with a parallel gripper. We placed 5 RGBD cameras around the manipulator. The visual observations and camera parameters are provided to the robot as inputs. And the model needs to predict the end factor translation, the rotations, and the action of the gripper. We create a total of 800 test cases for evaluation. The test cases cover in-domain tests and the generalization tests for novel objects, scenes, and states. We further withhold the part of the test case and do not show their results on the leaderboards to protect potential overfitting. A test case is considered successful if the object state is within the respective tolerance threshold of goal states continuously for 2 seconds. We compute the average success rate of all the test cases over 3 trials and use that as the final evaluation metrics. The challenge was open for submission from April the 2nd to June the 1st. We received a total of 99 submissions from 9 participant teams. And the highest performing model is able to achieve 45% success rates. In comparison, the baseline solution based on the Preact model can only achieve 22%. Without further ado, let me introduce the challenge winners. The third place team is the SSU Reality Lab, affiliated with the Songso University. I'm not sure whether they were able to be here today, but there is a short video introducing their solution.
Which is developed for the Arnold child. So it is running the subjects, which is a continuous birth case, such as
Okay.
Starting the part model as baseline of our work. We propose a solution function based on the agents that state population. Page inflation displays criteria and position that can generate various state data with precisely instruction. Our PSA trained models specialize in breast manipulation.
We're at time, so if you could just, we can't play the video.
Sure, yeah. So the second place team is the Fun Guy team from affiliated with Xi'an Jiaotong University. And the first place team is the Robot AI, from University of Science Technology of China, Deep Space Exploration Lab, and the Stanford Research Institute. And I like to thank for all the organizers and participants. I would also like to thank NVIDIA for the GPU grants. Thanks. Thank you so much. Sorry for the technical issue.
Nice.
All right, can we? Hey, everyone. All right, so I'm here to talk about the Home Robot Open Vocabulary Mobile Manipulation Challenge. So I'm presenting for Sri Mandra, who's a student that I work with, who's actually now starting at Stanford in the fall, but couldn't make it today to actually do the presentation. He did all the actual work putting the CVPR version of this together. So yeah, so what is this challenge about? So good question. I thought that was funny. Okay. Well, okay, what are our goals? So we want to make robotics research a bit more accessible. We would like to evaluate multiple different skills necessary for building a robot that can work in your home. Standardized real robot benchmarking. So we want to be able to test these skills in a way that you can actually try them out, and that we can standardize them, make sure we're making real progress towards problems that we really care about. Provide a platform for sharing ideas about how to solve these interesting problems, and also build a community of robotics researchers interested in deploying real generalizable home robots into different locations. So what is this challenge actually? So let's start with previous stuff like the habitat rearrangement challenge. So in the past, we've done a lot of work on geometric rearrangement of homes with known sets of objects, like you can see the YCV kind of Cheez-It box there. And these are small environments, known objects, all of this kind of stuff. Goals given as particular positions that you need to move to in the world. That's not really what homes look like. So really what you want to do is you want to have a robot, which is something like pick up the box on the table and put it on the sofa. So that's what our OVMM task is, our open vocabulary mobile manipulation task. So I want to control this mobile robot, a low-cost mobile robot that I can deploy into different home environments. I want to move that object from a start location to a goal location. The start location is given as is open vocabulary, meaning that I have not necessarily seen that object class before. We have a very large different range of different objects that it could possibly be. We also have not seen the environment before. It's a apartment or home or something like this that we have not previously explored it. You have no training data in this. You have no training data of the objects that are going to be involved in the challenge. So it's very challenging, as we'll see later. And the idea is that we have actually tested this stuff out in a apartment that Facebook owns. So this is an example of a robot performing this task. So picking up a stuffed toy from a chair and placing it on the couch. And then it picks up the toy. It has to actually successfully go find, look at, localize, pick up the object, pick up the toy. It then has to go and place it on the couch. So it has to go drive over, find a couch that it can place this object on. And then it actually has to lift up its arm and place that thing on the couch so that it doesn't fall on the floor. So we invited participants to submit their agents to this competition. So basically, you submit an agent, you receive egocentric RGBD, you receive the base pose, you receive joint states from the robot. So just sensor data, essentially, so no state information, no privileged information that you would not expect to get from a real robot, because we're not doing anything like that. The robot is running SLAM, so you get a pose relative to where it started, but that's about it. And then you have to predict actions like how far the robot should move, what the joint should, how the robot's joints should move, whether or not it should try to grasp, etc. So it's a very hard task, lots of parts. So participants are asked to develop their agents using our simulation stack. So the simulation is based on Habitat, particularly Habitat 2.5 now, where we have the robot moving around in these large simulated home environments. where it has to go and pick up these different it has to explore this environment. There's lots of different things that it could see. It has to find the target object and then move it to any valid location, from a valid location to a valid location. So if you pick up, if the task is to pick up a cup and you pick it up from a sofa, you pick up a cup from a chair and you pick it up from a sofa or table instead, you're wrong. So it has to do this all correctly. And then we test them using this. So you're supposed to develop and test using our home robot library and simulation. And then we can evaluate their solutions zero shot on real robots. So they're tested in our unseen test environment with unseen test objects. Based on, so we ranked our different participant teams based on overall success. So basically just number of times it manages to move the right object to the right location without colliding with anything and failing, right? So just what you would expect success to actually look like. Partial success meaning like whether or not it manages to accomplish each of these individual subtasks in order without failing. And also that basically if there's a tiebreaker, we can look at the number of steps that it took to do the episode. So we did a full version of this with the real world part of the challenge at NeurIPS. We didn't have time to run we weren't able to run the real robot version for CVPR. So we're just doing the CVPR version of this challenge. But I will talk, actually, I have a keynote talk later where I'll talk a lot more about that, the whole real robot side of this thing. But just to keep things short, we're not going to go into that now. We provide a bunch of starter code, which provides a modular baseline for chaining these skills together. So finding objects, looking at them, gazing, localizing, picking them up, etc. Participants submit their solutions as a Docker image to Eval AI. We evaluate them remotely and rank them. So we had 6 participant teams, 17 total submissions to the leaderboard. They were evaluated on 250 episodes, meaning combinations of start, goal, and target object, open up their object, using 10 held out test scenes and unseen instances, unseen objects. So a mixture of unseen instances of known classes and of totally unseen classes. And so this is the snapshot from the leaderboard. So we ended up with so the success rates were all less than 10%. So this problem is definitely nowhere near solved. A very challenging task because you have to move through a very large environment, find these sometimes very small objects that the robot can grab and move them from different locations. Lots of potential for failure. Partial success is notably higher so it's like being able to actually find objects in the environment is much easier sometimes, or at least feasible. But completing all of this is difficult. So I'd like to congratulations to Team Uniteam, who got first place on our leaderboard this time. They also got first place in the real world challenge. So they're probably not too surprised, I guess. Maybe they're confident in their solution at this point. So about those solutions, the top 3 solutions, so 2/3 of them built on our heuristic baseline. So we provided both a reinforcement learning based and just a motion planner based solution. Reinforcement learning solution was not the top solutions. The top 2 both used just motion planning essentially. 1/3 built on the RL baseline. They're the one that was below our baselines actually in that previous thing. So sorry guys. So all of them worked on improving the open vocabulary object detection though, which is based on foundation models, and that's a very important thing to see. They all had changes to high level planner, meaning that it was important to do things like error recovery and making sure and better exploration, things like that. So made improvements to all the different component skills. So what's next? So the leaderboard is still open. So it's great if you guys can keep submitting. This is a very challenging task. So there's a lot of progress to be made. It's also a very realistic task. That's part of why it's so hard and why everyone's scoring why we have like below 10% still, because like it is actually the case where you have a robot that has to move around in a home and find objects that are pretty small, right? It's very hard for current perception methods. So stay tuned for updates on future the competition, grow the community. Please let us know. Otherwise, thank you for listening and participating. It's 20 minutes to give a few words, but.
There. So you all can see each other. Breaking. Okay. Great. Cool. So I want to open this up to the crowd in a moment, but maybe just kick us off. I'm sort of inspired by Rob Sturchik's talk yesterday, where he talked about sort of real and fake tasks, and sort of made the point that we should be sort of really emphasizing working on real tasks, and those are tasks that actually have economic and cultural value. I guess I would want to start off a little spicy. Do you think the current tasks and your challenges are real tasks, or are they fake tasks?
Yeah, for my task, definitely not real task. Yeah, I mean, we have the possibility to make it a real task, but it would be like too challenging to like combine them, like a navigation part and a manipulation part, like into one challenge. So we kind of like split it like in and focus on the manipulation part, like specifically for this like challenge. In the future, like it makes like perfect sense to extend it.
Yeah, I think that our challenge is pretty good, better than most. I do think that it's still easier than it really should be, than a real world version of it is, actually. I think like the real world setup is simpler than it would be. So we're trying. That's all.
I'll definitely say I think there's different spectrums of real. You have one, there's an actual real world evaluation, and you have also two, whether or not there's something actually someone needs. Like, I don't think you really need a lock picking robot. But the point of research is also to investigate problems at maybe a smaller scale first, so that we can actually do something real robustly before we start tackling maybe crazy hard problems sometimes. So both are very valid to investigate.
So I guess you gave an example of a task we don't want a robot to do, although maybe argue, maybe a locksmith really wants a lock-picking robot, but that we don't want them to have one. But if you were to think about sort of a next incarnation of your respective challenges towards realism or towards having real tasks, what would that look like for your individual challenges?
I guess I can start. I think something I'm really excited about in the future as far as simulation platform is we want to support a lot of like open source and reproducible digital twins. So we aren't as focused on, let's say, mobile manipulation. And I think one problem with mobile manipulation is that it's hard to set up in your own home sometimes. But with reproducible ones, if like a lot of labs already have existing, let's say Franka robots, KUKA robots, whatever, just buy a few things off Amazon, use a couple rendering tricks to make it look as real as possible in simulation and try training it. That's something I hope to try to do something similar in the future.
Yeah, I think one big improvement that I would like to, okay, microphone. So one big improvement that I think that I would like to see from ours in the future is that we we simplify the manipulation component a lot. In particular, grasping is not really simulated in Habitat, which is a simulator that we have. So that means that you can't really learn that sim to real, that you can't really do that, which really limits the amount of utility you can get in a lot of cases. That being said, the task itself is like, it's perfectly achievable because of the simplification. It's all fine. It works in the real world too. But yeah, that's something that I feel like is really grounds for improving it if you really wanted to make sure this went robustly in reality.
Yeah, for my challenge, like as I mentioned, like currently the initial configuration of the task, like the location of the robot and location of object is like determined based on human annotation. In the future, like it makes sense to like allow the robot to freely navigate the room and determine like what's a good position to start start this like manipulation tasks. The other like extension would be like adding more like diverse things, objects, and like robot manipulators.
Awesome. And so as the sort of the organizers and people that are working on some of this technology, I feel like we sometimes have the best view into what is actually most annoying about our particular framework. So, and of course, when we sell it, it's all easy. You can hit install, it's done. But what is the sort of the major pain point for getting one of your challenges set up and running and training and actually getting them all working?
Yeah, for my challenge, I think the pain point is really like, on the higher level, like the challenging part is like how to make a right challenge, basically. How to like set the correct like difficulty level. Because if you like make it too difficult, then like there's would be like no like models would be able to perform like get like a non-zero performance on the like tasks. Yeah, on the lower level, I think like we have like that there's a lot of like technical gaps like we need to fill for the simulator, for the X-axis simulator we use.
Yeah, I really do think that getting the difficulty right is very important and very difficult. And I think it's entirely possible that we skewed a little bit too far to the difficulty side if it's below 10%. But yeah, anyway, in favor of being also realistic or somewhat realistic. So I appreciate that. I will also say ours is not solvable. It is actually like a little bit of an ordeal to get everything working properly sometimes. So I think there's a lot of stuff like this.
I think in basically every iteration of ManiSkill, we always run into evaluation challenges. Partially because we don't use eval AI, we always build our own system, actually, a cloud service, which is quite complicated. But I think another thing is like also trying to pick what the right metrics are to show. So I know like picking hard tasks, I think is important. But sometimes, success rate maybe is not the best metric, maybe like, let's say, partial success, or maybe measuring some other measures to show incremental progress. Figuring out what those measures should be is not super obvious. And obviously we don't want people to like game benchmarks just to optimize a few metrics. So I think ultimately picking the metrics is one of the harder problems too.
I have more questions, but I want to also make sure the audience gets to have some participation. So does anybody have any questions for these challenges?
I guess for all three challenges, what part of the tasks that you have did you see that people were getting? Or like where are the roadblocks to getting better?
So just to repeat the question for Slack or for Zoom. So what are the roadblocks for each of your challenges that are sort of gating progress?
Happy to start. So I guess we'll start from the middle this time. But I think that the main thing that we see that people still have trouble with is actually just simple object detection doesn't work that well in a mobile robot. And part of that's because things are not actually very well framed. And so if you're trying to do this generalization kind of stuff that we really pushed with this challenge, a lot of the times you'll see that just it doesn't fail, it doesn't work, it doesn't detect the things that you want it to detect. It's hard to train these things. It's just like there's a lot of problems, honestly. And for long horizon tasks, training is slow and expensive and just some issues.
A large part of a lot of the challenges and work we do now for ManiSkill is mostly around like sim to real, real to sim. That's always like one of the biggest problems all the time, and it's a big research topic. Now, obviously, we're not going to solve it, but every year we design a challenge, we always have to make kind of compromises to make sure we can transfer something to sim to real. So for example, this challenge, there's only 4 axes of movement, and it's already quite difficult. You can only move 3 directions in Z, X, Y, and 1 rotational axis, and beyond that, sim to real gap starts to show more and more. So we are trying to confine as much as we need without making it too simplistic as well.
Yeah, for the Arnold challenge, I think like we're seeing like in terms of success rates, like we're seeing large difference like across the task. Like we have like for the simple task like reorient objects and pick up the object, I think the success rate can be quite high. But for the articulated like manipulation task, we're seeing that like first, the horizon is like very long, and second, like we're seeing that the robots can oftentimes struggle like in detecting the like object parts. It actually needs to like manipulate, such as the handle of the cabinet or the drawer. And for the like fluid manipulation tasks, such as like transport water, is also like quite challenging due to like it requires very like fine-grained like a motor control. Otherwise, the water can spill like all over the place.
So one quick observation and then a question. The observation is I was a huge fan of Ross Gershik's talk yesterday too, and I'm all on board. I'm 50% on board with going after real problems. But he worked on object detection for a long time. So perhaps his need to pursue real tasks is sort of more urgent than these tasks, because like maybe we have the opposite problem that our tasks are too tough. Maybe they're too real. So that's observation. And then the question is, suppose GPU performance doubled, like overnight, and you had the choice of investing that extra performance into making rendering better, or making like more realistic, or making physics more realistic, or making training go faster. How would you invest that 2x GPU performance that you just got magically overnight?
So I personally would focus, I think the biggest problem is actually diversity in data. Because if you looked at the talk from Alan and I earlier today, you know, they just take Dino V2 features and it transfers fairly well, not perfectly, obviously. So I would think that gap is not the biggest problem. And in fact, my personal opinion is if you just train on simulated plus real world data, the features should align, right? I mean, I don't know if anyone's done this yet, but it should in theory. So I think the biggest use case is actually diversifying the assets even further, right? We have like hand annotated assets from AI2 Thor, Sapien, what other benchmarks you're looking at. If we can get that GPU performance, you know, procedurally generate and verify, like these are all usable meshes, collision meshes, visual meshes, you know, or use all those GPUs to, you know, scan every room in this conference center and build all of them. Because I think training time is not a big issue. I mean, I work on GPU simulation now, so I don't think it's a big issue. but I would say the diversity is definitely the biggest problem for simulation.
Yeah, I mean, I don't know much to say. I agree with that basically entirely. I think we could get I think diversity is the biggest issue.
Yeah, on the sim to real part, like if I have more like resources, I would probably like you know, try to like identify the physical parameters of a lot of like these articulated like objects such as cabinet and drawers, because I think that's the like bottleneck for the sim to real transfer. Instead of like, I think the like visual part is like partly like solved.
So obviously I've been a bit biased, or I'm a bit biased from coming from AI2, where we do a lot of procedural stuff and we use language models to generate houses and whatnot. But I guess on this theme of scale, are there sort of how do you sort of envision scaling? And if you want to scale diversity, how are you thinking about that? What are the pathways that you feel are most promising? You know, maybe procedural is not the way to go.
I can't take it first shot at this, I guess. I think one of the biggest things that language models have provided us is like kind of open set generation. Like prior to GPT, whatever end, it was mostly very much like closed set generation. You had a fixed set of tokens you could choose from, right? Now we all of a sudden have open set generation. There's a lot of companies now, including one from my own advisor actually, who do 3D mesh generation, right? So I think generating things from language is one way to scale things up. I think a better way to think about is maybe not just scaling up, but also just thinking about fine-tuning paradigms. Like, to be honest, I mean, I'm too early stage. If I were to start my own company, I would focus a lot on taking those extra GPUs, giving one to each person that buys my robot, and fine-tune on their household. Because I think if you want, like, for example, like in robotics, you care about like 99.99 success rates. Sometimes you can't get there just by a lot of data alone. You know, if you look at GPT-4, it has a success rate of like 50%, 80%, that's not enough for robotics. So maybe focusing more on fine-tuning may be a better approach instead of just scaling, right?
Yeah, in terms of scaling, I think procedural generation of the thing like could be the way like for the like navigation task. Yeah, but for the manipulation task, I think like we're seeing like larger gaps like there.
Yeah, I think procedural generation only works to a point because we still need to make sure that that scenes are like the visual procedural generation isn't all there is to it, right? We also do need things like, I think eventually we'll need to be able to simulate different types of carpet and different types of like textures the robots will need to move over, and like walking through clutter and all these kinds of very, very, very complex and unusual scenes that fall into this very long tail of possible weird outliers. I think that there's a lot of work to be done on how to best procedurally generate things. If you can get them to work well, it seems like the only thing, I do think that the best route at some point is going to be able to collect lots of data in the real world, especially as robots get more accessible, lower cost. I like the idea of just of collecting lots of data, of having hundreds and thousands of robots out in the world and being able to have people send data back. I think probably the best example of this has been what Tesla's actually been able to do with autopilot, right? Where you can collect lots of data and have it start to work impressively well, even if it's still not 99.9%. Yeah.
Thanks for organizing all those great challenges. I want to raise a concern and ask a question about the default robot embodiment design and choices in what is benchmark, right? And I guess the first question is that should we assume like a fixed embodiment, for example, like Venta? And second of all, perhaps more important for mobile manipulation, right? What's the right or what's the first choice of the mobile manipulator? That's gonna be the new challenge for them for this challenge. And do you think the current solution is sufficient? And especially related to earlier comment about real task and situation, what should people choose as mobile manipulator?
So I have pretty strong opinions on this. Someone who works for now, a company building mobile manipulators. But so I'll have more to say on this later. But I think that something for mobile manipulators, I do think there's a lot of value to having everyone using the same ones. I think one thing that we did in the competition, which I really liked, is having basically just be able to download a Docker image from someone and test out their entire robotic stack and have it like go around and try to pick and place in our environment. That kind of thing is really valuable. So I think that on this, so there's a lot of stuff on the software side. On the hardware side, it needs to be a reasonably capable 6-stop manipulator. It needs to be light enough that you can move it and position it in different environments. If you want to test it in homes, it needs to be about a person sized, right? Meaning that it can't be like a Boston Dynamics spot, like a really big robot, an industrial robot that makes a lot of noise and damages tables and things like that. It's got to be small and safe and quiet, and it can't be dangerous because like there's people in homes and things like that. So there's all these other, so all of those things are very important in my opinion to be able to deploy. But I'll let these guys talk. I think I've gone on this for a while.
Yeah.
And will.
From my perspective, I think it's beneficial to have like a different like kinds of robot like for like specific kind of tasks. Like for example, in my challenge, like for the Franca robot we're using, I think like its like reach is limited so that it it's not able to reach like objects on like a higher shelf, for example. Yeah, and also I think like based on the like capability of the motor, there are also some like certain tasks like carrying like very heavy stuff that's the current robot like it's not able to. Yeah.
I guess coming from someone who works a lot in simulation recently, I'm personally not attached to any particular robot. I also don't work at a company, so I don't want to sell one necessarily. I personally am of the opinion like in simulation, the biggest use case for it is that you can test any robot basically. If I were to really work on real robots more often, I would opt for one similar to what Chris was talking about, basically one that's safe. That's a big part. I think safety concerns slow down a lot of teleop. Like if I was watching a robot bump in every hour, I would need 1 or 2 engineers monitoring that. That's like $200,000 a year, just paying to look at a robot. So definitely safety is a big concern. And also for embodiment is something that's easy to teleoperate and collect data with. So something really cool about Stretch Robot, for example, is there's a really cool project out of NYU where they get a really simple 2-finger $20 gripper and collect data for that robot. So robots that kind of afford that kind of easy data collection system is something I would be very interested in.
One question for Sam, where are you finding engineers that may take 100K a year?
Oh,
can you point them to ASU? Yeah.
Is another slightly sensitive topic to discuss. So we had this debate about end-to-end models versus modeling. So for your restricted tasks, like based on the submissions that you guys got, what was kind of like a more common trend, given that you have normalized tasks and also very articulated tasks such as like opening and trusting handles and stuff.
Sorry, you said trends about what? Like the models?
The
oh.
submissions were models or more modular. The breaking the normalized tasks into several basic models.
Sure.
Yeah, I feel like it depends on the feasibility of like a data collection and the availability of the data. So if we have a like large like amount of data, like, and the task is relatively like shorter horizon, I think like yeah, it is okay to use the end-to-end like based approach. Yeah, but if it's the other way around, I would like prefer to use the modular like based approach.
Yeah, for our task, end-to-end stuff was just completely infeasible. Did not work at all. Yeah, totally modular.
For our task, I guess we were quite focused on robot learning and more focused on like maybe the modern way of learning, not classical. So we did quite reduce task a lot. So that end-to-end with behavior cloning pre-training plus reinforcement learning did work. No one used motion. Well, I don't really think it makes sense to use motion planning in our sense. But yeah, we designed the challenge to support, neural networks and end-to-end learning effectively.
one other question. So, what would you, throughout your challenges, the types of embodiments you have and the way that you control them differs quite a lot. I guess what is your perspective on the right way to do control? What is the action space we should be giving to our agents, and why torques or velocities or?
So this is actually a pretty important problem because it's something that work in our own lab. We find that when we try to transfer, like really dig deep into the weeds of sim-to-real, choice of, like learning with end effector control. So where you just move so it's just 6 dimensions, rotation, XYZ, delta actions. Super easy to learn, sometimes not easy to transfer. What I mean by this is because a lot of companies have their own internal inverse kinematics solutions, and we found that we can't actually transfer simulation policy sometimes because we don't know what their IK solver is. We ourselves use Pinocchio, but they might be using something else that we don't know. So we find that, sometimes joint position control actually is what you should be using. Another short comment on this is in my own experience, when you do GPU simulation, solving for IK in GPU simulation is so slow to the point that learning with joint position control sometimes just faster. So maybe this is not a debate to begin with anyway, who knows?
So I'm of the opinion that you should probably just provide multiple different interfaces to the robot and have a low-level control stack be able to handle multiple inputs. Like, I think that position is often the best for generalization. I think that there are probably skills where that's not the best representation, but especially as we're focusing on pick and place, like joint position control really made a lot of sense for us.
Yeah, for under challenge, we're mainly using the position based control of the end effector. I think for certain tasks like like the transfer water task, I certainly can see the benefit of using velocity control, like for example, or joint space.
Any audience questions? Not, I'll ask a very related question. So we're talking about action spaces, and so the natural thing to think about next is sort of observation spaces. So there are lots of different ways that we can observe our environment, and we can use tactile sensors. We can use RGB, depth, LiDAR. We can have multiple cameras. So something we did for the Spock project or the Arnold tutorial ones, we use our own sort of mounted camera onto the stretch because we just found the stretch's viewpoint is too narrow to get the generalization we wanted. So yeah, what are your perspectives on the sensors we should be using? And I guess, is this something that you plan to change with future iterations of your project, or your challenge, or your robot?
So at least for ours, we used mostly the sensors that are on the robot, so RGBD, and but we also added SLAM, like basic state post estimates, but for where the robot is, instead of simulating a LiDAR, which you could do instead. I think that having a good SLAM system is kind of a feature of most mobile robots that you can buy these days. So I think it's a reasonable thing to say as part of the observation space.
I also agree very much. Like, I think RGBD, or at minimum, RGB is quite important. I mean, Tesla has shown quite powerfully what you can just do with just only RGB cameras, no LiDAR. I think one, they're cost effective. You can take your iPhone camera too to collect data. That's the main thing. The universal modality for robotics is almost always just vision, whether it's, this is how humans perceive things, robots perceive things almost the same way. And I mean, the other small reason is it's cheap to do in simulation now sometimes.
I think for the Arnold challenge, like right now we're using the 5 RGB cameras around the manipulator. But sometimes I think it's also beneficial to have a third-party view camera for the indoor household environments.
I guess I have one other small comment. I guess if you're coming from doing sim to real, there is still a lot of use case for using ground truth data, particularly with asymmetric training methods. So doing GPU simulation, whatever simulator you use, ultimately there's a lot of interest recently in trying to distill a vision trained policy by using fast state simulation and then take the vision simulation for fine tuning.
I guess on the point of speed and things that are fast, I feel like there have been a few claims today about very high simulation speeds, and both for rendering and physics simulation. So I think we heard some of the highlights in terms of GPU batching and all this, but what were the sort of main insights that y'all might have to generating fast simulators that actually you can train with in parallel?
I guess I can talk about our project to some extent. I think one of the biggest reasons why ManiSkill 3 has such fast art rendering all of a sudden is because we actually upgrade to the GPU state simulation. So that means we transfer state data to our renderer directly on CUDA. No need to move to the CPU memory. So our last year FPS was like maybe 4,000. We just kind of doubled that. Went up to 20,000 now. I think the other thing is, GPU simulation is super cool, but you can't actually GPU simulate everything possible. I'm probably overcame a crap ton, but like there is a lot of caveats that come with GPU simulation. For one, the per thread speed of GPU simulation is slow. So like for example, 16 CPUs, way faster than even 32 GPU threads in some sense. So you have to kind of pick and choose the tasks that you care about. Like if you want to do fluid simulation, yes, they run on GPU, but they're not very fast. So I mean, for the most part though, like for a lot of, like we're still working at pick and place for all things, and GPU simulation is very, very helpful for that. The other caveat that came with developing this new simulator is also that, you had to switch your brain a little bit to write GPU parallelized code. So I had to write all my code in batch, which is, it's like a trade-off you have to make, right? Do I spend more time writing code to be fast, or do I use a simpler CPU variant? Definitely it's a trade-off to think about.
Awesome. I guess in the interest of time, we're getting close to the end, so I want to give you all one chance to maybe say one sentence or around one sentence about what you'd like everybody to take away from your presentations today, and maybe save something for us. But
Probably like need more time to think about it.
Sure. I think you should try out our competition. It's nowhere near solved. I think it's a really challenging and interesting problem, especially since you can try it out in home environments. If it works, you could try it out in your house, for example, which is pretty cool. But
I think another takeaway I like to give away is like, there are a lot of simulators out there. Regardless of which one you use, simulation, I think will end up being very, very important in the future, whether it's for training or evaluation. I, of course, am biased to my own, but honestly, any simulator you use is better than no simulator.
Awesome. Thank you so much. Give one more round of applause to our
We keep this laptop for sure.
I think it should work.
Yeah.
Oh, perfect.
Yeah. Hello. Maybe we.
Oh, actually, I think I have to turn on my sound. Okay. Sharon, can you say something?
Hello, can you hear me?
Yes, it sounds great. Let me let Claudia introduce you. Oh, I think I need to pin your view. One moment.
And you're able to see my slides.
Yes, the slides look good. Let me just, we're figuring out the.
Do this one first and find her here
Uh-huh.
and then ping it. Oh, it has to be done.
Perfect. Okay.
Yeah. Yeah. Hey, Sharon, so you hear us well? Yeah?
Yes, yes.
Excellent. Okay, so we are ready to go. We're on time. Cool. Well, hey, everybody. It's really my pleasure to introduce Sharon Song. She's a faculty at Stanford currently, and she leads the Robotics and Embodied AI Lab, real for sure. I have been following Sharon's work as well as many of you. She has done excellent work on trying to understand what is the right data for robotics, what is the right data mix, as well as learning progress and devices and tools for data collection to also address this problem. She has done some pioneering work on showing to the world what diffusion models can do for robotics, which I've been very excited about. And with that, I'll just give it to her since she has all the time. Please take it away. Thank you so much.
Yeah, thank you so much for the introduction, and very excited to be here. It's a very exciting workshop. I was sitting in a panel discussion. That's all very good points made today. So today in my talk, I'm gonna talk about in the wild robot teaching without in the wild robots. So really kind of getting into the question of how to get the robot data. So to start, let me first show you a robot that I think many of us would like to have in our homes. That is this robot, this dishwashing robot, right? So you can see this robot is able to kind of pick up dishes, wipe off the dirt, and it's also pretty robust. If you add more sauce to the plate, it's able to continue to wipe it until it's fully cleaned. And then by the end of it, it still also remember to close the faucet, and if you open it, it will like close it again. So I think this is if everything is automatic, it's trained a policy. And in case you didn't realize, let me tell you, it is a very challenging task. It's one of the hardest tasks we have done. This has really pushed the boundary for robot capabilities in many fronts, right? So for example, first of all, it's a relatively long horizon task that it has many steps. Each step depends on the success of the previous steps. And also, in order to successfully do this task, the robot needs to perceive and manipulate a complex fluid. For example, the water and ketchup, they have very different dynamics. And then similarly, the robot needs to manipulate like constrained articular objects like this faucet, and also use deformable tools like this deformable sponge. And then finally, the robot also needs to be semantically robust to the concept of like, for example, cleanness. If you add more ketchup on the plates, it needs to understand that I need to continue clean before I end. So all these things I mentioned here is just what makes this task hard and challenging. And if you think about how to like write a program to program this robot to do this task reliably and consistently, it could be quite challenging. So how we can make this system work, right? So the hello idea, or the basic idea, is actually quite simple. It is just learning from demonstrations, right? So just like how you teach your kids to wash dishes at home, but here we just do the same thing with robots. However, while this idea of learning from demonstration is intuitive and simple to think about, actually making it work well in practice is not easy, right? So in fact, if you ever take a robot learning course, the first few lectures will basically tell you behavioral cloning and actually why it doesn't work, or why it won't work well in practice. There are many issues. For example, like the difficulty of modeling complex action distributions, how to collect those data, and then eventually how to make your policy generalized. So today in my talk, I'm gonna touch a little bit on all these three challenges and see how our current system can kind of bypass those challenges. So in a high level, I think there are two technical questions we need to address to make the system work. Right? So first is on the demonstrator side or the teacher side, which is how to demonstrate a new task to the robot effectively and efficiently. And the second is on the robot end, is how to learn from those demonstrated data, so that the robot itself can do the task next time when it encounters a scenario that's slightly different. And then we're gonna look at these two questions one by one. So first is how to demonstrate or how to collect the data. Now, typically in a robotics lab, the most common thing to do is to teleopt your robot for a new task for data collection. Right? So, however, in order to like really have a good and nice setup for teleoperation, that oftentimes requires either like very complicated device, or at the very least, a very well-trained engineer that knows the robot or how to teleopt the robot. And also another challenge, like limitation, is that the data you collected through this interface is often limited to only the lab environment. Right? So if you want your robot to work at your home, it's often very hard. So on the other hand, you can also just show the robot a video of how you washing dishes. However, the robot might have trouble learning from this kind of video because of the big embodiment gap. Right? So for example, your hand is just very different from the robot hand. So instead, what we do is kind of somewhere in the middle, basically using a sensorized handheld gripper that is very similar to the robot gripper, and use that for data collection so that the robot can easily learn from that data. And here is how it works, right? So basically, you can take a pair of this gripper, let's just hold it on your hand, and then do the task that you care about. And on each of the gripper, we add a GoPro camera to record the visual observations during the task execution. And then by tracking the camera poses, you can get the corresponding robot actions in the form of end effector trajectories. And then also on the each side of the gripper, we actually add 2 small mirrors to provide 2 slightly different perspective view so that it can help the robot to kind of help them estimate the 3D depth information without adding additional cameras. So here is how the mirror looks like in the input like fisheye camera. And also this is the view that the robot will see during execution, or this is the input to the policy. And then from this view, you can also see that this is almost no difference between the human demonstration data and also the visual observation the robot will receive. So as a result, it helps us to bridge the embodiment gap. So in the end of the day, all the demonstration data is stored in a single MP4 file that contains all the information needed to train an effective robot policy, right? So for example, those multi-sensory observations and also detailed robot actions. And hopefully we really like this MP4 file is actually something that's really easy to transfer and share. So we really hope that this MP4, like this kind of data collection format, can be a standard and shareable data for robot manipulation in the future. So now we have the demonstration data. The next question is how to learn from this data. So here the robot policy is modeled as a neural network. And the input is a visual observation that is from the GoPro camera, and we wanted to we infer the proper robot actions from the observation. So one of the challenge at this step is to model the action multimodalities or those complex distributions in the action, right? So which means that given the same visual observation, there might be multiple valid actions. So this is actually a very common problem in like human demonstration data, since that there are naturally many different ways to do the same task, right? So for example, in this simple case, I show you if you want to push the T, you actually can go from both the left and the right. And if your policy not able to handle this kind of multimodality, it's very likely to get stuck in the middle, which is pretty bad. So to address this problem, we are making use of one of our earlier work, which is called diffusion policy. So the idea for diffusion policy is actually quite simple. We basically want to use a similar idea for diffusion model for image generation, but now use it for robot action generation, right? So the difference here is that the output space for the diffusion model instead of image is now the action trajectories. And then we can do the diffusion process on the output actions in order to predict robot action. So intuitively, you can think about this whole iterative denoising process as a gradient descent process in the action space, where the predicted gradient fields can have arbitrary number of local minimums. And then each of the local minimum can capture a unique mode, right? So this is why or how by using diffusion model, we are able to capture those multimodalities in the action space. So long story short, by using the same learning algorithm, which is diffusion policy, we are able to train a wide variety of different manipulation skills for different applications, like folding cloths or tossing objects, as long as you can provide the right training data. So for example, if you look at the tossing task, this is actually a task that's really, really hard to tally up if you think about it, even with very expensive tally operation device, because this action requires actually very fast reaction speed and also very smooth actions. However, now anyone without knowing how robot works, as long as you have this gripper, you can teach robot the skills by just demonstrating the tossing action. And then also in this tossing task is where we start to realize that the importance of properly handle the different latencies between the robot's sensory observation and the hardware execution. And so here, for example, is a system that's without handling the latency matching properly. And you can see that the robot will have a lot of jittery behaviors. So this kind of jittery action is probably okay if you care about only pick and place task. It's probably still able to complete the task. However, this jitter action will destroy all the momentum that the robot trying to build up when it's trying to execute this tossing action. And therefore, in this video, you see that all the objects actually have trouble reaching to the desired tossing velocities, and objects actually fall outside the beam. And then by give you another gripper, we can easily kind of extend this system to perform bimanual tasks. So for example, in this video, we are showing how we can demonstrate the cross folding task, which by using 2 grippers, and the robot is also able to learn from this training data. And I think one of the tricky part for like doing bimanual demonstration is that now you cannot actually press the GoPro to start and stop. So we actually use voice command so that you can actually start and stop the data demonstration. Okay, so that's the tasks that we actually select and picked to highlight the difficulties of the task and also highlight the capabilities of the system by showing like what kind of complex tasks we can do with UMI Gripper. So, but then how about in the wild generalization? So I think one of the biggest criticism that people typically have with behavioral cloning policy is that they oftentimes has very limited ability to generalize to unseen scenarios. Right? We all know that a behavioral cloning policy, if you test it with auto distribution scenarios, it's gonna be like it's oftentimes not gonna work well, right? So so far for all the experiments that I have just shown you is what we tested on what we call narrow domain evaluation, which means that the algorithm is pretty much tested on a very similar environment where the training data is collected. So although we varied the initial configuration of the robots or initial positions of the objects, the environment itself is very similar between training and testing. However, now with handheld grippers like UMI, we can really get into many different environments to collect very diverse training data. And what we really hope here is that by using those very diverse training data or collected in many environments, now we can train a policy that's able to generalize to unseen environments that the policy is not originally trained on. Right? So that is really the hope of why we want to build this handheld gripper. So in order to validate this idea of see whether this is true, we test the system on a relatively simple task, which is this cup rearrangement task. So in this task, although it seems simple, but it actually still requires the system to kind of rotate the cup into the right orientation and perform a very precise pick and place. And then you can see in this video, you can easily carry this handheld gripper to many different environments to collect data. Right? So overall, within just 12 person-hour, we are able to collect over 1,400 demonstrations in like 30 different environments for this cup rearrangement task. So basically, the students just carry this gripper with them, go back home, and then whenever they go to a restaurant, before the food is served, they can collect some more data, or at their home, they can collect some data. So that's the data collection process is actually quite easy. And then with all this data, we can train a final policy. And then to test the generalization capability for the policy, we basically drag our robots across Stanford campus and evaluate the policy rollout. So to our surprise, actually a single policy trained with this diverse UMI data is actually able to work out of the box for many unseen environments. Right? So for example, the fountain, like we actually test the robot to do the cup rearrangement task in this fountain setup that is actually not really even a table. We just put the cup and the saucer on the fountain, and the robot still able to perform the task regardless of the water. And then also, oops, okay, can I play this? Yes. So because our system only used a wrist mount camera, so the whole policy only needs one camera and it's wrist mount camera, and then the policy predicts the relative motion. The whole system actually does not require any camera calibration. And then it's also, as a result, it's actually robust to the base movement, right? So in this video, what we are showing here is that you can drag the robot a little bit around, and the robot still able to complete the task despite the base movement. So because of that, I think this UMI setup is also very suitable to be deployed for mobile manipulation as well. So now you can you have seen that the policy can generalize to different environments. But now I think the next few slides, I want to show you to dig one layer deeper and then really ask the question about where does this generalization capability come from, right? So because one thing is that for all the policies that I'm showing you today, all start with some kind of pre-trained visual encoder. So for example, most of the policies are pre-trained with a clip visual encoder, and then we fine-tune it with the data we collected. So there is a possibility that the generalization capability is actually come from the visual encoder, and instead of, so we actually don't really need in the wild action data. So that is the possibility. So in order to really answer that question, we did another experiment where we still use a pre-trained visual encoder, in this case CLIP, but now we actually fine-tune it with with the narrow domain training data, which is the action data collected in the lab environment. And then here is the comparison of the two trained policy with and without the in the wild fine-tuning. Right, so as you can see that the model on the left is the one that's only trained with in the lab narrow domain action data. And then the system actually barely works. It almost cannot finish this task. So I think based on this limited experiment, I think one of the important takeaways here is that, at least for today, I think fine-tuning a large pre-trained vision model with just the narrow domain robot data is actually insufficient for generalization, which means that we still need very diverse action data if you really want your robot to generalize. So just rely on large vision model is not sufficient. Okay, so lastly, I also want to show you, talk a little bit about a slightly different type of generalization, right? So this is generalization instead of two different environments, but actually two different hardware embodiments. So as you can imagine, because of the design that we did for the hardware interface that's only used a wrist mount camera, the system actually, like the data and also the policy can easily generalize to different robot arms, right? So so here I'm actually showing you the same policy that is deployed on the Franca arm and also a smaller ARX arm. So as long as you have the robot arm that you can precisely compute IK solutions and do very good position control, you can directly deploy the same policy. And then also thanks to the in the wild training data, it's the same policy could work almost in any environment with any espresso cups that you can get on Amazon, right? So we actually released the pre-trained weight for this particular task. So you can actually download this weight and then directly deploy it on your robot, and then just buy some cups from Amazon, and it should work. And if it doesn't work, let us know. And then also to take this cross-embodiment idea one step further, we actually recently tested the trained policy on a very different, like drastically different embodiment. That is actually a quadruped with an arm. So here you can see this is a little robot dog with an arm on it. So the difficulty here compared to the earlier example, that's when we're deploying on industrial arms like UR5, is that for like quadrupeds, we actually no longer have a very good controllers or IK solvers to give us a very precise and effective position control. So as a result, we actually need to train a whole body controller to help us to realize those predicted and effective trajectories. But the good thing is that the training for the whole body controller can be done purely in simulation without the need of additional real world training data. And then once you have that whole body controller training simulation, you can actually easily deploy any existing manipulation policy trained on the WUMI framework to a very different embodiment like quadruped. So basically making your manipulation policy mobile. And here so that is the tossing task. And in this video is a whole body pushing task. And then we actually call this system WUMI on legs, which indicates that you can directly put any WUMI policy on a legged robot. So we want to highlight how simple it is. So that's why I think you should probably also try this policy and also the system as on your favorite robots as well. So we actually open source everything, including the code, the hardware, assembly, tutorial, and pre-trained weight. So please check it out and let us know if you have any questions, and we are happy to like see the system running on different robots as well. So if you have a new system running, shoot us an email. That's the end of my talk. Thank you.
Thank you, thank you. Can you hear us?
Yes, I can hear you.
Okay, we'll take some questions from the audience. And by the way, Sharon, I don't know if you can see people from the other camera, but this is a very full room. Like, I'm just standing here. Okay, now we need this for her. Okay, please pause 1 second. Can you see this?
Yes, yes. Hello, everyone.
Okay, there are like 3 rows of people standing. Okay, thank you so much for being here. Okay, so questions from the audience. Go ahead.
I have a little bit trouble hearing the question. Maybe you should come to the front.
We'll repeat it for you. We will repeat it in a second. But please speak up because I don't hear you.
For which uses the vision language model as the starting point. We know that the treatment policy is more attached to the noise. We see security losses and many other properties of the security. While the vision language model part has like common sense knowledge and also the better visual understanding. So what do you think of these two work together? Like how is it going to?
Yeah, correct me if I'm wrong, but I'm gonna pack the question as in, how do you compare your approaches based on diffusion models, which are very robust for noise and multimodal and so on, with sort of kind of another approach in which models are based more on pre-trained models, kind of more what Google is doing. Take a pre-trained model with a lot of semantic knowledge already embedded there, and then keep training from there.
Okay, yeah, I think there are two parts to that question. So first is that I want to clarify our diffusion policy also actually rely on some pre-trained models. So the vision encoder, as I described, also rely on pre-trained large clip models that already kind of have some benefit of pre-trained models. But I think the question is more about what if we do like kind of like more modular based approach that's, for example, use VLMs, LLMs, and to do like motion planning, and in comparison to like diffusion policy directly doing behavior cloning. So I kind of feel these two type of approach, they are kind of handling slightly different parts of the challenge. So for like high level planning and reasoning, those large language models and vision language models are very useful by providing those common sense knowledge. But this like very fine-grained low-level manipulation task, I think that's probably easier to learn directly from behavior cloning. So it's a little bit harder to like squeeze out those action, like very detailed or dexterous manipulation action from those VLMs or LLMs. So that's why maybe I'm pretty sure eventually it will be like combined that you have large language model for planner and then kind of triggered to call those like low-level behavior cloned policies in order to do a very long horizon task. I hope that I answered the question.
Yep, thank you. Go ahead, Arsenal. How do you deal with kinematic differences between the human demos and the robot kinematics embodiment gap?
Yeah, that's a very good question. I get this question quite a lot for Wumi. So I think we have slightly different solutions if you have different robots. So when we just do Wumi like with very good industrial arms like UR5, when we have a really good model for the arm, we have really good IK solvers or controllers for the arm. What we do is basically do a very simple data filtering. So you have the human demonstration data, and you can actually filter the data based on like whether it's a kinematic limit. And you can filter the data if it's not reachable by this particular robot, you can just kind of make those data invalid and then only train on the valid data. However, that approach won't work very well if, for example, once you move to like the quadruplex scenarios where you don't have an IK solver and you don't have a very good controller. So in that case, we actually need to train like a controller ourselves with reinforcement learning simulation. And then in that case, actually the reinforcement learning is trying to reach all the end-effector trajectories that you demonstrate. But of course, there are cases that it cannot reach. And then automatically it will able to learn like what are the data they should learn from. So that is how we right now handle the embodiment difference. And there are indeed cases that human demonstration cannot be realized on the particular robot embodiment.
Yeah, next question. Yep, you were.
Yeah, just a quick one. So regarding the hard drive, the grip on the binary on the closed or the
A couple of things about the gripper for data collection is the open closing binary, or you control the like length of the opening, and what was the other one? Yeah.
Okay, yeah, that's a very good question. I'm so glad you asked. So it's actually binary control is not sufficient. So one of the reasons that's why I can do, for example, tasks like tossing is because we actually track the gripper width, because the opening moment is actually very important and critical. It needs to be very precisely controlled. So we have a QR code on each of the finger so that you can track precisely like the opening width. and then that is also transferred and learned onto the robot. So that information is critical for like a lot of fine-grained manipulation tasks when you cannot just do binary control.
Questions from the audience? One over here.
So about the generalization test, I think that's a good process. But even then, we get like 75% success rate. Whereas with practical applications, you might want something like 95%. So I guess the question is, how do you extend this approach to get accuracy that high?
The question is about the performance that you're getting, success rate, something around 70, 80%. What is the next mile to get that to 90, 99? What do you think is the next approaches for that?
Yeah, I think that's a very good question. And I think if you ask this question to different people, they will have different answers. I'm pretty sure if you ask that question to Cheng, his answer will be like, just collect more data. And actually, I think it's kind of partially true. So for all the examples I show you, especially for those hard tasks, we actually add additional iteration of more data. So for example, for the dishwashing task, we collect the first batch of data and it doesn't work that well, and we actually add more data, it works significantly better. I think that is the beauty of learning-based method is that a lot of times the complexity just gets into like collect more data, and the more data you have, oftentimes the performance will get better. But I guess another question is that how we possibly get the system to work like 99.99% accuracy. I think that's probably require slightly different approach, or like maybe something different than just getting more data. I think right now I don't have a very good answer for that. I think maybe, for example, the system can be doing a little bit of exploration and collecting some more error correction data by itself, or using some reinforcement learning in simulation to help them to like get those the last bit of performance. I think those are like all valid idea, but I don't see one solutions that's really able to like solve all the problems. So I think that is still open research question.
I'll take a quick question from the Slack and then I'll go to you. So one question from the Slack from one of our organizers, Luca. So building generalizable and performant models seem to require training large deep models, which are slow to run inference on. So the question is about the trade-off between sort of well, let me read it because I was trying to summarize too much. Real-time dexterous tasks computation, however, require low latency decision making. So how do we resolve the tension between these two aspects?
Yeah, I think that's, again, it's a like excellent question and something that we're actively thinking about. So right now, diffusion policy is just a flat policy that I think it's actually not fast at all. It's pretty slow because it's using a diffusion process, and we didn't really optimize it for it. But there are a few things that you can make it like okay. So for example, by predicting a trajectory, instead of just next step, you actually can like get away by predicting it slower because you have so many actions that you predicted, you can actually execute it for a while. And however, I do feel like at some point, we probably need a hierarchical policy. So right now, diffusion policy predicts the anti-factor trajectory, and we rely on the robust controller to do the more high rate decision making and actually executing the action or doing the linear interpolation between the action. So that is already like a hierarchical representation. Like diffusion policy is slower, but like more faster controller in the lower level. So I think in the future, once we have like, if we really need to take in like force feedback, if we need to have more fast rate like reaction, it's possible that we probably just make, for example, diffusion policy or like different network architecture that naturally has this hierarchical representation. Some of them is slower, that's able to consume more data, do more common sense reasoning, and another policy that is more reactive, just doing like faster reaction and also control. So I think that is like a pretty natural direction to go.
Great. I think we have more questions in the room, but unfortunately we are right on time, right out of time. So thank you so much, Sharon, for presenting remotely, and thank you.
Thank you. Bye-bye.
All right, we good? Yeah, good. Okay, cool.
Sorry, there's just a little not hearing anything.
Okay. Where? Zoom in the screen.
This is possible. It's fine.
I'm just trying to find it. Okay. All right. All right.
So you heard from him before, and now you hear from me again. We are very lucky today to have Chris Paxton from Hello Robot come to talk to us today. He has been very big in the space of making sure that we have robotic systems able to operate in human environments. He's been working on ways of being able to do using language perception, planning, and policy learning to make robots into general purpose assistants, and is now leading the Embodied AI at Hello Robot to build practical in-home mobile robots. So I look forward to hearing you got to say today.
Thanks. Yeah, hope everyone's not tired of hearing me talk about home robot again, because we're going to hear that a bunch of this. So the general idea is, how can we build? And again, my keyboard isn't working, so that's fine. Yeah. So how can we make robots that are robust, general purpose assistants that work in any environment, right? So particularly, this is what I want for my robot. I have a robot that can go into my house and I can talk to it and have it go and perform any different complex task. It can generalize to different environments, different room layouts, it can do whatever it is that I might ask it to do. And it has to be able to do a wide range of complex tasks. So this is the dream that we want to build towards. And what I'm going to talk about is basically how we can get there. So way that robotics people like me would have gone with this is something called task and motion planning. I don't know how many of you know about this, but basically you would have to know, you'd have to build in all of these kinds of behaviors. You can do really complex stuff like this, but obviously this doesn't quite scale. You have object models, struggles with partial observability, and so on. Of really great imitation learning work, including from what the talk that we just saw. One of the issues that we still see with this is generalizing to different environments and different settings, and being able to capture really wide ranges of different tasks, preferences, etc. So we need solutions that allow as well to different environments. Robots embodiments can perform different tasks, different types of manipulation, whether it's dexterous manipulation or being able to do navigation, exploration, and so on. So I'm going to talk a little bit about different solutions that we have for this, and why I believe this is possible, that we can in fact do generalizable robot autonomy in homes and in a wide range of different environments using current techniques and so on. In particular, I think one thing that I like to note is that for a lot of the videos and stuff that I'm going to show and stuff that I'm going to talk about, is that we really have this strong assumption that we really care about generalization. We want to deal with objects that we haven't seen before, instances we haven't seen before, lots of different tasks and so on. The other thing that I'm going to talk about, of course, is home robots. So how do we know whether or not when these things work? How can we assess this? How can we share code? How can we make sure that we can actually have these kinds of systems and deploy them at scale in the real world? And finally, we have the robot itself that we're going to talk about. So this is Stretch 3. So it's a very simple. This is the robot that I'm going to use a lot of, especially later on. And I want to talk about why we're going to do this. So particularly, there are a lot of different types of robots out there. Like there's all the humanoid robots, there's mobile manipulators, like dogs. But we really care about this being like portable, lightweight, easy to deploy in different environments, and safe to use around people, because that's what we're going to be doing. We're going to be I'm going to be running experiments in my home and in other people's homes and so on. So all of these things matter quite a bit. We have a low cost robot that we have for this. So particularly the problems that we need to address to be able to build robots like this that we can deploy into homes is that we want robots that can navigate and represent scenes, so we can answer questions about them. We can move to open vocabulary goals. Like if I ask it to cook something or get me food, it needs to know to move to the right cabinet and open it up. It should capture semantic knowledge about the scene and the purpose of things in the environment. We need to be able to manipulate objects, perform multi-step manipulation tasks on unseen objects in unstructured environments. So I don't know what I've encountered yet. I need to be able to perform. I might want to set the table or stack a bunch of boxes or something like this. All of those kinds of tasks have to be in scope. And of course we'll talk about benchmarking and bringing it all together and actually deploying it in real environments. And again, generalization is really important to us because we need to be able to scale to homes and to a wide variety of environments. And your home is different from mine and so on. And we're not looking at lab kind of environments as much as possible. So first of all, I'm going to kind of quickly go through a bunch of different sort of like how techniques that we can that show us that we can actually kind of do these kinds of things, at least to some extent now, and that we should really be assessing on these open vocabulary kind of tasks where we have different kinds of objects and different requirements and things like that. So with navigation, so this is open vocabulary. We want a robot that can follow, to which we can give high-level instructions. Go to the bookshelf, help me clean up the trash. So we need to be able to capture some knowledge of the world in our robots in a way that they can use it. So the question is really then, how do we learn and build like useful representations? So we go with these kinds of spatially organized representations in a lot of this work. So I can either walk around my house with an iPhone, or I can have a robot explore it automatically, and then I can detect objects, and I can take in and I can build up a semantic representation out of off-the-shelf features. So in a lot of this work, we're going to assume we have 3D depth sensors so that we can capture structured representations of the world. But these representations are populated with open vocabulary features from things like Clip or Dino that we can so that we can actually make open vocabulary queries. So if I get a 3D representation like this from having my robot explore or whatever it is on the left, then I can if it's populated with Clip features, in this particular work is called Clip fields, then I can ask it for something like more about my lunch, and I can see an activation potential on top of the microwave there, which is where the robot should go to next. And so these kinds of techniques, they're inherently modular because we have these spatially organized kind of representations which tell us sort of spatially where the robot should go, where it can plan to. But now it can start to do like compound reasoning. But I can also have it I can ask it a wide variety of different questions, having it go and wash my dishes. These representations, we can train it to capture sign distance fields, so we can do object avoidance and motion planning on top of this, so we can get lots more robustness than we would get just from training end-to-end policies. In addition, we can use similar set of ideas as far as spatially abstracting out some of this for generalizable object manipulation. So given a point cloud description of a goal, I want to be able to tell it something like put the boxes in a line or set the table. If I give these kinds of language instructions to my robot, then it can do is that we can train models so that it can predict basically where these things should move in the world. So like this plate should go in this direction, instead of explicitly training like end joint state positions or end effector velocities or whatever it is. If we express things in this way, it generalizes really well. And again, we can all these experiments that are showing it wasn't trained on these particular objects or on these particular scenes and so on, and it can do these fairly long horizon tasks just from language instruction. Once we move on from that, we have to. So now I've got basically the tools that I need to be able to take that robot and have it perform long horizon tasks, but I still really want to be able to capture user preferences and common sense knowledge and so on. It would be great to just be able to throw this all into GPT and ask it what to do. These models. So once we can do that, we can use these to be able, together with different algorithms for planning, to be able to reconstruct user preferences and predict things like if I show it a bunch of pictures, I can then have it sort of assemble different structures based on what my preferences are. And we also see that GPT is really useful in these kinds of cases because it can capture all the semantic information about like kind of how objects relate to each other. And that means that when I take this robot, I can have it perform multi-step planning, as long as it gives us. GPT may give us a bunch of contradictory information that prevents it from being reliable enough for a robot. But once we put it into those kinds of planning stacks, then we can actually start to get real executable task in motion, like full plans, or that let us solve very complex tasks. All right, so that was a whole lot of different things at a very high level. But my point is that the point of saying this, now that we're about halfway through the time, is that we basically have this kind of recipe that lets us perform long horizon open vocabulary object manipulation in a wide range of environments. And yeah, these aren't like the smoothest and most beautiful possible actions that we can do, but things like tools like GPT, OpenAI Clip, and so on, basically all of these foundation models that you've heard so much about today and yesterday and so on, actually do give us enough information that we can start to deploy robots in real environments on real kind of open tasks. And so now what we're going to talk about for the remainder of the time is basically like what goes into actually benchmarking this and trying to deploy these systems and get them to work well. So that's where we can get back to Home Robot, which you already heard something about. So I'm going to go into a little bit more detail of what that is and what the thought process. So
So instead of doing geometric arrangement like we used to, we want to do this open vocabulary task. So instead of so I'm going to say something like pick up the box from the table and place it on the sofa. Great. So the reason we set it up this way is that we really care about. I want to in your home. There's a very wide range of different objects that you might want to be able to pick up and manipulate. You cannot assume that you've seen this in the training data at all. A lot of the issue is that the difficulty in this comes from the intersection between perception and manipulation and planning, because I need to be able to explore my environment and find the objects that I care about. So we're really pushing on, like, we should test on objects you do not know what objects we're going to deal with. In particular, when we put this together, we wanted to come up with an embodied AI benchmark, which had continuous action space, was deployable on real robots easily, that we could that was solving a meaningful problem that looked like one that you might actually want to do in your house. Because, for example, this open vocabulary task may sound a little weird to you, but if you think about something like setting the table or cleaning up the dishes or whatever, it really is just a sequence of these open vocabulary manipulation tasks. Right. So this is a very foundational piece that allows us to do a lot of really cool things if we can get it to work well in homes. And that's the real question. Can we get it to work? And so so we set up our challenge or our competition to have two different benchmarks. One is a simulation, one is a real world benchmark. We have a lot of different environments in simulation. The environments are created using we'll get into that later, but we have 150 different categories of object, about 8,000 different instances, et cetera. So it's a fairly large data set, not the largest that I'm sure you've seen, but it's reasonably big. Created using open object data sets, so licensing is all good, and you can train it if you want to. So four different parts to the task that you get scored for. So finding the object, picking up the target object, which is a target object on a particular goal receptacle. This goal receptacle, the start receptacle part, is to kind of give it a hint as to where it should explore first, because you can put something anywhere in your home, and it might take a really long time if I have a really large multi-room home, and we'll get to that in a second. And then you've got to move it to a goal receptacle and place it on it. This is starting from this. So these are what the simulation environments we have look like. So these are all from the Habitat Synthetic Scenes data set. The nice thing about these is that they were all created by actual humans. They aren't procedurally generated, which means that they actually look pretty weird in some cases, but there's actually some human thought this was really what a house should look like. They were using this like home design authoring tool to do this. So we end up with so we have a lot of different environments like this, but they're all multi-room environments. They're big. There's lots of clutter and distractors and things like that. So in simulation, so this is kind of what the simulation looks like. There's a bunch of different examples here of the robot moving around. So a robot, again, roughly human size, so it can move into all kinds of different kind of small areas to go and find objects. The objects themselves are all small. They're all like roughly the size of your hand, because they can be picked up very easily by a 2-finger gripper, which means that in a house like this, there's a lot of room to explore. You've got to really move around through these very large areas to find the correct object. You also need to move close enough to receptacles that may have the object on them to explore them, and that makes it a pretty challenging task. So here we go. So we provide different baselines for implementing this. One of them is this modular kind of motion planning based baseline that still is running an open vocabulary object detector, of course. So you can't do this without machine learning. But there is a case where that's basically all that there is. Otherwise, we do a bunch of reinforcement learning benchmarks. Which one's better kind of goes back and forth. But in our benchmarks, usually the reinforcement learning ones are better. The leaderboard, as we'll get to, and if you heard the talk earlier, the heuristic ones tend to be better. But so what happens here? So you can see on the right, it's as it sort of the exploration process, as it has to like move through this environment and kind of build this semantic map. Find the different start receptacles the objects might be on, find the goal receptacle, and then it has to actually find and move to and grasp this object, right? So challenging task, long horizon task. And then we tested it out in this real apartment in Fremont, California, which is owned by Meta. This is a fairly large test apartment with 3 different rooms. There's a kitchen, kind of a living area. There's a bedroom, an office, and so no real world training, no maps or real world training data were provided. So we have the robot has to go around and pick up these different objects. And this competition at Neuros, with the prize being to give away a free robot. So we got a lot of different people trying to participate. 21 ended up actually submitting. A lot of people registered. So we had 80 to almost 80 to 79 total submissions. We end up seeing the success rates were about 10%. This was on a previous version of Sim 4, so the numbers are a little bit different here, but yeah, evaluating on these 10 held out scenes again. So the scenes that it's evaluated on have different objects that aren't seen in the test. So the way the evaluation is set up, it's totally agnostic to whether it's being evaluated in simulation or on the real world. So we set up this kind of Docker framework for being able to pull and download people's code, and you can test it out on the robot, which means that we could you run the robot system and it sends over all the observations. So once we've agreed what the observations are, you can try out these different methods very quickly. I really like this as a framework because it allows us to test, allows us to like share and test code very quickly on different robots. So when we evaluated the top 3 teams, we saw that 2 out of 3 of them were based on these motion planning benchmarks. So I'll show this is one of the successful episode. So we had when evaluating the real world it's a feasible thing to do. You can test this stuff out. You can test other people's code in the real world, which on this robot without their involvement on these fairly challenging tasks, which I think was more work than it sounds like maybe. And it was nice to be able to show that we could actually do this. So basically, we can actually benchmark real world mobile manipulation. It's possible. We should do it more. It's hard to say which methods are the most promising because we really saw things go back and forth here. Like in the first versions, it was reinforcement learning was better. In the competition, it was these modular motion planning kind of stuff was much better. And so these open challenges based on in this were all based on things like perception and robustness, in particular the things like error recovery and detecting objects and making sure that like if you get near something and it drops it, what do you do? If you get near something and then lose track of it for whatever reason, like maybe because the angle changed and now your detector's failing, like that was a huge cause of failure here. And so these are the kinds of things we're bringing together. More end-to-end type of solutions might do better, but as I said earlier, end-to-end training was not very tractable in this problem, so there's a whole bunch of other issues there to resolve. And so the next thing we did so after that, we have been since deploying robots into actual homes, doing this stuff called OK Robot. So it simplified the exploration part to save time, but you can now do vocabulary pick and place like this. So we have robot that can move to like pick up a purple light bulb box and move it to a sofa chair and so on. So moving around all these different real home environments, doing pick and place again. So generally, again, success rate's not great. In these kinds of cases, we see like 50-60% success rate, tested in a lot of different homes. The nice thing about it is that we can have these robots that deal with like home environments, like real home environments. If you take those, they often tend to be like very complex, lots of distractors. Perception models can fail. This is why these problems tend to be with like dealing with unusual objects, clutter, distractors, avoiding obstacles, grasping and manipulating reliably. So there's lots of cool challenges, but again, I think the important thing is that these are feasible things to do. You can in fact test in these real home environments, and probably we should be doing more of it and less of it in laboratories, because like there's something to be said for like this is just the robot running in my home. It's a little messy, so so you can do this, and there's something magical about having the robot like pick stuff up and move around in your own home, which I feel like is kind of the dream, right? So in the future, is stuff like you can do dexterous skills. So this is examples of using the robot to do dexterous teleoperation and data collection. So we can start to train policies that are actually very complex using very simple low-cost hardware. So really, I would say like hardware is not the limitation. It really seems like it is learning and generalization. In general, really always going to say generalization, right? And the other nice thing is working with people. So in this case, this is like an example of bringing someone a snack. This is the kind of thing that we really want to have the robot able to do is like, can I talk to it and have it go and move to different locations, go pick up some food on a tray so it's not too hard to grasp and bring it over to this person. Also teleoperated, of course. Yeah. I think we're at a really exciting place. Generalization and robustness are like really basically the going concerns. We can start to do more evaluations in the real world on long horizon tasks. And we're at a really exciting place in robotics in general. I think that there's a lot to do. I hope that people can try out this challenge and do better than we did. Just like there's still clearly a lot of ground to cover. And thank you.
So time for just a handful of questions. So
yeah, are there any plans or ongoing research that use the have informed stretch where appropriately grasp something.
Where, like, which part to grasp? Did you have to? Oh. Yeah, I think that's it. So, so the question is there any research on using open vocabulary models to grasp like particular parts of objects? So, not that I'm doing or involved in, but I do know people are working on this. I think it is a really cool problem. Like, it is clearly an important one. Yeah. So.
I was curious to know, a lot today we were kind of discussing different types of embodiments, like different types of systems. And I'm curious more kind of like the AMR autonomous mobile system you guys have kind of developed. And also your thoughts or perspectives around like we're seeing a lot with different types of humanoids and different types, and then there's spots, there's different embodiments, and I'm curious on kind of from Hello Robot on the Stretch 3.
Yeah.
And also your thoughts on other systems. And I know it's dependent on different use cases.
Right. So I think so the question is basically from my thoughts on different types of embodiments, like this robot versus like humanoids and dogs and so on. So I think that because I am fairly convinced that the like based on these dexterous teleoperation videos that I shared, like I don't think that the limiting factor is the embodiment, right? I think that the thing stopping a robot from being in your home is not that we need a cooler robot. I think it's that we need AI to work. And that means that what we really need is robots that you can deploy and test a lot of interesting stuff with. And that's part of why I'm a fan of this particular platform, because it's like relatively low cost. Lots of people have it, which means that I hope that we can share more code and models and data from the robots. And that means that we can do lots more experiments. And really that's what's going to like data in the real world is, in my opinion, a very large part of what's going to solve this going forward. But yeah, of course, all those platforms do have huge advantages in certain ways. Like I think everything is suitable for different things. Yeah.
You talk about like evaluating most simulation as well. So I'm curious, first, if the model is performing better in simulation, does that first off? Does it perform also well better in the real world? And the second is if that's not the case, like how do we bridge this gap with the metric that tests both or do we make it better?
Yeah, so that's a really good question. So the order in between sim and real was exactly the same actually in terms of like which team did well. Like the rankings that didn't change. Which so it sounds like I should probably say that simulation is good enough, but I actually am going to say that no, it's not. And I thought that was just chance personally. I think we really do need lots of real world evaluation to drive these kinds of things forward. The simulation in particular, there's a lot of shortcomings of simulations. They're good at different things, in my opinion. So the real world is still irreplaceable, in my opinion. But you do need simulations. Yeah.
Why first of video? Why does two-finger graph instead of 5 fingers? Hands, fingers.
So cost and robustness are big things, right? So like if the robot's moving around, so the nice thing about that gripper is it is fairly reliable and compliant. I think that a two-finger gripper can do tons of different tasks. Like and Sharon was just showing all the videos of two-finger grippers doing things. I think two-finger grippers work well. They're also mechanically simpler. They break less, right? It's lightweight. It's things like that.
When you shoot lava,
yeah,
the human most likely to walk into like other so basically, is the best way to get directed because they don't know. We then visualize every actions like our hand and just do their normal work all the different time.
Yeah, so the question is about whether or not like we should just be using human hands because we can just like take human data. I think this is a much longer discussion that I feel like I probably don't have time for. But I think that's an interesting point. But I actually think you can do this with two-finger grippers too for a lot of different tasks. I think there's some good work from CMU that I'm not involved in, but that basically tracked human motions through the environment and is able to use those to train robot policies on these robots and other robots. So I think this is a good point. I don't think that it means that you have to use human hands, personally.
Yeah, so you guys like have shown there was a timeline in framework provided that had these different stages. Some of them included RL, and you mentioned that there's like a efficient means, which was better, either an RL-based like solution or the heuristic-based solution that submitted to the challenge. But I noticed that like you kind of have broken things down into like a traditional robotic stack, like you perceive and then plan. Yeah.
Yes.
How do you see like that comparing to what people are trying to now with for end approaches that's making straight capture, which you.
So I think that this question. Oh, sorry. So the question is, so we had this very modular stack with like sort of a pipeline set of skills where some were RL. And by the way, the ones that were RL were either RL or heuristic. There were some that did not, that RL training in the simulator was not really feasible for various reasons. Those were just, yeah. But so the question is, so we had this fairly traditional robotic stack where you perceive and then act, right? And so the reason that we went with that partly is because we really were not able to train things end to end and get these kinds of generalization on these tasks yet. I think one thing that you can do if you do this division is that you can train models that do just the perception part based on web scale data, and that's what these open vocabulary object detectors can do really well. So I can take an open vocabulary detector like ALVIT or DEDIC or LangSam or whatever it is, and I can run that, and that is kind of its own problem, and it works really well. And then like I can use the outputs of those to parameterize skills downstream, and that makes everything more robust. I think that in the long run, it seems like end-to-end should be the right solution because you don't have to have all these different components. But I am of the opinion that we need to get this data flywheel turning and get robots out there, and that means getting robots to work, however, whatever it takes.
We do have one more question that has been really short.
Safety. I think you are the only one who talk about safety. And in all the simulation we've seen today, we saw a lot of holes with no humans, even if the purpose is to help humans. So I was wondering.
So to be fair,
Say something. Testing, can you hear me from Zoom?
Okay. And then one thing it's not showing there. I don't know if you have to mirror the screen or.
Sounds good. Yes. Great.
All right.
right, so, and then this is for the rest of the room. Hey, everyone. I want to welcome Eric Zhang, who's a former colleague from Google, now at 1X. At Google, you can always count on Eric to have a very thoughtful approach to problems, and he's also the author of the recent book, AI is Good for You. So please take it away.
Great, thank you. And thanks everyone for coming here. I'm really excited to see such an interested audience. So today I'm going to talk about a new effort we're doing at 1X called the World Modeling Challenge. And this is fresh content, so you're the first to hear it. So a little bit about me. I've done, prior to joining 1X in 2022, I did a bunch of research on visual robotic manipulation at Google. Here are some of the projects I've worked on. And basically, I'm a big believer in end-to-end vision to action policies for robots. Sort of after doing this work, I came to the realization that the bottleneck, in my view, was actually hardware, not the algorithms. So I kind of wanted to work on humanoids after that. A bit about 1X. So it's a humanoid robot company founded in 2015 in Norway. And as of today, we're actually dual headquartered in both Moss, Norway, as well as Sunnyvale, California. The company is about 120 people, and the AI team that I lead in Sunnyvale is about 15 people. So a bit about the AI stack as we have it today. We're always iterating on it, but the current instantiation is this kind of decomposition of a high-level planner with a low-level end-to-end policies. So you can imagine if you want the robot to go over to the window and open the window, you'll have this text prompt that says, go to the window. It triggers a particular model that is responsible for driving to the window. Then you might switch the task and say, like, open the window, and then triggers maybe the same neural net or a different neural net to open the window. And so we do low-level dexterous planning with just end-to-end methods that just do imitation learning. They predict 10 hertz actions from raw sensor data. And the high-level stuff currently is sort of human-driven, where the humans just enunciates the task into the like a smartphone app. But we expect that we should be able to automate this quite soon with the VLM.
Are you sharing your screen?
Yeah.
Okay, so is this
oh yeah, sorry. I think Zoom I should share it. Yeah. Okay. Can the folks on Zoom see this? Great.
Yes.
Awesome. So just to give a sense of like what this is able to accomplish, here's a recent video that we put out on the 1X social media channels, showcasing basically this architecture of using voice commands to chain a bunch of tasks to do things autonomously. Everything you see in this one-take video is basically autonomously controlled by a neural network, except for the task switching part. So a human is basically dictating remotely which task it should do. And again, it's not a huge leap of imagination that with the progress in VLMs, we should be able to have the data collection on what humans are seeing and saying, and be part of the imitation learning process as well. So I'll just let this video complete. Basically, there's a lot of kind of contact-rich tasks that we can do, like wiping tables, picking things off the floor, pushing in chairs. The bots are pretty strong. Opening doors, and so forth. And on the bottom right, you see the text commands that we're actually sending to the robot in this video. Some cups were harmed in the making of this video. Cool. So the video ends basically with a door opening task, and so that's kind of like what we're able to do with our current autonomy stack. So let me move on, and I'm going to actually motivate the focus of this talk not by what we're doing on autonomy, but actually a strange experiment that we ran into recently. So for people who are in NLP and vision, it's very common to have this kind of expectation of a scaling law, where if you add compute, you scale up the parameters in your transformer, or you add more data, this basically almost guarantees performance improvement if you're kind of doing the right scaling and hyperparameter search. So for example, let's take one of our dexterous low-level models that we're training in the previous video, and let's just try scaling it up, right? So what do we expect to see? Well, if this tracks things in computer vision and NLP, what we should expect to see is that as we go from like a 10 million parameter model to 100 to a billion to 10 billion, we should see this progressive decrease in training loss for the model, indicating that we're fitting the data better and better. So what do we actually see? This is just like an experiment we ran about a month ago. We see something like this, where the losses all kind of go to the same place, which is extremely disappointing, right? So maybe to people who are in LLMs, this is actually really odd, but a lot of people in robotics frequently run into this problem. And these are often negative results that are never published. So I was trying to look on the literature for like instances where this happens. And I'm pretty sure like every robotics imitation learning person has run into this in their TensorBoard or WANDB at some point, but it's shockingly like rare to see this kind of published. So what's going on here, right? Well, I dug up a few results from the literature suggesting that sometimes more parameters is not always better. So there's a few works from the Rail Lab at Berkeley showing recently that, for example, in the Octo paper, the 93 million parameter Octo model outperforms the 55 billion parameter RT2X model. Similarly, the SUSY model, which is like an image goal condition paper, also does that with a much smaller model. And then recently, there's this open VLA paper that also gets outperforms RT2X with a 7 billion parameter model. Similarly, there's other papers that show that more data is not always better. So the Droid data set recently also shows that despite being a smaller data set in total size, it also outperforms training on the compared to the OXC data set, which was the paper that kind of got co-released with RT2X. And then another paper from CMU shows that in terms of the foundation model pre-training, you don't necessarily always get automatically better performance when you pre-train on a foundation model that was trained on a lot more data. So it turns out that ImageNet is actually a surprisingly strong baseline compared to things like Ego4D and so forth. So there are these weird negative results in robotic scaling that kind of defy the intuition of where scaling should go, which is very concerning because a lot of people who are trying to solve general purpose robotics want to actually scale things up. And if things don't just get better automatically, then it's pretty risky to do that. So here's a few hypotheses on why this might be happening. The first reason, and I think this is a significant one, is just that real world evaluation is just fundamentally very hard to reproduce. Many robotics labs cannot reproduce other robotics labs' work. So it's just very hard to measure the effect of scaling. There's also a data freshness confounder. This one is particularly scary to me, which is that if you, let's say, collect data on Sunday, you train a 100 million parameter model on Monday, you evaluate the model on Monday as well, and then you train, in the meantime, you're training 1 billion parameter model. On Friday, you evaluate the 1 billion parameter model in the real world. It's going to be almost automatically worse just because it's Friday. And Friday is like far away from Sunday when you collected the data and the world has changed. So this bias in evaluation is very, very pernicious in pretty much every robot learning paper. And if you're evaluating your tasks on like different days, there's already going to be this like default regression in performance. Another one that's potentially suspicious is that if we look at LLMs and VLMs, they're often trained with a cross entropy loss, whether it's some sort of mass token prediction or next token prediction, whereas a lot of robotics models tend to regress some sort of geometric thing like mean squared error of a 6-stop pose or some sort of loss like that. So maybe there's something going on there with some scaling bottleneck. Relatedly, maybe there's a lot of bottlenecks in robotics that restrict parameter efficiency. So maybe you have this cute idea to improve the sample efficiency of your robot model, and it helps at some scale, but as you increase the scale of data, maybe it actually has worse gradient flow compared to just a big transformer. And then therefore, maybe your earlier layers suffer more if you're scaling up the parameter size from this bottleneck. One example of this is that pre-transformer in NLP and vision, it was actually very common to see this effect where scaling up the model didn't automatically make things better. And this was the case with a lot of RNN-based architectures. Another way that, for example, you might see the bottleneck happen is that with an MSC model, it basically regresses one mode. So potentially if, let's say, the other parameters that you're adding to the model would let you learn more modes, the MSC loss is kind of preventing you from learning the modes even as you're adding parameters. So there are these ways in which maybe these architectural decisions in robotics can actually prevent your ability to get improved performance as you scale things up. Another hypothesis is that a lot of these baselines showing that smaller models or smaller data is working better is that maybe the RT2X 55 billion model was just very undertrained with respect to the actual test domain that was evaluated on, because it's a very big, very big model with a big data set. And maybe similarly, there's kind of suboptimal data cleaning in the OXE data set as well. So when people talk about like how does scaling laws work in robotics, I guess it's also sort of unknown how we count data in robotics. In language modeling, we just count tokens, but it's not clear what the equivalent of a token is in robotics. Is it just like per demonstration? Is it like the sort of log base 2 of your action space and then times the number of seconds of actions you have? Do you count the image tokens? These kind of questions are still unanswered in robotic scale. And so it's maybe very possible that like robotic data is sort of overcounted in terms of its data size, because maybe the sort of interestingness of the data is not as compressed compared to entropy, which sort of encapsulates all of human knowledge. I'm sorry, compared to language, which encapsulates all of human knowledge. And another way to express this is that maybe the robotic task itself is not hard enough to require that many parameters in data. So if the effective data size of robotics data sets are actually really, really small, then you don't actually want to have that many parameters and that much compute. And so let's talk a little bit about tasks. So what is a task in robotics? Oh, I'm sorry. Let me talk a little bit about evaluation first. So in robotics, if you're running evaluations in the real world, getting statistical certainty on your evaluation is very tough, because the number of trials you have to run to estimate something like a binomial success rate is very large. So the standard error of a binomial variable is basically square root of the mean times 1 minus the mean divided by the number of samples. So if you want to get within, let's say, 10% of your true success rate, you have to take like 300 samples. And then similarly, if you want to go to within 3%, you have to take 3,000 samples. And this is very bad because it goes up quadratically because of the square root term here. So evaluating how good a robot model is, if you don't know anything about the black box that is the policy, is extremely expensive. In fact, all robotics papers today don't really evaluate with the level of rigor needed to actually know for certain whether an idea is good or not. And this is further confounded by the fact that like if you have, if you're trying to get 3,000 trials, you're not going to really be able to evaluate this in one day. And so then when you evaluate something the next day, you have to then deal with the bias of the environment changing. So the evaluation is a very tough problem. Okay, back to tasks. Why do language models benefit from scaling laws? Well, you can think about a language model as actually not just modeling the next token, which it is, but what it's really doing is jointly predicting many, many tasks at the same time. So if your context window in a language model or transformer is like 2048, you're effectively on every single forward and backward pass predicting 2048 different tasks, for which each token that you're predicting can be its own unique task. Let me give a specific example here. Suppose you're trying to model like a mystery novel, and the novel kind of has a token sequence that begins like, the novel is the beginning, and then person A does this, and then person B does that, person C does this, A says this, B saw C, C says to B. So, it's just a very standard kind of linear narrative in a book. Let's suppose we're constructing an LLM task where we're just predicting only A's behavior. So we're only going to care about what person A does in the book. And we're going to learn this probability distribution, P of whatever A is doing, given what A previously did, and then also condition on all the data that you see in the novel, right? So what you end up learning here is that you can get information, you only improve your performance on what A is doing based on A's interaction with other characters and relevant data in the corpus. If you get some data from, let's say, B interacting with C, it's very unlikely that it helps you actually improve your predictions of what A is going to do next. And so if you think about the corpus as being all kinds of characters doing all sorts of things, any given random data element is actually going to not really help you predict what A is going to do next. Conversely, if you predict everything together, then basically any data element you're predicting is going to help some task somewhere in the data set. So there's this nice design of LLMs where almost all data helps some task in one way or the other, because you're trying to predict every token. And I think that's why we see very slow data scaling when it comes to just scaling up action data in robotics, is that if you are only trying to predict scaling with respect to the prediction of one variable, then most of the data in your corpus is actually not going to help you learn that variable because it's only useful for learning the sort of conditional distribution on other data points. So we can basically rewrite this language analogy directly into the language of robot actions. So imagine instead of character A, we just say A is the actions, and the behavior of all other characters is all the other non-action tokens in your sequence, right? So let's consider this very simplified control example where you have an image and you're trying to make decisions from the image. The image is tokenized into a 4x4 set of tokens. So you have like 16 vision tokens. They go into your policy, you generate one action token. They go into your world model, you get your next state, right? If you're just trying to predict the actions, then seeing data points from x0 and x1, the relationship between those two variables may not actually give you that much information on how you improve your predictions of A0. So let's try predicting everything that there is to know, just like in LLMs, right? So if we flatten the data into a one-dimensional sequence and we just predict this language model style, then we have basically this sequence that goes from all your image patch tokens to your action, and then you repeat this for every step in your episode. To use like a Jan LeCun cake analogy, basically most of the data in your data set is cake. Very little data is the sort of supervised action, and even less data is the final terminal success criteria. So let's just ignore the reward for now, because let's consider a simple imitation learning case. But if you're trying to learn to predict the frosting, most of the data in the cake is not really going to help you to do that. If you're trying to predict everything from the cake to the frosting to the cherry, then any arbitrary random piece of data that you sample is likely going to help you predict something, which is why I believe we see better scaling laws in VLMs and LLMs, because we're fundamentally trying to predict every quantity. And so the sheer number of tasks allows you to see this kind of benefit of adding incremental amounts of data. So I'm going to then start to motivate why we might want to do world models where we predict everything for robotics. But first, to set a precedent, there's already quite a few works where we're seeing like AV companies doing this. Wave is pioneering quite a lot of this sort of photoreal image generation, where they can even try to evaluate and check counterfactuals in their sort of world model. Wabi has done some interesting work in a sort of different space. And recently, Comma had a tweet from their CTO saying that they're training their policies now and on policy with a learned world model. So there's definitely now this idea in the air that like maybe it's time to actually apply world models to self-driving cars. So basically, I'm going to announce it's already public as of today, the 1x World Model Challenge. And so this is basically our attempt to focus the community on an interesting problem that we think is now ready for general purpose robotics. It comprises of 3 different sub-challenges: the compression challenge, the sampling challenge, and the evaluation challenge, which I'll describe now. So why are we hosting a challenge? There's already a lot of like interesting benchmarks for general purpose robotics, but I think I have a pretty different angle on it that's kind of not satisfied by current evaluation benchmarks. So we think that video generation models have improved enough that it soon may be possible to actually do end-to-end hallucinated evaluation and potentially even training of millions of different tasks in a learned world model. So no more painstaking simulation engineering. You don't have to go and measure the spring constant of your door and then implement that in your door. You don't have to figure out how to do deformable cloth simulation. You don't have to figure out how to simulate people. Maybe it's going to be possible quite soon that we just put this all into a Sora type model and then be able to just roll out these learned hallucinations to evaluate our robot policies. And this would basically solve the general purpose robotic evaluation problem. If we're able to definitively measure and compare policies in the simulator, then you don't have to worry about resets and going from Friday to Monday and having the environment regress. So we think that if this evaluation problem is solved, it would greatly accelerate the progress of general purpose humanoid robotics and be able to get these into the home very quickly. One more thing that I believe is that the set of people who are qualified to help is now much larger than the set of academic researchers. So we are less interested in a benchmark that is published in papers and more interested in a sort of public prize competition. And we're very much inspired by efforts like the Scroll Prize and Comma VQ. So this is why we're doing it. We think it's very possible that in the near future we can solve the general purpose evaluation problem with training on real data. And why is this evaluation problem important? Well, I think in order to see scaling in robotics, you need to have many, many tasks. I don't think it's sufficient to have a benchmark that has like 50 manipulation tasks, and then you try to use that to estimate what techniques to use. Because of the sheer number of tasks needed to measure a scaling law with respect to data, at least that's the hypothesis, then it seems like in order to actually see a effect from scaling, you actually need to evaluate on millions of tasks. So if we're also going to make a big investment in data collection and compute, as we are in 1x, then we need a predictable way to see how money spent correlates with the capability increase. It's very scary to not know that, and so we're trying to figure this out. And finally, if there is a learning algorithm that has a scaling bottleneck, it's very useful to know this because if it cannot get better predictably by scaling up compute and data, it will never be a candidate for large-scale generalist policies, at least of the kind of investment spend that you see that like big players like Google DeepMind and OpenAI do when they're making their generalist models. So a little bit about the challenge. It's still a work in progress. We're trying to iterate on the community with the community on this because it's hard to get the metric right exactly the first time. But I'll give a high-level description of like what the core tasks in the challenge are. So you can already see the challenge on this GitHub page here. Basically, we're releasing a data set of 100 hours of tokenized images from Eve's collecting many tasks in our offices. So this is like pretty much every kind of manipulation task that you can think of. With a lot of like deformable object manipulation, bimanual manipulation, pretty much everything. The tokenized images are 20 by 20 with a codebook size of 1,000. We think we can actually make this a bit more compressed, but we were trying to trade off the sort of making sure we're not discarding too many semantics of the tokenizer and making sure that it kind of is a somewhat general image patch representation. Although in the future, we might look into kind of releasing maybe a different data set with a more aggressive tokenizer. We're also releasing the raw actions, basically the joint angles, the wheel velocities, and the gripper open and close commands for the Eve humanoid. So if you're interested in conditioning on the actions, that's available to you. The first task for compression is basically centered around predicting the next token. However, from talking to the comma folks, shout out to Yassine for kind of giving us a lot of feedback on how to make this work well. We don't want to have a benchmark where it's just predicting the next token because that only admits one kind of solution of basically an autoregressive LLM. So we're trying to make this challenge basically admit a slightly larger set of models that you can train. So the benchmark is to basically try to minimize the cross entropy loss on all of the logits of your next frame or your next latent frame of tokens. We've released 2 code implementations in the code base, which is a simple autoregressive LLM, as well as a Genie implementation, which is a recent Google DeepMind paper. And again, this was largely inspired by the comma BQ compression challenge. The only difference being that in our compression objective, we're measuring the cross entropy on your entire frame's worth of logits. Okay, so for the second challenge, oh yeah, sorry. The prize is going to be a $10,000 prize for the first contestant that hits a certain milestone. Because the stakes are kind of high, we want to make sure that the prize is like both achievable but not trivial and also not impossible. So we're still figuring out exactly what the right score should be. But at least the code is kind of available for people to start working on it, and then we'll shortly release the specific criteria. So when you cast everything to an LLM baseline and you implement things correctly, predictably, you do see that scaling laws work. So here's basically our tokenized data. And when we train a llama-style model on the data, predicting all the tokens and all the actions, we do actually see scale, which is very promising. So here you can see the sort of the flops versus the train loss. And if you fit the lowest minimum for the curve for each flop, you can kind of get the optimal compute profile versus parameter size. Okay, the second challenge is a sampling challenge. So we don't want everyone to just work on only discrete distribution modeling. We think that there's a much larger family of interesting generative models that could solve the ultimate evaluation problem. For example, like latent diffusion methods, video generation models, and so forth. So the second challenge is basically to generate the best quality latent in the future. And we're going to use a perceptual similarity metric to score against the ground truth versus the next frame that you're sampling. And the goal of this is basically to kind of encourage more interesting work on test time search. So for example, approaches like ManiSkill can improve your prediction if you spend some time doing compute at test time, as well as diffusion, and potentially even like this kind of new age of MCTS might be able to give you better results at test time. And we see that the kind of things that are playing out in LLM land will probably transfer really well to this. Again, the prize here is going to be $10,000, but we're going to have to figure out exactly what is the middle ground between impossible and trivial. We're finding that next word LLMs are too slow to run in real time for our robotic systems, even at the high level. So we provide an open source implementation of the Genie architecture, which is essentially this transformer that alternates between your temporal and your spatial dimensions. Yeah, it turns out actually that the QK norm is really important for this architecture. That took us a few weeks to get right, but yeah, this architecture is kind of our best baseline right now for the challenge. Here's some examples of our model. This was trained just for like a couple days, so I don't mean to say that like this is the best that 1x can do. It's more like here is a simple baseline. Here's kind of how bad it is. We can definitely do a lot better, but the starting code lets you produce something like this. Okay, and the final challenge is the evaluation one, which I believe is the holy grail of robotics. So we think that in a short period of time, it might be actually possible to do evaluation in learned simulators. So the way we're structuring the evaluation challenge is that we'll give you 10 black box checkpoints for some task, and we would like you to basically find some way to predict the best to worst ranking across these checkpoints. And this will likely incorporate techniques from both 1 and 2, although you can imagine there's actually even more broad ways to solve the problem, such as using an off-policy value function or something. And the pricing criteria are also to be determined because we want to kind of get some confidence of what is achievable and what is impossible. But I can say that it will be a much bigger prize than the previous two. Basically, the structure of the problem is that we give you the MDP, and then you have to score how good it is at the end of the rollout. Here's some numbers on our existing leaderboard. And let me just close with a few open questions. So, it's still uncertain to us whether we should be scaling policies or world models, right? Like just because we see better scaling on image tokens does not actually mean that's the thing you should be scaling up. If at the end of the day, what you're trying to make is a general purpose home robot that can do lots of tasks and chores for people. That's why we're actually trying to bet hard on this evaluation setup where there are millions of tasks, so that even if it is the case that you only want to scale up the policies, at least we have the millions of tasks in a learned world model that we can measure scaling with respect to. Jan LeCun is kind of well known for saying that predicting future images is kind of a waste of time, and maybe that's true. Like the future does contain a lot of irreducible entropy, so maybe those parameters that you spend and all that like GPU time you spend is better spent compressing something that's a bit more efficient with regards to like long horizon reasoning. And then finally, there's a question of like, okay, so if you scale things up and everything works, what happens if it's 100 billion parameters? How do you run it effectively on the real robot? We'd love to have some feedback on how to extend the challenges. So we've set up a Discord. If you have suggestions on what kinds of data we can add to our fleet, we'd love to help you do this. If you want safety critical tasks like carrying hot cups of coffee or something like pseudo-conscious like dressing yourself in a mirror, please suggest that and we're happy to add that. Think about us as your data operations team, and we'd love to also have donors help us increase the bounty. And finally, you can do this internally at 1x. We're also hiring. So yeah, here's the information on GitHub and Discord for if you want to talk to us about the challenge. Thank you very much.
All right, I think we have time for just one question because we are at time. Anyone got one?
Oh, because with the people that are remote.
Yes.
Yes, yeah.
They're gonna be pointing in there, right?
What was that?
This camera looks at them.
Yes, yeah.
And then Brian.
I think yes. Oh, please down in here. Yeah.
Yep, I'm here.
Questions and stuff.
Say it again.
I'll use my laptop for some questions.
Okay, perfect. Okay, so then I guess I don't need. Oh yeah, no, this should be good.
Thank you. Yeah, I'll be feedback.
Hi. That's all right. Should we just shift it?
Yes, I see.
That's I'm okay. Don't worry. Yeah, maybe that's the best meeting.
Right. Oh my God, this is exciting. So much to back.
Yeah. That's as far as it goes.
Okay, no, that's- Okay, thank you for being here, all of you. Hi everyone, so we're gonna start the speakers panel. In order to save time, I will skip the introduction. They have all been talking today, plus I think you already know all of them. So let's see, this is how we're gonna do this today. I will start with a few questions. Hopefully we get the discussion and conversation going, and then we can take a question from the audience. Yeah, we have an hour, so plenty of questions, please start thinking about them. I would like to start the panel by asking you this thought question. What is an opinion that you think is commonly held by our community on embodied AI, but that you think we should rethink about, or we should at least explore in different ways? I'm sure that will open for some questions.
Any order?
Free.
I can do it. I think there's a lot of excellent work in modular architectures in embodied AI, and lots of us have built them, and lots of us are building them. And for those of you who heard my talk this morning, it's no surprise. I'm going to say, I think we should rethink this completely. I think we should have simple architectures trained end to end, and I really think that's the answer to build generalizable robots.
And I'll have some random stuff just to follow up. You mean truly end-to-end, or modular by perception and action kind of thing? Truly end-to-end.
I mean, if you want to bring in outside word knowledge, like for example, you want to train a robot and you want it to learn say, I don't know, cook me, make me a turkey sandwich. This outside world knowledge of what goes in, you're supposed to put mayo and you're supposed to put mustard or whatever. I don't think this needs to be learned end to end inside the parameters of the embodied AI model. And you should be able to leverage a language model for this. But in terms of performing short horizon tasks, I think the true answer that we will all learn in the better way, just like other AI communities have learned, is everything's going to be a clean end-to-end model.
Another volunteer for a commonly held opinion that you would like to invite us to think about again?
That's robot task right there.
I got it. The length of the cables is definitely one.
I'd like to rethink the length of this cable, but then the rest of the thank you, sir. Okay, so I guess I'm representing sort of like somewhat embodied by humans, because we're went into Project Harrier team. So it's the human who's got the body. The humans, already very good at interacting with the world, and I guess we've already moved on from like fine-grained manipulation, because humans just do it very well already. To some extent, there's I think a big question about why we're so interested in robots that do humans' jobs. I think that's something that we should all question pretty severely, versus assistants for humans who would like to be sort of more performative, or in other ways, brought back from maybe injuries and that sort of thing. I think the obsession with obtaining sort of human level, humanoid-like robots is one that I think the whole community should think about, given the both the challenges that apparently are solved by end-to-end learning and fine grain, when actually the real challenges are sort of like timescales of days, weeks, months, years of lives that actually then lead to the context that's necessary to actually do the right action. It's not even going to get started in robotics. So from a point of view of like, let's just assume a second that the fine grained manipulation problem is actually solved because actually humans can do it very well. The real challenges are going to come when we're looking at data sets that absolutely cannot be solved by end-to-end learning. You cannot get a year-long data set and do anything with it. It can't fit in a data center from an egocentric perspective. So I think if you think about it that way around, as in, okay, fine, tomorrow, our colleagues here to solve end-to-end learning for fine-grained manipulation, now what? And it's interesting to ask, so what are you working on? If you're working on that fine-grained manipulation problem, well, humans do it already very, very well. It's not a problem that actually needs to be solved as much. There's some fringe areas where it'd be great, very, very dangerous areas where you don't want humans to be. Whereas actually dealing with context in AI, in the embodied, as in I'm an embodied human, is actually one where we have no solutions. And sure, if you could solve it for humans, maybe it might be good for robots too. But I'd say let's think about the human-centric view of embodied AI more than we currently are.
I'm just curious, what do you envision as the application of the sort of in-context AI, as opposed to use the big models for learning for robotics manipulation? Like, what do you envision the application to be for or assistance, or like what do we do when we solve your problem?
Well, yeah, my problem is essentially the same problem that you have when interacting in normal society, where whether it's cognitive or memory related or otherwise enhancement and regaining things like vision for those who may not have the best vision, or hearing, or otherwise in general, everybody, as you start to move away in particular from sort of a demographic that deals with social media in particular of the current sort and says, well, hang on, what are our applications as people age? The answer is actually you really want to get back functions that you already had just fine with your normal human memory and cognition. So again, it's about sort of like looking at reality, look at your family and friends around you, look at people who need help, look at how teams of people need help with each other, and talk about that embodied artificial intelligence problem. I think it's interesting because otherwise I think there's a dilemma for embodied AI, which is to scratch at the surface of what are really very small problems in the scheme of things, even though they're hard technical challenges like fine-grained manipulation. They're small in the scheme of things. Actually, the big problems are really at the very human level of interaction with each other, and then at societal scales of AI. So, yeah, I'm interested to hear from colleagues who, of course, are solving these very technically challenging fine-grained interaction problems. But I also want to understand what your motivations are beyond it being a technical challenge.
I'll take bait. So would you argue that, I would argue that, as my parents age, I would think that having a robot that would help them with the dishes would be something that the robot would, be augmenting their lives, but still be independently performing the tasks. And so you still need to solve the low-level manipulation. It's not really human AI collaboration. It's human AI collaboration on a longer scale, or, well, they are collaborating to live together, but the tasks themselves don't require fine-grained collaborations. I would give that as a counterexample on why low-level manipulation is important.
Yeah, I'm also pretty much in favor with the low-level manipulation thing. I think we work a lot with folks who have disabilities or aging people, and I think a lot of them do actually want these robots to be able to help out around the home and things like that. I think that's a huge issue, right? Even if something as simple as being able to pick something up off the floor is not trivial, right?
Yeah, I think if you if you were not able-bodied and you wanted someone to like swap the mic and pull it up, talking to an AI about like human values is not gonna
Yeah, and yet here we are, so many humans able to help each other out in these areas. So thank you, by the way, human who's next to me, and I hope you don't get replaced by a robot anytime soon.
So I think that the challenge is not that it's not interesting and important. I just mean if you look at the whole space of problems where embodied AI, given this is this workshop, I do think it's interesting. I'm from a robotics background myself. Why we're so interested in the particular form of embodiment when actually humans are really like quite exquisite embodiment, even when they're not fully abled in that sense. What I'm saying is not that the problems aren't interesting or hard or they won't be useful. I'm saying that just assume that you've solved the fine-grained manipulation problem. So now what? And I'm saying that there's a lot of fertile ground there where you didn't have to solve the fine-grained manipulation problem to be tackling some incredibly hard problems that will also be useful not just for the robot, but also for humans who are embodied via augmented reality and various sort of wearable devices.
Well, we definitely got the thinking going here. We will get back to this definitely. But I still want to have some answers for a commonly held opinion that you would like to challenge. And I'll pass it to Brian that we have online to give him a chance. He has a less of a chance to just take the mics, right? So take it away.
I mean, I'm happy to let you guys duke it out about whether fine-grained manipulation matters at all. So I don't know. I think maybe I'll say one that I'm not sure that I like quite believe in, but I'm curious to hear people's thoughts. I feel like in the language model and foundation model community, people have gotten extremely far with no planning or real like deep algorithms beyond the main learned model. As someone who's like most of my career has been around planning, it makes me like kind of question to what degree do these things actually matter. I mean, there's a few like fundamental problems where you can point to and say, yes, like clearly planning is necessary here. But then when we see this in action, it makes me wonder to what degree it actually is, because most things seem to be done pretty well without it.
Can I add to that? So I think that this is a sort of a belief that I'm trying to figure out how to articulate more formally, but I believe that there's a sort of notion of like a cosmic greediness to the environments that we live in, where an extremely greedy policy due to the very high dimensional nature of the environments we live in, which is not 3D, but it's really like a high dimensional configuration space. A greedy policy can probably get really, really far with doing very useful tasks. For example, like if you want to tidy a home, it might be possible to achieve this with like an extremely OCD greedy policy, as opposed to like a long horizon planner that knows where to get all the appliances and so forth. And I think that like we see this kind of in deep learning optimization, where optimizing in high dimensional spaces using first order optimizers works really well to find some good local data. It might also be the case that like in the sort of high dimensional unstructured world we live in, a greedy optimizer might also have similar benefits, where you'll get a tidy home, but not necessarily like the optimal tidy home.
Yeah, I think that's reasonable. It makes me, I guess if I look at myself as a human, I feel like I probably am very often in this greedy local minimum. But if I then project it onto robotics, it feels like maybe it's enough for robotics to not do it.
Well, I think so. Personally, I guess I'll be the one who somewhat defends planning here. But like, I think that I do agree with everyone here that I think intent is the right way to go in the long run. But I feel like you can think about planning as a way of building in better generalization and data scaling and things like that. And in particular, if we think of robotics as I think it was as instead of requiring like 50 to 80% success reliability, as requiring like 99.9% reliability or something like that. If you actually do have that robot in your home, and we're not in Richard's land here where we don't need this at all, right? Then you need to be able to actually make sure that you can arrive at a solution. So how can we do that? Because currently, I think that we see LLMs and stuff that work really well with a human in the loop. And now I think that assistive robots are a really important use case. And for a very long time, we won't need robots to be at 99%. But if that is the goal, then we need an answer that is not what we have now.
Yeah, I think yes, I'll defend planning as well, just as a class of solution that gets the job done if you need it. But I like your point about interaction with humans and closing the loop. There's something very important, I think, that's been found where we moved from assuming that you give some form of AI embodied or otherwise a task, and then sort of it spit out an optimal solution versus humans interact and get there and possibly even construct what the goal is in a more precise way as they go about doing it. I think this again is another one of these examples where, looking at the problems of embodied AI includes the class of interacting agents that are humans first. Like if you go and talk to behavioral economists or social scientists and ask them, how is it humans are getting on to solve this task? It won't be that they're forming some formal planning stage, but in the end, the abstraction is that a plan got formed and got executed. It's just that's not how they'd articulate it. It got done through interaction, and then sometimes there's emergence as well. But yeah, it's interesting to sort of like if we forget about interaction between even if it's just a robot and the user of the robot. I think it gets even more interesting to talk about planning at the scale of entire workforces. What is the plan to enable that giant group of manipulators that might be thousands of people to actually get the job done? It's not so trivial to think of it in classical planning terms, but it is interesting to talk in terms of interaction between the agents.
I think the longer horizon the task, so for example, at some point I need to go for dinner and then I need to go home. I think this has to be done with some sort of planning. But I would say medium range, after this panel, probably going to go out of this room. And so I have to open the door and make sure I don't run into one of you here. I don't think we should be, I don't think the answer lies in explicit planning. I know this is controversial, but if I had to bet money on it, I would say the answer would be without planning, but I don't know.
Well, I'll take you away to another topic. Let's cover a few topics here. Let's see. I want to bring you back to the definition of embodied AI as a research field with research questions and goals. Yeah, sorry.
There's a question I really wanted to ask. Do you mind if I jump
back?
Go
Go
ahead. So what would convince you otherwise? Like, is there an experimental result that you would see that would be like, oh shit, I was wrong. We got to do planning.
I don't know, that's a hard one to answer, I guess. So what would convince me that planning is the answer? Well, I guess if it, I guess the ultimate answer is if it works in the real world when, for complex tasks where people are moving around and things change dynamically, I guess, well, if it works, then it's a solution that's acceptable.
So what would convince you is the planning people get to it first?
Sorry?
Like if the planning people get to it first, and then they're right.
Yeah, I think it could. Yeah. I think yeah. I think everything that we've seen in yesterday there was a wonderful talk, the parable of the parser. It's talking about how we built all these parsers in natural language, and not we, but someone built it, and then eventually all of that got all of that got consumed by end-to-end models. And there was an argument yesterday saying that object detection and semantic segmentation, all is just another form of parsing which you don't really need. All you care about is you have some task that you want a visual system to do, like assist a human being, and answer some questions about maybe there's a blind person, you want to answer a question, like doesn't matter if you have object detection. I think this is in that vein, this argument. So that's why.
So aren't we already bringing back planning into LLMs though with the MTTS stuff that we're seeing over the last week or so? Right.
Like I said, I'm betting money on it, but I'm not betting a lot of money.
We have somebody jumping in from the audience, so let's get it going.
Just to make things even more controversial. So I want to push back on the premise that these LLMs are doing so great without planning. Why do we need planning at all?
Are they?
No, they're not. Have you guys ever used an LLM to try to produce stuff that you wouldn't be embarrassed to say, I don't think they are working well. I think they could use a bit more planning personally, to look up sources or stop them from hallucinating. I know hallucination is sort of in the eye of the beholder, but I have not, I tried once a month or so to get some kind of usable output from an LLM. I can't, I never have. I would love to be wrong about this, but I can't. Admittedly, no. Maybe I didn't plan.
Well, so I do agree with you, and I think I said that is, as you go longer horizon, I think planning can help. But I think we are currently using planning for all kinds of short horizon tasks, and that's where I'm betting my money is. I think you would. Those methods would probably be, consumed by an end-to-end model that does not do explicit planning. I know one of you is going to ask me where's the boundary. I'm not going to take bait there because I really don't know. But shorter the horizon, lesser the probability that planning is the answer.
What generalizes better today?
Neither. I mean, I don't think anything generalizes.
Or better?
What?
As a comparison, just as a comparison.
I mean, you're comparing like, forget all the benchmarks we have and the 3 experiments that we run for a paper. And you're comparing like 3% versus 2%. It's all noise.
Got it.
Well, I'm sorry, but if you paid attention to my talk, you would see that the planning entry got like 4 times the learning based one. No, I don't think that's really that. Yeah.
Just for the record, I'm completely baffled. I must be from like a too older school. So planning used to define a thing where if you had a goal and then you'd like find
we're talking
you and so so what does it mean to have this conversation, right? I mean, you can implement a system that effectively does planning in several different ways, and maybe it is contentious as to whether or not you can implement it with an autoregressive model. I think it might depend a lot on the dynamics of the problem as to whether or not it's closed or chaotic or whatever, without any kind of feedback. But then there is feedback. That's the point with LLMs, right? So an LLM that has a human in the loop is no longer just a forward prediction system. An agentic implemented LLM where it can do a few loops and keep hold of what was asked at the beginning without it corrupting the context window, is no longer a trivial implementation of an autoregressive model. And all these are fine because it's a class of problem with a class of solution. So sorry, what is the problem again with planning? Clearly we need planning because it's a definition of I have a goal and I want to get there, and then I can implement it in different ways. Maybe I can implement it in a model because it's such a trivial problem.
I mean, I do think when we're talking about planning, that's all right, but we're talking about mostly about like whether or not search, like particularly like iterating on having a system for iterating on solution input, right, automatically is useful, right? I think that's fair, and you can implement this with learning, like with the MCTS, LLM stuff, right?
Yeah, agree.
I mean, it's trivially useful. The question probably is it efficient relative to your compute resources, right? If I can, then I'll allow my LLM, if that's what we're playing with, is saying something that isn't planning, and I'll have the distribution over it, and I'll check where it gets against relative to the goal state.
Well, I think the bigger argument is usually not about the compute resources, but about the human resources it requires to put that algorithm together, and whether or not you need to adapt it to different use cases and things like that, right? Which is where I think.
So in like 2014 to 15, there's like the really cool guided policy search work from Chelsea and Sergey, where they basically solved some simple manipulation tasks by combining like a system 1 and system 2 thing, where at test time you have to actually the sort of local policies are trained using IOQR like kind of planner based algorithm, and then you distill that into a system 1 thing that can do the task. But today, when people solve those specific tasks, no one really uses a system 2 thing anymore. They just like imitate it directly from scratch. And I think like what will sort of always happen is that system 1 systems will kind of get better, and then people will say like, oh no, like it's hit a wall. You got to add a system 2 thing. They'll add it, it gets better. But then like a couple years later, the system 1 thing will then catch up and do the thing. And I think it'll just keep being that.
So maybe let me rephrase it. And maybe the thing that's changing is the definition of what a goal is. Which used to have to be defined in kind of quite precise terms, is no longer needing to be defined in very precise terms, for example, coordinate frames of arms and manipulators interacting with contact. And so then what we get to is actually the social construction of what a goal is for a human doing useful stuff. And we get back to it's about interaction between the two agents or more, because the definition of a goal is actually never clear for more sophisticated things. For example, even picking something up, once upon a time, picking it up under an energy efficient trajectory, picking it up with precision. Well, actually, people were just trying at all to pick it up, right? And so then they'd have all these various ways of formalizing it. But actually, now that we've got systems that are good enough in several different ways, maybe through, the various different robot morphologies to solve it, certainly lots of different morphologies can pick stuff up without lots of planning simply by suction, for example, with a very trivial kind of forward model or planner. But is that what it is that we are, what we really care about is getting away from having to precisely define our goals. And if that's true, then actually that's because you're going to do interaction now, continuous interaction. Or are we just talking about fine-grained planning and that's going away?
Maybe what I was referring to was not when the goal is precise or the goal is ambiguous, but I guess when the environment is extremely well specified, or when we can assume perfect knowledge of, like, for example, I think if you're working in a closed world setting, you have to have this robot that works in a factory, and this red block comes down at exactly the same location every time. Then I think, like what I was referring to as planning, a planner can probably work really well. It'll be explainable. It'll do exactly what you code it up to do. But if you want a robot to, walk around CVPR and do something in a more unstructured environment where you do not have perfect perception, then I think, I don't think those methods are going to work very well. But it's interesting that it's interesting that you have, instead of thinking about the environment as underspecified, you're thinking about the goal as underspecified. And I think that's also valid.
I think we do see algorithm or planning algorithms that would work in that situation. We see plenty of them, like these POM-DP planners, which can handle crowds and have robots moving through crowds and so on. I think the question always comes with planning, and the argument against planning doesn't come back to any particular capability. It comes back to how much effort it takes to implement that capability in a robust way. And the question seems mostly to still be open because we don't have systems that are 99% reliable and loyal.
So, for example, do you expect to be able to solve Go without some sort of system that defines a state, even if it's complete, just using a forward model? What would that look like?
It can beat most people, but not the best people.
So maybe the best people will use this other thing, which is trying to get towards a goal, be it ill-defined or otherwise.
I'm forced to interrupt you to change the topic. We have we have many questions. He asked first. Christian, I think. Yes. Go ahead, please.
So someone was said that experience will tell us, right? Experiments will tell us whether planning is needed or not. The question is the following: do we even have the complexity or the scale in our experiments which can answer this question? We're very short example. For example, episode length and environment size. So let's take a very extremely simple task, navigation. So there's no moving object, there's no installation. If I need to run around in Seattle and find something, and I haven't seen Seattle, I will not necessary. I'll just need to go roughly this way, and I will just have local exploration combined with lots of greedy search. I really like what Eric said, that planning can be seen in very many cases as some greedy policy high-dimensional search. Right. But now let's take the other side. If I'm living here, I have seen Seattle, this neighborhood for lots of time, and I will do planning, I will be much more efficient. And planning will happen. But in all our challenges in Embodied AI, we don't do that. Our episode size are limited to 500 steps, 2,500 steps. Our environments are Gibson, HM3D, etc. Obviously, we don't need planning in this. But the robot is not fired up when it starts the episode. The robot has operated for weeks around. It should have a mental image of what it did for weeks. And then, that's my opinion, planning can be helpful. And whether it's true or not, that's what I think is we didn't do the experiments yet to confirm it.
To be honest, I think maybe my controversial opinion, which I didn't say earlier, is that I think we generally build benchmarks so that learning algorithms work. So it's not that surprising that learning-based end-to-end stuff always looks better than planning. I think you would probably end up with very different things if you picked some random hard task and tried to do it. Like solutions for like the DARPA Grand Challenge or DARPA Urban Challenge or DARPA Subterranean Challenge. Like those are big goal-oriented challenges, right? And none of those use end-to-end learning systems. So anyway.
All right, we're at a vision conference, so I have a vision question. How much do you think of robotics is currently held back by visual understanding, either like of the geometry of the world and its dynamics? Is it contact modeling and control, or is it this like nebulous third thing you guys are yelling about the plan? Where do you think the like biggest open issue is?
So I can go first. So this morning I presented some work which showed that, it was not a very complex task, object goal navigation. And we showed that this end-to-end learning with imitation learning gives you, some 60%. And then if you just solve last mile detection, right? If you assume last mile detection is solved. So you don't know anything about the scene, you don't know where the chairs are, nothing. But if I have to look for a bottle, when I see a bottle, I tell you the coordinates, only when I see it, right? You suddenly get like a 30% improvement. And this was sort of a controlled study that was, that we were using to answer the question, if some part of detection is solved or some part of perception is solved, can we get a big jump in the ability of the robot to navigate around? And we saw this, you can see this in sim. And I think we've some preliminary things to suggest this in the real world. So I would agree with you that I think as we get better visual representations, I think things are going to get much easier. There's another experiment that also proves this, not just in our papers, but in many papers, is that we've been seeing over the years that as your visual encoders get more capable, your downstream tasks are improving quite a bit. So that's the second piece of evidence. I think it's not just a matter of like, oh, if I can see the object, I can navigate to it. I think it's a matter of if the visual encoders, which let's say they're frozen during training, are doing more and more of the heavy lifting, the parameters in your neural network can spend more of their time on producing the right action. And so we've seen that if your perception gets better, your reinforcement learning trains faster. So I don't think perception is the only problem. I'm a vision person, but it's going to take things to the next level as perception gets better.
This is like a follow-up directly to that. So a lot of the demonstrations, like videos that we saw today, we've had robot images, and they're taking these like fisheye cameras that are like 200 by 200. I don't think people let this do where we have screen iris sensor suites and depth sensors. And if you guys are saying that like, okay, perception, like representations are a problem, then why do you not use better sensors? Right? Why are we still doing 200 by 200 images with Retina 18?
I completely agree. I think you should just buy high quality cameras and put them on your robots. It's just there's no need to do 200 by 200 unless there's some niche application where you're doing like some sort of surgical thing, some surgery, and you need some camera. But if you're constructing a robot today, just put a better camera. And we see this in vision that higher resolutions are leading to much better performances in multimodal foundation models. This is a well-known thing.
On the back, you have a right again.
Yeah, nice. Nothing forward-looking. So suppose that your favorite technical method, like that you've been discussing, whatever that means for you, successfully reaches the core technical goals in front of you, you sort of get a minimum viable product for some kind of robot. But then on deployment, the system either fails or not, or causes scanning or something like that. What you see as the odds and potential mitigators.
I can take that one. So, so basically the question is like, in deployment, what happens? What is the most likely cause of some sort of scandal? And then what's the mitigation, right? I think that in the short term, the most likely thing is that the robot does something extremely dumb, like fall down the stairs and like, fall on a kid or something. So that would be by far the most likely outcome. And it would be potentially for extremely dumb reasons like, oh, maybe someone pushed it off the stairs, but still it's like your fault if the robot falls down the stairs, right? So I think that is being pretty likely. Or for example, you're doing the classic bring someone a Coke and then you drop it and the Coke explodes. Like that's also extremely highly likely, I think, which is much less serious, but probably going to happen. I think the mitigation is that we probably have to adopt a lot of the safety and alignment techniques from the LLM community to give these general purpose robots a common sense understanding of how to be safe. At least that's the kind of best guess I have in terms of how to avoid these pretty general, open-ended safety scenarios.
I think that's a good point, Eric, about the common sense that's in these. I think in the past, the way that we thought about safety in a lot of cases is extremely explicit, hard constraints and some clear representation of the environment. I think this is really powerful that we now have the ability to have a much more semantic reasoning over safety. I think it can provide a lot of additional layers of safety that were otherwise very difficult to express.
I think it's also going to be important. I mean, the cases that you suggested are going to happen on day one. The first day you ship a robot, those two things are definitely going to happen, right? But I think it's also going to be extremely important for robots to be able to say, sorry, I can't perform that safely. And so the ability to say no is going to be an important, I think, research problem we should all be thinking about. Well, for that, you should first be able to perform the task. But once we get there, then you should be able to predict if you can perform it safely.
We're going to jump into David.
Just a quick question there. So, on the safety front and the reliability front, a lot of these systems are getting complex and involve more big models. How can we sort of decide upon the standards, reliably? And we can say a embodied AI system is going to work up to this percentage of reliability, rather than sort of saying, oh, the system knows blah 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 blah, but then someone can go how do we sort of put forward systems that we can say, we should work within this percentage of safety?
Yeah, David, let me take a crack at that one, because I think probably again this sort of if I have my roboticist colleagues, there's already agents acting in the world way before we have humanoid robots in the home. And so here's a question: who here, within the next 5 years, envisages giving their agent AI assistant, ChatGPT 6 maybe, their credit card details so that they can go and start to act on their behalf? Got one person over there. Definitely want to sign up at OpenAI 2, one on the panel. That's great. There's I don't know, 2%. Okay, so what you've got there is definitely actions that can be taken in the actual world that do deliver actual physical consequences. And from a point of view of us wondering about those standards, that is where it will play out first. There are plenty of consequences, even in sending a digital message, long before we worry about an exploding Coke can, or not, frankly. Even in the driverless car community, way before those humanoid robots, So I do think it's very interesting. I think a lot of the things we use 200 by 200 images in robotics. Why is that? Well, because of end-to-end learning. Because if you don't do that, then your data sets get too big. Not because you can't get better quality images than that. And yet a human requires on the order of, well, let's talk about it in terms of megapixels effectively, because otherwise they don't have 20/20 vision, which is necessary to see a 12-point print on your mobile phone within the foveated region. So what we've got is sort of a complete disconnect between where robotics actually is today in the real world versus sort of where agents and LLMs are getting. And of course, this question about, does it need to be goal-oriented? Will it have actions? Will you allow it to take agency through, basically the various means it can already have? And that is where it will play out first. And if we don't see it play out there, then we will not see it play out in physical robots. It's as simple as that. Oh, I don't know if that's a controversial point of view, but I think that's where it will play out. I agree.
That's where it is playing out now.
Absolutely, absolutely.
That's trying to figure out what that's going to be for us and what we should do. Someone else is going to have for upon them.
Strangely, I think it's the same community. So if we see a bifurcation today in the community, even though we're at a computer vision conference, the concept of embodied AI that has access via wearables is going to happen before you have a humanoid robot. It is going to need to have a semantic awareness of your environment. It's need to deal with the uncertainty of stuff it can't quite see and tell you, I can't quite see that thing, when you're asking about it. All of those things are going to play out first in spaces where there's commercial advantage in developing those things so they can actually be in the wild, to get real data at real scale with real commercial application. And in the meantime, there's actually some very exciting work that seems to be going on in the sort of like space of making physical robots cheaper, but they're still cheaper in a very kind of like toyish way. They're not cheaper in a sense of sort of like a robot car is cheap so you can go and play with it. And even if you could, the consequences are too terrible for you to go and play with it on the road. So what we've got here is a giant gap, that has to be breached by or bridged rather via like these other mechanisms in perception of systems that are worn by humans, in actions that are taken by internet scale agents, and all of the safety measures and all these kind of exactly following the current sort of chat systems. We're going to see it play out exactly in those spaces. And then we're going to, it's not going to be a credit card that it can use. It can open a door for you as well. But actually by that point, you will trust it with your credit card. So as to whether or not, like, it knew that that was the right kind of shoe for you and that that was what your pet wanted. And, it didn't kill your plants with the stuff that it had already ordered for you that you then put into the mix or to feed your cat, etc. A lot of those actions are very real with real consequences, and you're the manipulator. You're the thing that does the actions. Now, if we can't bridge that gap, solving the fine-grained manipulation problem so that, the robot presses the Amazon button, and unwraps the Amazon box is the least of our worries, right? So I think that's probably how it's going to play out over the next few years.
Seems like we have a bonding question right here.
I think that was a great question, and this is kind of might be a bit similar on the lines, but something I get really deep into is like my team on benchmarking right now with the models that we have, and I think it's really interesting what Scale AI is doing, but thinking more so on the benchmarking of these models, whether you call it a general purpose robotic model, and how should we kind of look at that or think of that? And there's like kind of two sides of it, and a lot of today we're discussing the simulation and the training of these systems and benchmarking there, but also trying to do that in the real world. But there's also much you can do because of the amount of employees or engineers working in training that system. So I'm curious of how do we really think through benchmarking of with these emergence, if there will be these emergence of these very general GPT-4 style models for the physical.
So how should we think about benchmarking? How should we think about benchmarking like a GPT-4 for the physical world? I think that this is something that I feel like I've thought about a lot. I think that we just need world benchmarks where we can like reproduce and test these things in different environments. Like you need to be able to easily download someone else's model and try it out. I actually think that like the way OpenAI does things where you just have API access and can run it on your own platform is a great way of doing this, right? People can trust those models to the extent that they do, which of course you can argue about, but people do trust them for the tests they use them for because they're very easy to test and you can run it and you can try it on your problem and you know what it's gonna do because you've seen it do stuff. I also actually mostly disagree with what you said.
Oh, good.
I think that I just think that like a robot in your home is probably going to be far less harmful than giving a robot your credit card. Honestly, I think that a robot, like there's plenty of things like low-hanging fruit that I feel like is very useful to have a robot that can do manipulation and navigation and planning and grabbing things and just whatever. Like the nice video that Eric showed earlier of the robots like bringing you a drink, right? I don't need to give it my credit card. It can find these things. We can do similar to what self-driving car people do and have like multiple levels of safety to make sure it doesn't run over a kid or fall off a cliff or something, right? These are all solvable problems, I think. But giving a robot your credit card and telling it, hey, buy my wife a present or something like that is an insane thing to do that I cannot see myself doing in 5 years, personally. That's
But you could imagine having the stretch go to the corner store and then like, using the contactless payment terminal and then bringing the thing back, right? For
If-
someone who's not able-bodied.
yeah. If I told it like go to this store, buy me this thing, then I could probably see that. I don't see a way of making that safe, but you are also telling it to do this. At which point, maybe it's like maybe it can tell you that's probably a bad idea, but I could try it.
Well, you can certainly put a gate on it. You can say you're authorized to spend $6.
Right. Yeah.
You're allowed to buy
Then
this.
it has to. I don't know. Like if you maybe but then you're setting the bar pretty. If you can actually make sure that's getting into a complicated.
Before we design the final products, let's get back to the science of how we're even trying to achieve this. I wanted to talk a little bit about simulation, because clearly, if you see all the talks or the challenges, we really use simulation heavily in this community. One of the reasons is that apparently the only thing we all agree on is that scaling up helps. Any booms? Okay, so oh, there's one. Okay. But we all seem to be pursuing more data, and with the exception of having the glasses from Project Area, having simulation is pretty helpful. At the same time, it has the challenges of building the actual simulation. We saw talks on that. There are new trends in generative models to be able to generate the assets, et cetera, et cetera. But we still need the real data at the moment that we want to do sim to real. So I was wondering how you think about those trade-offs in your particular applications. If we think about humanoid robots, there have been a lot of work lately on trying to collect data from the humans directly, less of simulation because we cannot simulate the tasks. So talk a little bit about the trade-offs between simulation and real data for your respective applications.
I think today, so I'll condition that on today because, technology progresses. But I think today, I would say, if you're worried about navigation problems, go here, take a picture, send it to me, avoid an obstacle, go find this, go do, here's a, the robot has a basket, I put a Coke, just go and, give it to my friend who's sitting at the end of the room. If it's navigation, I don't think you need any real world adaptation. I think this is solvable only in simulation. I know this is a bit, so people might disagree a little bit, but I think you don't need any real world adaptation. Manipulation, because of the limitations of, there's a trade-off between how high fidelity physics you want to simulate and how, fast you want your simulator to be. And that trade-off often means that you do not have high fidelity physics, which means you probably have to do a little bit of real world fine-tuning today in manipulation, or a lot of real world fine-tuning. I think that amount of real world fine-tuning is going to keep reducing because simulators are going to keep getting better. So hopefully, asymptotically, we don't need to real world fine-tune.
I guess for me, I sort of feel like scale in this case is really, you need to think about what axis do we need scale on. If it's just sheer quantity of data, then obviously simulation can work quite well. But really the ones that matter and the ones that seem to be challenging are like real diversity over tasks, both like physical diversity, certain things that are actually pretty hard in semantic diversity, things that are a little bit more difficult to express through simulation. I think like if I wanted to go and like manipulate a tissue, designing that in a simulator is relatively complicated, but here's a box next to me and it's like extremely easy for me to gather data with a robot doing that. So I think for most of these like really challenging things, the things that we're struggling with right now, I actually see the real world as in a lot of ways a better place to gather this quantity of data. I think what sim can bring us is really fast feedback, okay, like of evaluations that this is working and this isn't working. It's really easy to iterate and debug in that. But I'm not sure that outside of things that, I think navigation was a good example, but in manipulation that it has as much of a place as we might think.
So I think simulation is most, I think this is a good point, but I mostly think that simulation is good at like kinematic kind of problems where you don't really need to deal with lots of complex interactions or like the weird physics of simulating something right now. Now, hopefully, of course, simulation will get better, but like let's go with navigation, right? So I think for 99% or 90% of the time, I think you're probably right. But one thing that you probably have is that the mobile robot is, maybe the mobile robot is running like some kind of controller that someone has spent a bunch of time tuning based on real data. Maybe that's not, maybe that's even manually tuned. If the robot is doing like accelerating and slowing down, it's got like, maybe it's running NPC or something on board, which is, we're getting into planning land again, right? So basically probably are not solving the whole problem in simulation. You're probably still solving it with a lot of real data. And I think that this gets even more pronounced once you get into things like, I've got to have my robot go over carpet. I've got to make sure that I've got to, it's got to accelerate and then slow down and ramp in this right way so that it can go around a corner and at speed or something like that, or go off road if it's an autonomous vehicle. There's all kinds of stuff like this that I think is not well modeled. And so there's always going to be a role for real data.
If you learn a world model from real data, then you kind of get the best of both worlds. This is with a big, asterisk that like it has to work. But if it does work, I think that's that kind of gives you the benefits of simulation and also the real world feedback loop and not having to model tissues. I think there's a reasonable chance that it actually can work with the sort of latest generation of video generation models. And also the robot actually might even improve fidelity because the data from context actually gives you a lot of information on what happens in the world. So unlike, it might actually end up being sort of easier than the unconditional video generation problem. If you have a system with high torque transparency that can see actual external wrenches on the links.
Follow-ups to the, yeah.
Something that's been brought up again and again when you talk about data is diversity of the data. So what I want to ask is, what are your strategies for improving the quality of your data sets and maximizing that diversity?
Yeah, I mean, here's one for sort of like realizing the sort of potentially what comes before full-blown robotics, which is solving a ton of the perception problems, a lot of the, what might be long-range planning problems, possibly implemented in different ways, and doing it where the human is wearing wearables and you've got all the same problems. You just don't have to solve the fine-grained manipulation problem. So why is that important from the diversity point of view? Well, because I mean, you perhaps can see there's Ray-Ban Meta today. It's a product that exists. These are glasses that people can wear and start to capture data at scales of product. Aria is our research device. That's, it's only a few thousand devices, but they're out there for free with the academic community and collecting, tens of thousands of hours of real-world people interacting. I really can't see a way of bridging the gap without going through that space. I think what might be going on is that people don't know how big the problems are to solve once you get away from the fine-grained kinematics and dynamics problems. Like the problems are far bigger than that. Those are definitely problems, but then there are the problems of exactly us interacting, the fine-grained problems of understanding the social, like navigating the social, which is like potentially much bigger than sort of like the problem as to whether or not I can get over the carpet. Do it right and the human will carry you over the carpet if there's a human nearby and so on, but do it wrong. So I think I get back to like, what do we mean by embodied AI and the problems in it?
Do you think the social, do you think the social dimensions of like how people interact with whatever is wearing the glasses would be very different if the person knew that the the thing wearing the glasses is a robot versus a human? And if so, then does that mean that you actually need to collect data with those glasses on robots?
Yeah, I think that's a very interesting question, which gets at the heart of like the motivation, which was very sincere on my part, of humanoid robotics. And from a humanoid robotics background, we were doing biomimetic robotics, where we had tendons that were like humans, and we were solving problems that made robots look and move like humans, because we thought there was very interesting, important problems to solve with exactly this, that otherwise the gap in interacting with humans is also unknown. It's also interesting, it's technically interesting problems for simulating that stuff. But I agree. The thing that I can't quite get over in my mind is sort of like, what do we mean by the problems of embodied AI that need to be solved? If we could hold on to that for a second, we might have a more diverse discussion even, because I feel like we're skewed in the direction of fine-grained problems, because they are the hard problems today in autonomous robotics, but they're not the hard problems of tomorrow. And that's, I think that's fascinating, from a point of view of the many different morphologies of robots today that are nothing like as sophisticated as our humanoid robots today. And in principle, they can do quite a lot of manipulation tasks, thinking they're in terms of sort of other animal morphologies with very simple manipulators relative to what we have. So yeah, what do we mean by embodied AI again?
We're gonna get back to the definition, which is what I wanted to start, but we have a burning question here. He has been trying hard, so.
Yeah, so if you were given like all of the H100s that Facebook bought from the media recently and like had the entire Facebook AI research team proposal and you had a bunch of CapEx to partner, do you think that it's like scaling up multimodality, right? All the text, all the video, all the images, like throwing every problem formulation into some really big model? Do you think the representation that ultimately learns is sufficient to then train some policies on top and we'll actually get where it needs to be? Is that going to give us a step function unlock with then scaling up SAM to the amount of data they had so we can solve segmentation?
I don't think scale, when implemented in a very raw way, is going to be the answer. I think the key is high quality data. So, you said, you have all the H100s and you have all those bright people in Facebook, and then you throw all the data on the internet at it. I don't think that is the answer. You need scale, but you need scale with very high quality. And so I would, just my 2 cents there, that if you want to solve the perception problem, I think stapling all the websites together isn't going to get you there. Sorry?
Otherwise, they would have solved.
Otherwise, they would have solved.
What if you also stuck all of YouTube in? And like,
Yeah, I mean, I'm not suggesting that you won't get an improvement, but for example, I mean, I'm just guessing here, but OpenAI's visual perception models tend to work much better. Forget the benchmarks, tend to work much better when you actually give it all kinds of tasks compared to other models. And I believe the reason is that they just spend a lot of time thinking about what data they're putting in. I don't think they have any other secret sauce. And I think that's probably I'm just guessing here, but I think that makes me believe that whether it's in vision, whether it's perception, or whether it's in training these end-to-end policies I'm advocating for in robotics, I think we don't have that clean data yet. We don't have that high quality data yet. And how to create that data, whether it's in simulation or whether using a little bit of real world, ego data, I think that's going to be key.
So wait, isn't that, just to go back to the question there, but isn't that an argument that our algorithms aren't good enough? Because like humans learn all this stuff off of pretty bad data, like really whatever we see. So
I'll take that point and ask an opposite question of what he asked, but is connected with that. If you have very few GPUs, what research would you be working on today?
I can answer that because 1X has very few GPUs. So everything you've seen in our public demos we've done on like basically single 4090 cards. And we are a little bit on the far side of like anti-scale, but and we do need to scale things up quite a lot. I would say that like you can get extremely good memorization results on very small amounts of compute. And that can go a long way because like once you verify you can memorize, then it's kind of you verify the correctness of your system. Then you can like scale things up, and I think a lot of people often scale up before they check for correctness. I think if you are also scale bottlenecked, you probably just have to like ride the open source wave of models or rely on APIs. And there's nothing wrong with that. You can build great products and build really good working systems using kind of the API providers.
I want to take it.
So you said we had just very few GPUs?
Yeah, like not at the scale that you're probably working on, but
no, we're working on
a lot of researchers don't have access to massive clusters. And the question is how do you produce interesting research? And probably there is a lot of interesting research there.
Yeah.
So that's what I want to focus.
Well, let me answer a slightly auxiliary question. If you had very few GPUs, how do you produce effective solutions? I don't, some people would consider that interesting and some people don't. And I think I would focus on data quality. And that's, that's what we're currently working on. We don't have a lot of resources because we're not a big company. So finding the right recipe for creating your data, I think it works as a huge compute multiplier.
I guess.
I'm sorry, go ahead.
Yeah, I was just gonna say that. Yeah, I feel. I mean, along with what everything's been said here, which you can actually learn like pretty good, policies for specific things on much smaller data and focus on sort of efficiency and areas like this. But I mean, we all have access to like APIs and things like this that don't require you to have these like a ton of GPUs. In the past, you might have needed to be part of something to have any access to what's now just like open source and out there freely available, or for cost some small amount of money. But I think the fact that like these large models are actually available to us opens up a lot of research progress for sort of everyone without requiring a ton of overhead and compute on your side.
If you're also compute poor, you can open source a benchmark challenge for people to donate their.
Well, we are really actually almost out of time, minus 2 minutes. So I'm sorry, we're really out of time. I want to give you a final row of thoughts, and I actually wanted to know in your most positive dreams, if we have this workshop next year, what would you love to be here showing up next year? What do you think the progress goes towards?
Yeah, I mean, if I was to have my dream, there'd be a much tighter community of embodied AI, really looking at the opportunity for, given we're at CVPR, where this embodied AI is active vision, which is a term I haven't heard in a long time. But at the heart of it, we've got currently this kind of like dilemma in modern AI that uses absolutely insane sized data sets relative to what we think humans post-evolutionary scale learning need to learn to be, decent humans, or otherwise animals are all the same. But I mean, to me at least, it looks very obvious as to like what we can do here, because you don't need 12 megapixel images at 60 FPS times like a day long times a year times whatever data sets. What you need are properly embodied data sets which make use of the fact that manipulation of the environment changes sensory observation. Those sensory observations are actually incredibly sparse, relatively speaking. Most of the environment is not changing most of the time. Most of the pixels in most images are redundant. Once you factor out various things that change, like lighting as a function of, weather and otherwise like the day and shadows and all this sort of thing. Now, evolution got us there through like a very crazy tree of, creatures that solve lots of these problems before we get to the sort of scaled learning from sort of like, a baby onwards. But I hope that we'd have closed the loop on understanding that the kinds of data that have been used for internet scale AI are exactly the wrong kind of data to scale to embodied AI. And hopefully we'll have closed that gap on sort of like the future of computer vision in active vision as it used to be.
And I like that. I agree with that. But so my thing is going to be a little bit less technical, which is that I really hope next year that we just see lots of robots and lots of interesting like real environments and in homes and things like that, and less. Yeah.
Yeah, I was also going to give a slightly more boring answer, and I was going to give a very similar answer. I would love to see next year all the invited speakers bring a robot along and showing a real demo of what's working and what's not working. I don't expect a lot to work next year, but we're working in embodied AI, and we're all saying, "Oh, real world is so great," and then we don't do any live demos. So I think proof is in the pudding. So I would love to see that.
Richard will drink his robot.
Yes, this is something I really like about RSS, is that they have like a big demo track now. That's what I really think that we should do.
Maybe Brian, and then go ahead.
Yeah, maybe that's what we should think about when we're all sort of putting our brains together to organize the next version. Is dedicate some time towards real robots.
Maybe Brian and then
Sure. I mean, I think I just echo what everyone said, that, yeah, like having a real robot there doing something that I can then interact with and see, you know, how robust your policy is. I'd be pretty curious to see that, and I think we'll be at a point where we can do that, where we're in a place where we really believe that that things are working a little bit.
Yeah, plus one to what everyone else said.
So you're bringing the humanoid?
I would like to attend next conference as a human.
Well, thank you, everybody. I think that closes up the panel, please.
So I just wanted to thank, all of our panelists, speakers, our organizers, Claudia, Luca, all the rest of the team, and everyone that came and made this a standing room only experience. Thank you all so much. This has been Embodied AI 5. We'll see you next year at Embodied AI 6.
Be interesting to see a position paper on whether or not embodied in physical robot.
Thank you.
Really,
Thank you so much. Thank you.
No abounding in terms of safety.
Yeah.
Honestly, like the way robots are right now.
Really nice. Hold on, because you said the keys.
I think,
What kind of things are